1 minute to start. Okay, dear colleagues, I think it's time to start and to start the open ceremony of the 6th summer school on nanophotonics and metamaterials. Let me introduce myself. I'm Andrei Bogdanov. I'm one of the chair of the school, and I think you can also see the second chair, Valentin Volkov, from Moscow Institute of Physics and Technology, and I'm from ITMO University. So as I told you, this is an annual event, and unfortunately, the second year in a row, we have to arrange the school in online format. Hopefully, maybe next year, you'll have a chance to come to St. Petersburg in person and visit our department, our faculty, and our university. So here you can see the organization of the school. So this year, it's the first time when we arrange this school in collaboration with our university. So this year is MIPT. The program chair is Ivan Yorsh, and the school secretaries, these are Anastasia Kopsova and Daria Kravko. You could contact them for with any questions. So, and it's not occasional, this combination of organizers, because ITMO University and MIPT is connected not only by some research field, but also some history. And I recommend you to have a look at this very short movie. It's like 3-minute movie about the historical background of our departments and our universities. So, and let me say a couple of words about Faculty of Physics. We are quite young. They are only 10 years old. And the head of the School of Physics and Engineering is Professor Pavel Belov. And our scientific advisor is Professor Yuri Kivshari from Australian National University. So we are quite big. We have more than 150 students, more than 80 postdocs, and many PhD students. So, and we have also many open positions, and you can find all the information at our website, and I provide a link to our website at the end of my talk. So we are quite young. So the average age of our employees is just 28. And if you're interested to join our team, please visit our website and see some open positions. So we are trying to do interesting cutting-edge research with breakthrough results, and we base our work is based on collaborations with different universities and research centers. It's not only scientific collaborations; it's all education collaborations. So with double PhD programs, double master programs, and etc. This is just some featured research on the cover of the prestigious journals. So we are trying to publish, of course, our results in the best international journals like Nature, Science, Physical Review Letters, also, and the full list of our papers you can find at our website. So we are, because we are quite big, we have many different directions of the research, which include optical and microwave metasurfaces, all the electric nanophotonics and topological photonics, biophotonics, nano-optomechanics. This is not only, it's both in theoretical, experimental, and numerical science, and also quantum nanophotonics and wireless power transfer. We have many laboratories which are doing research in these directions. So, and our faculty is not only sciences, of course, it's education. We have several bachelor programs and several master programs like nanophotonics and metamaterials, and I'm also served as a head of this master program. It's international program in that all lectures are given in English, We have scholarships, and if you are planned to enter some master programs, you could consider this option. Also, quantum materials and hybrid materials, they are also international master programs, and you can see also the detailed information, these syllabuses of the courses at our website. So, and this is a link to our website. The all actual information about seminars, about different events, you can find there. Follow this link. So, and I'm very pleased to say that this year this school is supported by journal Sensors. It's by MDPI Publishing. This is open access journal, and the best poster award is sponsored by the journal, and also we will try to select the best research, and the journal will provide some vouchers for with a discount. The standard discount is 10%, but for the best research, the discount can be up to 50%. So, and now I'm give a stage to Professor Valentin Volkov, and he will talk about his research center on photonics and 2D materials. Valentin, the stage is yours.
Andrei, thank you very much. Just give me a second. I will. Okay. Yeah. Just a sec. It's coming. Can you see it?
Yeah.
Okay. Okay. I would like, of course, first of all, to welcome all participants of the summer school on photonics of 2D materials. It's my great pleasure to say a few words about our center. It's called MIPT Center for Photonics and 2D Materials, and so I think it's a perfect match with the subject of this current school. So, and it's placed in Dolgoprudny. It's a suburb of Moscow, very close to Moscow, at the Moscow Institute of Physics and Technology. And the center, well, Andrei told that his research unit is very young, but our center is really young. It's a couple years old, basically. We just physically appeared in the, well, I think at the end of 2018. And at the current moment, center consists of 8 labs, and 2 more labs coming are going to be launched very soon. So I'm a director of the center. Konstantin Novoselov, who is basically, of course, directly connected to the subject of graphene and other 2D materials. And of course, he's directly connected to the MIPT in general. He is a member of the MIPT supervisory board. He's also academic supervisor of our center. And I'm very pleased to announce that within this year, we are launching a laboratory of programmable functional materials, which headed basically by Konstantin Novoselov itself. And one more lab is coming out this year. It's International Laboratory for Advanced Nanophotonics, which will be headed by Luis Martin Morena from the University of Saragossa. This lab is launched within the Mega Grant program, well, this year. So right now, I mean, as I mentioned previously, lab center consists of 8 labs. The center called Center for Photonics and 2D Materials, and this is because historically many labs, at least half of the labs of our center, they're kind of connected to nanophotonic subject. So we have the laboratory of nano-optics and plasmonics. That's my own lab. We have terahertz spectroscopy, microwave photonics lab. We have a couple of labs which has basically 2D materials term in their names. So it's 2D materials and nano devices and 2D materials for optoelectronics. And then we are also very much interested in the quantum nature of low dimensional structures. So we have a couple of labs, topographical quantum phenomena in superconducting system labs, and magnetic heterostructures and spintronics labs. lab, which actually we held together with the Russian Quantum Center. So those two, they study quantum phenomena. And then we got very new lab, material computer design lab, which basically focused on a computer design of new materials. So right now we have more than 150 employees. 70% of those researchers, they're young officially, so they're up to 35 years old. And the main purpose of our activity is basically to create a world-class national scientific center in the field of graphene and other two-dimensional materials. So we also do education activities. So from 2019 and right now, I mean, and until this period, we launched national, or I'd say Russian-speaking master program, Advanced 2D Materials. From fall 2021, we actually launching international master program, Advanced 2D Materials. And then very soon, we're also launching bachelor programs on photonics and 2D materials. So right now we have like officially it's 10 students per course, but we are going to gradually increase the number. So if you are interested in studying and doing research with us, please visit our website. I will give you contacts later in the end of my presentation. So of course, the center is equipped with a very nice laboratory equipment, and we are perfectly equipped with a very modern research facilities. But our main treasure, of course, not an equipment, it's our scientists, especially our young scientists, our postdocs, our assistant professors, staff. So at least I think like 30% of our young researchers, they got experience to work all around the world. So here you can see a part, or at least some of our young scientists, which will be happy to become your supervisors. So please, again, visit our website, and if you are interested, join our educational programs. So we do research in different areas. It's photonics, integrated nanophotonics, different type of metamaterials studying. We are very much interested in sensor technology, biosensing, nanolaser, single photon sources, photodetectors, and many, many others. So of course, we are also quite efficient in publishing our results. So here I just took some of our recently published papers, I mean, together with the Nature family journals. So these ones, these 10 papers, they were published, I think, within the last year. And here, contacts. So this beautiful building, it's called Fistech Cifra. That's a very new one. So the first floor is actually occupied by our center. So please use these contacts to contact me directly if you would like to know more about our activities. Here also you can find our website information and also my email. So one more time, welcome to the school, and thank you for your attention.
Mm-hmm. Okay.
Yep, Valentin, many thanks. Just one more second. We're turning on the...
Yeah, great.
Yeah, hello, dear colleagues. My name is Daria, and I'm a school secretary, and I will talk in brief about the organizational side of the school. Here is the final program. You can also check the schedule in the app or on our website. Link and QR codes are attached to the slide. To see all the broadcasts, you can log in by the web version. Link is on the slide and also was sent to you in the informational letters and in the app. If you have scientific questions to the lecturer during the lecture, you need to open the schedule menu on the right, find the lecture you have a question about, and tap on questions. You can also ask questions via the Discuss button in the app by opening the schedule and choosing the lecture that you're interested in. After the school program also includes 2 practical classes by Professor Alexey Nikitin and Professor Pablo Alonso Gonzalez. We will publish the Zoom link in the class description, so just before the start, check the schedule and also turn on the pushes from the app to find out all the news and changes in our program. After the school closing ceremony, we will open the final test exam that will be available for completion to 11:59 p.m. Sunday, Moscow time, GMT +3. The questions will be based on the topics of the lectures. If you miss something, then at the end of each day, we will post recordings of lectures and presentation materials. However, not all lectures will be recorded depending on the permission from the lecturers. 2 poster sessions will be held on Monday and Friday in a format of pitches presentation with 5 minutes for the performance and 1 minute for questions and answer session. We invite all of you to join the poster sessions and ask your questions to your colleagues through the app or the web version. On Friday, we will have the closing ceremony with the Best Poster Award and METANANO Summer School 2022 announcement. We will be very glad to see you. Do not miss this event. Join our Telegram chat, and if you have any questions, do not hesitate to ask school secretaries Anastasia and Daria. Thanks again for joining us and have a productive week.
So, dear colleagues, now we will have a short break around, I'll say, 15 minutes before the next lecture, which will be given by the Sir Konstantin Novoselov from University of Manchester from the UK. So you can make a coffee and prepare to the lecture of the Nobel laureate Konstantin Novoselov. So maybe if you have a question, we could discuss something. Gosha, could you check, please? Do we have a question from our application, please?
Yeah, sure. One moment. Opening ceremony is not clickable. Okay. Not yet. We don't have any questions yet.
Not yet. Okay. If you will have a question, so we can answer this question in 5 minutes before the lecture by Konstantin Novoselov. Okay, dear colleagues, let's have a break. Please make a coffee, and so we will start in 10 minutes.
And make a proper one, since the lecture is going to be interesting. Morning, dear colleagues. We're just waiting a few more minutes to start. And just quick reminder that my name is George, and I'm going to be chairing this session. Please use Event-Rocks app for any questions for lecturers, maybe the Slalom School, or not Slalom, but METANANO School. And just a quick announcement that the lecture by Professor Sir Konstantin Novoselov will be split in two parts. So first part will be approximately 35 to 40 minutes, and a few minutes for questions and 5 minutes for break. And then the other part will be given. So pay attention to that. So before starting, I mean, we still have like 1 minute left. I will be sharp in time. So exactly at 11 a.m. we'll start. 11 a.m. Moscow time. So I see Professor Sir Konstantin Novoselov in the room, so this is great. You can start sharing your screen, and before that, I will just announce your talk. Yeah. So yeah, great. Yeah, the presentation is perfectly visible. So guys, colleagues, it's my ultimate pleasure to introduce the first lecturer of today and the first lecturer of the school, Sir Professor Konstantin Novoselov. And just a quick bio, just because maybe a lot of you already know. I mean, I'm mostly sure that all of you know who. I mean, we were grown on his papers and his research. So, but basically, this is what we should do as being a chair of this session. So, Konstantin Novoselov graduated from the Moscow Institute of Physics and Technology, which are our co-hosts of the school. And thanks to Valentin Volkov for helping us arranging this school. So, Professor Novoselov completed his PhD studies at the University of Nijmegen in the Netherlands, under supervision of also Sir and Professor André Game, before moving to University of Manchester in 2001. What's interesting that Professor Novoselov published more than 270 papers in leading scientific journals, including, of course, Science, Nature, Phys Ref Letters, and so on. And fascinating fact that 2004 science paper is listed among top 100 most cited papers ever in any field of science. Well, this is very incredible. I mean, this is what we're all young researcher students are aiming for. And in 2010, which all of us know, that André Game and Konstantin Novoselov were awarded with the Nobel Prize for groundbreaking experiments regarding the two-dimensional material graphene. And today, graphene has a lot of applications, including medicine, electronics, energy sensing, aviation, even tennis, and like just a watch. So, and also very, very, I would say, not interesting, but inspiring that in 2011, Queen Elizabeth II knighted both Professor Konstantin Novoselov and André Game with titles of Sir. So with all that concluding, let me give a floor to Sir Professor Konstantin Novoselov for his lecture entitled Science and Applications of Graphene and Other 2D Materials. Konstantin, please.
Okay. Good afternoon, and thank you so much for the introduction. It's Kostya, actually, and it's a great pleasure to be here, and really great pleasure to see old friends with whom got a bit lost connections over the last year. And for today's topic, so since the school is on the optical properties, I'll try to focus on optics of 2D materials, but I will just go quickly through a general introduction. Nevertheless, if you don't mind, guys, I will switch off my video. I'm calling from a funny place, so it's the internet connection might not be stable, so just in case. If you really need to see my name, just shout. No, so just to see my face, just shout. I will switch it back. So of course we have to start from graphene, and we all know what is what is this material about. Just two-dimensional hexagonal arrangement of carbon atoms. Despite being a very, very simple material, it is also it has a number of very unique superlatives, like being the strongest, the most conductive, thermally conductive, impermeable, flexible, stretchable, and so on. And because of those properties, it has a chance, or it actually does already go into many different applications, as George already mentioned. And as usual, that's something which really gives me an enormous pleasure, that despite being very special, it actually follows the footsteps of many other materials before it. So most of the advanced materials, they really follow exactly to the to applications. So you start with something relatively low tech, and you go like composite materials and sport goods, because you can pay premium there. And we also at the University of Manchester, we worked together with McLaren and Richard Miller to create this world's lightest, unfortunately also world's most expensive watch. So it's 1 million Swiss for 32 grams. 32 grams of time. And if you haven't got 1 million Swiss, you can spend £250,000 pounds on this car, and that's already where the things start to be interesting, because originally we thought that, so it's a small manufacturer which produces road legal cars, the fastest road legal cars, small producer nearby Liverpool. And originally we just thought that, okay, we try to gain a few kilograms of weight. In fact, they use those composites for the sake of speeding of the time of the production, because of the thermal conductivity of graphene. Those composites settle much faster. And then if we're talking about the automotive industry, pretty much every single Ford car these days got graphene under the bonnet. And again, the applications are a bit unusual. It is used for noise cancelling properties. Again, from the hindsight, you would probably say that introducing a lot of 2D materials, a lot of interfaces, you would scatter phonons quite readily. But so it really required some tests from Ford to develop this material. And then we go, and if you don't want to noise cancellation, you actually want to create noise. So there is a wonderful company in a startup in Canada who produce graphene phones, and they use graphene to create membranes. So membranes of the headphones of the speaker needs to be flexible and stiff at the same stiff and light at the same time. And that's of course all graphene, and again a bit of an unusual applications. And then going more towards electronics, thermal management. So you really haven't got any rival to graphene with the thermal conductivity of above 1000 watt meter Kelvin. You really have to use this material, especially as the production these days is ramping up. But then it goes into a deeper and deeper tech. And if we're talking about optics, so there are several companies who actually produce photodetectors based on graphene and quantum dots, and it's a commercial product these days. So basically what you do, you put graphene with quantum dots on top of them, and as quantum dots hole pairs are created, and then if holes are donated to graphene electrons, which sit on the quantum dot, act as a floating gate, and then you basically measure the changes in the resistance of the of graphene, and because you can integrate across any appreciable time, you can control it by ligands on quantums, for example. You can bring the sensitivity very, very high, and you can also control the operational wavelengths to pretty much anything, because you can change those quantum dots. So it's quite a promising technology for autonomous vehicles and some other applications. And probably what is the most interesting and exciting these days is the use of graphene and actually other 2D crystals as well in silicon photonics, because of course these days silicon photonics being used quite broadly for telecommunication. You are trying to move as much of the signal processing from the optical side, from the electronic side to the optical side. Unfortunately, existing ways how to control the properties of silicon photonics are quite slow. What you can do, you can deposit graphene or other 2D materials actually on top of your waveguide. It just goes conformally, and then you can modulate of the light which is passing through, simply by due to Pauli blocking. So if you don't dope graphene, it absorbs light. If you dope graphene, so it doesn't absorb light. And here because graphene absorbs only a small fraction, and it only acts on the evanescent wave on the surface of the waveguide, but because you can put quite a long strip of graphene here, it is still enough. You can achieve quite an appreciable depth of modulation. Or, which is actually probably more popular these days, is the phase modulator. So where you modulate the phase of light, just shift the resonance peak a little bit due to the changes of N and K, and then you can modulate light this way. And currently this activity is being developed by several companies. So before we go, and similar ideas have been utilized to produce tunable terahertz lasers, so you can put graphene on top of again basically the same waveguide, and then change through gating, change the N and K of graphene, but now in terahertz, and then you can controllably switch on and off certain resonances. So before we go to to other 2D materials, I just want to say that that's the beauty of graphene, that you can get tunable adsorption as well as tunable emissivity, because it's fairly easy to dope graphene in terahertz, but probably even in the optical range as well. So, and as I said, tunable adsorption, so it's easy to understand how do you tune adsorption through the Pauli blocking, but it also of course means that you got tunable emissivity as well. And that fact is actually being utilized quite readily as well, because what you can do, if you can tune the emissivity, you can tune the apparent temperature basically of your device. So and it's quite a simple technology, so it's pretty much ready to go into application. So what you do, you take your graphene, and so it has to be several layers of graphene, and then you can place it on any substrate which is porous and can hold ionic liquids. And then if you apply voltage, you can drive bias voltage, you can drive those ions to graphene, and then you can dope it, and through doping you change the absorption, but you also change the emissivity. And for example, if you try to measure temperature now, the real temperature of course doesn't change, but the apparent temperature, what your material emits, changes quite a bit. So you can see that you can change from say 50 Celsius to about 40 Celsius. So the difference of 10 degrees, and it's like I'm not sure how it is in Moscow these days. Let's say in Singapore, you have to measure your temperatures with those infrared detectors every time you go to pretty much any shop. So, but you can actually, with this thing, you can cheat the system, because you can lower your temperature by a few degrees really easily. And then it's actually very easy to go into application, because you don't need high quality CVD graphene. For example, here you can simply use reduced graphene oxide, and you can change your apparent temperature by 10, 20 degrees. And can actually move it from infrared and terahertz. You can move it into visible. You have to dope quite a bit here. Lithium is the best dopant. So and by doping with lithium, you have to protect your system from oxidation. But if you do that, you can actually change even the apparent color, not only apparent temperature as well. So just to finish this part, I want to say that these days, of course, there are many different ways how to produce graphene. Not only the Scotch tape exfoliation, which is still being used quite a bit by a number of groups in the world, but you can actually, depending on the quality and the price you want to get, you can use the liquid phase exfoliation, the CVD, the chemical vapor deposition, and some epitaxial methods as well. So to move to the next step, we just notice that of course you can get graphene if you exfoliate your lead pencil, the graphite which is in your lead pencil, and it's quite reasonable to ask a question: what happens if you exfoliate other colored pencils as well? Well, apparently you can get many other two-dimensional crystals beyond graphene, and these days we enjoy working maybe with a good few dozens of those crystals. Each of them is very interesting to study in the two-dimensional form. Actually, there are materials which do not have a three-dimensional counterpart as well. So there were a couple of papers recently published on the CVD growth of two-dimensional crystals, which are not available, or at least were not available in the three-dimensional form. But it's still interesting to study even those which are coming from quality, because physics in two dimensions is usually very different than physics in three dimensions. Sometimes it's simply the basic properties, like you get, for example, direct semiconductor, direct band gap semiconductor, if you go to monolayer of molybdenum, the sulfide rather than useful hybridization between the bands in few layers, already starting with 2 layers, and or many of those materials are not centrosymmetric, so you get piezoelectricity, you can magnetic properties change, and so on. So it's quite an exciting story to investigate the properties of all of those dimensional crystals. But at the same time, what has been realized, and the important step which was made was the fact that you can try to assemble those 2-dimensional crystals back into a 3-dimensional stack, the so-called van der Waals heterostructures. So you basically have your 2-dimensional crystals on a substrate, you can pick them up, and because they usually stick quite well through the van der Waals interaction, you can pick them up sequentially one by one, and you can create artificial materials, artificial 3D stacks, which otherwise are not available in nature. And it's extremely popular technology these days. So many devices have been produced this way. Many, I would say these days, pretty much every single device is using some kind of the van der Waals heterostructuring. So probably the most typical is the tunneling transistors, the solar cells, photodetectors, LEDs. So we're going to talk a little bit more about those. I just wanted to say, to finish on the technology side, I wanted to say that the quality of those heterostructures can be extremely high. So here is an example of a heterostructure which is based on boron nitride as a substrate, and then 2 layers of graphene, then 2 layers of boron nitride, again 2 layers of graphene, more 2 layers of boron nitride, and then again graphene again. And then if you look at and I just want to say that it's not so this to impress people. It's actually the real tunneling heterostructures to study tunneling through the mid-gap states in bilayer, in the gap of bilayer. And here, if you look at the especially in the image, you probably won't be able to say where your boron nitride, bulk boron nitride stops, and where your graphene starts. Of course, not any heterostructure can be created this way. So stacking relies on van der Waals interaction between those two-dimensional crystals, and it is better that this interaction is quite strong, because if it is, and it's not only just the stability, mechanical stability, it's actually is the quality of the interface which is under question, because usually when you create those heterostructures, you want it or not, typically those materials get covered with water or organic molecules very, very regularly. So when you put 2 layers together, typically there will be impurity in between. The question is which interaction wins, because if it is the interaction between the 2 crystals wins, then all these foreign molecules would be driven away, because the 2 crystals would like to stay as close to each other, pushing all the foreign materials away. And typically, if you see those white pockets, so those are droplets of foreign materials like organic contaminants. If you see them forming, it basically means that the interface will be very clean, because all this organics is driven away and is collected in a few pockets around your heterostructures. It does happen that it might happen that it's not the case. For example, mica graphene on mica, they don't interact strong enough, because mica crystals are strongly charged, and they attract a lot of water, a lot of organics, and you can see that those pockets are not being formed, unfortunately, and it just tells you that the interface might not be good enough for you for heterostructure engineering. Okay, so now if we go back to those heterostructures, let me maybe, as a sort of introduction into the heterostructures, let me just tell you a little bit, let me review some very basic ideas about some the properties of some very basic heterostructures. And it's probably easier to start with the tunneling heterostructures. The most popular combination is graphene and boron nitride, because graphene is the zero overlap semi-metal. Boron nitride is a wide band gap semiconductor, or 6 electron volt band gap. So if you put 2 layers of graphene and then separate them by a layer of boron nitride, you should get some tunneling resistance. But of course, you only have 1 layer of atoms. Would it be appreciable? Well, apparently, even a monolayer of boron nitride, because of its very large band gap, produces quite a substantial tunneling resistance. It's about a kilo per square micron. So it's quite a sizable resistance. But then you can put, say, 2 layers of boron nitride. You can put 3 or 4. So you can actually control the tunneling resistance quite readily, simply selecting how many layers of boron nitride do you want to put there. And then, of course, the tunneling current is simply proportional to the density of state. So the band gap varies not very significantly in such heterostructures. So if you apply some bias, you get enough electrons on your Fermi level, so the current would increase. And because we're dealing with graphene, so the increase is quite peculiar, because the density of state, of course, changes, but the function on the bias voltage is quite particular of the contribution from the quantum capacitance, again because of the small density of state. Now, the trick is that you can actually, if the current is proportional to the density of state, you can simply gate your graphene. And if you gate your graphene, you shift, even at 0 bias, if you gate your graphene, you shift the Fermi level to higher energy, where the density of state is not 0. So if you're tunneling, if your graphene, if the 2 graphene electrodes are at the Dirac point, the density of state is 0 at the at the Fermi level, so that there shouldn't be any current. If you dope graphene, you drive the Fermi level to high energy. The density of state is finite, so you get finite current, and basically what you get is a tunneling transistor, because you can control tunneling current with external gate. And so this unlike many other transistors, unfortunately the current here, the control of the current, is dominated by the changes in the density of state, simply because boron nitride is such a wide gap semiconductor. Even if you change your Fermi energy by, say, 200, 300 MeVs, well, really 200 MeVs, it doesn't change much in the exponent of the tunneling current, but the density of state changes quite a lot. And still, it's such, even with boron nitride, such devices operate better than other quantum capacitance devices, the tunneling transistors. So the traditional competitors are based on 3-5 heterostructures, but they're only operational at very low temperatures, and the on-off ratio is quite small. In boron nitride, the on-off ratio is 50, even at room temperature. But you see, and the beauty, of course, that there are many two-dimensional crystals which you can use either as electrode or as a barrier. Well, for electrodes, the graphene is probably the best because of the small density of state. So you can change the work function in quite a large range. But for the tunneling barrier, in principle, any material would do here, right? Because all you need it to be thin, tunneling thin, and there shouldn't be as little number of defects as possible. And just for the sake of a joke, so some time ago we created transistors made from vermiculites. Vermiculites is basically clay, and the reason why we used vermiculites is because you basically can get this material anywhere. It's something which goes into your cat litter boxes filler. So you basically go to the nearest convenience shop, buy this cat litter boxes filler, and then you can make a transistor out of your cat litter box filler. So it's just the only trick that you use it before it goes into your cat rather than after. And then if you it does work as a tunneling field effect transistor. Unfortunately, it goes well, the on-off ratio is quite small, but it has some unusual properties like piezoelectricity, because those vermiculites, when you make them few layers, they actually switch, and it's either ion driven or it's the structural change, or but basically just shows you that you can make those heterostructures from many different materials, including from those which you got at home already, or even your cat got at home already. So now to finish on the transistor story. So the on-off ratio of 50 is still unpractical. Of course, you need something more interesting to go into applications, and for that, all you basically need is to make sure that your band gap in your tunneling barrier is comparable with the changes in the Fermi level. So the typical changes in the Fermi level, as I said, is 100 MeV. So you need your band gap to be in about 1 electron volt, maybe 2 electron volt, not 6, like in the case of boron nitride. And for that, you basically, and then your tunneling current will be dominated by the exponent, and will be quite sensitive to the gate. And for that sake, you can be using various transition metal diethylcagenides like MOS2, for example, and so the band gap is of the order of 2 eV when it goes into a monolayer. You probably would use few layers, 2-3 layers, so it's about 1.6, 1.5 EV. And then if you make such a device, you actually notice that indeed you get a huge on-off ratio above million. So it is already practical for applications if you dare to create such devices. So now we just go into the right. Just thinking time wise. Okay, let's cover one more topic here. You can ask yourself a question. So what happens if you eliminate such a tunneling transistor? Well, of course, you can create electron hole pairs in your insulator. For boron nitride, you would need to shine really deep UV, but you still can. The problem is this structure is very symmetric, of course, and then even if you create electron hole pair, it will simply recombine back, and you won't see any photocount. So to solve this problem of the large band gap and the symmetry, what you can do, you can apply gate voltage, for example, here. Then you create built-in electric field. So now, if your light comes and you excite electron hole pair, what happens? It just goes. So this built-in electric field separates electron and hole to opposite electrodes. So you should get some photocurrent. And as already mentioned, if you want to make it practical for some infrared or visible light applications, you would better use other 2D crystals like molybdenum disulfide, tungsten disulfide. So there are many of them, and especially as those crystals, they're quite their work function is such that the Dirac point sits exactly in the band gap. Well, in reality, those crystals are slightly doped, so your Dirac points get shifted. But in the undoped case, the Dirac point sits exactly in the middle of the gap. It is quite practical, so you can actually use them for photodetector applications if you want. The devices are extremely simple, so you just have 2 layers of graphene separated by a layer of semiconductor. So that's how it looks like. And then, so here, for example, what we did, we just shine light and scan light across the device like this. And then, if you look at the electric response at the photocurrent, all photocurrent is only generated when in the areas when you shine at the areas where the bottom graphene, the top graphene, and the semiconductor, they all overlap, and then you can apply gate voltage, positive or negative, and the sign of the photocurrent does change because you simply introduce different introduce different built-in electric, so your electrons and holes would be separated into different contacts depending on the direction of this this built-in electric field. So the quantum efficiency of those devices is not very high, and there are many reasons for that. For example, you need fairly thin semiconductor, because if it is too thick, you simply cannot apply large enough gate to create built-in electric field. So only the surface layer would work and because you need to create fairly strong electric field to separate the charge carriers. But in principle, and the problem is that in thin semiconductors, the absorption is limited. So what you can do, you can, for example, play some plasmonic tricks and put plasmonic nanostructures on top, and then you can increase the absorption quite readily. So yeah, without those nanostructures, the response is quite small, but it just increases orders of magnitude if you put plasmonic nanostructures on this device. So I think let's make a 5-minute break here. If you've got, guys, any questions, please shout at will, or otherwise we just continue in 5 minutes.
Oh, thank you very much, Professor Novoselov. So, guys, I encourage you to ask questions in the chat. So, by the way, there are not yet any questions, but I have a few short questions, if I can ask.
Right.
Yeah, sure. So the first one is concerning the van der Waals heterostructures. I just wonder, since they are attached one to each other due to van der Waals like forces, it doesn't matter which type of lattice periods there are in those monolayers. So they're okay to have some differences in the periods.
Well, it's that's not entirely true. So the van der Waals forces is still the it's still the dipole-dipole interaction, and it's related to the polarizability of your atomic orbitals, and it does depend on the relative orientation of the atoms. And maybe the best, I mean, okay, I will talk a little bit about the twisted heterostructures later, but even if you measure, say, resistance, so just two examples. If you measure resistance between two layers of graphene which you stack on top of each other, and depending on the angle, the resistance changes really by a couple of orders of magnitude easily, because it's not easy to determine what is the resistance of such a structure. I mean, the vertical resistance, if you measure from one layer to another layer, from top layer to the bottom layer, even if you don't have any boron nitride in between them, the resistance varies from tens of ohms, maybe hundreds of ohms per square micron to kiloohms. So it's it does matter the orientation. Another famous example is the superlubricity, because the friction can be a signature of the van der Waals interaction as well, and if you are close to some commensurate structures, the friction will be very high. But then if you rotate it to some non-commensurate angles, you get basically zero frequency. So zero friction. So the orientation is very important, and later on I will talk a little bit about the twist control heterostructures. But I'm sure that other people will be talking much more about this. So it's not the main topic of this talk.
Okay, yeah, thank you very much. So there is one question in the chat. So sorry if I'm reading the name incorrectly. So Mas Ahmed Kirishi is asking, is it possible to also increase the photoresponsivity in a waveguides integrated by 2D materials devices by making the vertical heterostructures of 3-4 multiple flakes on the same material, such as MOS2 on top one of another?
Right. Okay. Again, that's I'll have one slide about this later, but the basic answer is yes. So the the problem with the I'm not sure which waveguides do you mean. So silicon waveguides, the responsivity is quite low simply because you've got only the tails of the electric field at the surface. You need certain distance for the light to travel, to overlap with the material, but few microns is enough. So I think the typical modulators with MOS2 is only few microns long, and it's enough to get very high interaction. Same for the emission. So you can actually produce heterostructures and emit light, and you can couple it to the waveguide. It's a little bit of a question which exciton you would be emitting light. Is it exciton or a trion? Because the polarization might change in different materials, and some polarizations are better coupled to the waveguide than the others. But again, you can play with it.
Yeah, okay, thanks a lot. And final question from this part, Idris Abu Hasba is asking, what is the effect of graphene coatings on the nonlinear optical properties of metallic structure?
Okay, that's I'm not even sure how to answer first. Typically the nonlinear graphene properties, optical properties, are used for in cerebral adsorbers and in second harmonic generation. What about coating? I should admit I don't really know. That's probably beyond me. Sorry.
So yeah, sorry, thank you very much. So I suggest we'll continue in 5 minutes. So it's 11:46 Moscow time. So let's get back at 11:51. So short break. Yeah, thank you very much.
Short break. Okay, I think we can probably continue. Right? Can you hear me?
Yeah, perfectly fine. Yeah, just a quick announcement. I'll try gently to notify you 5 minutes prior to the end of the session, just to conclude the talk. Yeah, very sorry and thank you.
Okay. So we've got another 40 minutes, right?
Yes, approximately 40 minutes. Yes, please.
Okay. So now what happens? So we know that such heterostructures can absorb light, and if you apply some bias, you can separate electron hole pairs. Now, a good question would be, what happens? Can you actually so can you inject electron hole pairs into such a heterostructure and generate light? In principle, yeah, so you can apply large enough bias and inject electron hole pairs, hoping that they will recombine and generate light. In practice, it's not actually that easy, because what happens when you inject those electrons and holes, they simply don't have enough dwell time in your semiconductor to form an exciton and then recombine. They usually just go into the contact and disappear. So instead, what you have to do, you have to add some tunneling barriers to increase the dwell time of your electron hole pairs. So then when you inject them, they spend a lot of time inside of the semiconductor, and then they can emit light upon recombination. So here is an example of one of our maybe largest heterostructures. So it has a number of those semiconducting layers. So it's the graphene here plays only secondary role. It's just transparent conductive coating. You inject electron hole pair into those semiconducting layers, and then they recombine, producing light. The more it's typically better to put several semiconducting layers, because those which are not catched in one, they go into the next one. So your overall quantum efficiency increases here, and it's actually quite a promising technique, as I said, because you can, for example, again combine such heterostructures with silicon photonics, because one of the major problems for silicon photonics is the absence of the light sources operating in this in the telecom range, which you can easily combine with silicon photonics. You have to either do chip bonding, or you have to put a fiber on your silicon chip. Here we have only a few layers of 2D material, in particular molybdenum ditelleride, which emits exactly in the telecom wave range, and you can conformally put it on top of your waveguide. And as I said, you can in principle control the polarization of the emitted light, so you can couple it reasonably well with your waveguide and emit directly into the waveguide. So these days the selection of the 2D crystals is quite large, so they already cover quite a range of the wavelengths. Molybdenum ditelleride on the low energy range, telecom range, so tungsten sulfide on the in the visible But in principle, if you want anything in between, you can have devices with tunable emission, and there are several tricks how you can tune emission of your semiconductors. So I would just show you a few of such tricks which people are playing now. So one thing is actually to grow other 2D crystals on demand, and of course the number of the crystals which you can grow is limited, but the beauty is that you can actually mix and match those materials by growing alloys, and in alloys the emission wavelength changes, and well, it's not just a simple linear dependence of the band gap on the alloy composition, but you can still get some idea how it works. And these days we work on to produce several types of machines to grow different 2D alloys exactly for this kind of application. Now another way how to tune emission is through indirect excitons. So imagine we have, say, a layer of two-dimensional crystal, say tungsten selenide, and we create our usual light-emitting diode out of it. So if you apply voltage, you do get emission from the tungsten selenide. Now let's put another material on top of tungsten selenide, say molybdenum sulfide, and then immediately instead of the emission from molybdenum sulfide, which is somewhere at 1.79, 1.8 electron volt, you start to see very strong peak at 1.2 electron volt, but much lower energy. And what happens here, you inject holes into tungsten selenide, you inject electron into molybdenum sulfide, and then these electrons and holes, they actually form an indirect exciton, and it is indirect in that sense. It is indirect in space, so the electron and holes, they live in different layers, but they also indirect in the K space, because the lattice constant of molybdenum sulfide and tungsten selenide are slightly different. And then because such an exciton would have a dipole moment, you can control the emission wavelengths by applying voltage. So, and you can control it in quite an appreciable range. So 100 MeV is definitely possible. So you get controllable emission, and it's actually very interesting to show how sensitive is this device to the structure. So here is a different representation of this structure. So tungsten selenide. Here we have the sulfide separated by boron nitride from graphene electrodes. But now let's imagine slightly that we use exactly the same heterostructure, but now we put a monolayer of boron nitride between tungsten selenide and sulfide. Everything else is exactly the same. I only add one layer of which is 1 atom thick in between molybdenum sulfide and tungsten selenide. Immediately, apparently, the situation changes entirely. So at this bias, we previously could see quite some large emission at 1.2 electron volt. We don't see this emission at all, and then only applying larger bias, we start to see emission from tungsten diselenide and MOS2. No indirect exciton can be seen here because tunneling and coupling through the boron nitride layer is quite small. But what is impressive is that we actually have this emission at 1.7 and 1.9 electron volt with the bias only 1.4 volt. So we apply less energy than we get. So the emission is at much higher energy, and you see those peaks become quite strong even at minus 1.6 volt. Again, the emission is 1.7 and 1.9. So what happens is that you have the Auger excitation of those electron hole pairs, and then you get the up converted electroluminescence. So maybe a few words about a very popular direction of research, that all those two-dimensional crystals, so they of course they're good emitters, but in principle you can actually create defects in such materials, and then those defects will be acting as single photon emitters, quantum dots, the colored centers. Typically, the most promising materials, or most popular material, is tungsten diselenide. We're still not entirely sure how those quantum dots are formed, whether it is atomic or it is strained. But at least you can now create those quantum dots on demand simply by so one trick is simply to push with an IFM tip and create defect, either strain or atomic defect, or you can put your material on top of pillars, and then once you create control with those emitters, you can put them back into your light emitting diode structure, and you can actually produce light emitting diodes which emit single photons on demand simply by applying bias voltage. So, and that's again, it's quite promising for quantum telecommunication, quantum dots, especially those which can be emission from which can be controlled. Is always required for quantum telecommunication. Maybe while we are on this topic of the quantum dots, let me just tell you one story. I quite like it because it really combines the planar heterostructures with the vertical heterostructure. So some time ago we worked with Professor Shin in South Korea to create planar heterostructures, planar quantum dots, graphene quantum dots in boron nitride. So what you do, you create tiny platinum islands on the surface of silicon oxide, and then you transfer hexagonal boron nitride on top of those. And then if you run a chemical reaction which is catalytically activated, you can convert boron nitride into graphene, but only in the presence of platinum, so only on top of those platinum islands. So basically what you will get at the end is a nice graphene quantum dot embedded into boron nitride matrix. And the beauty of that is that you can control the size, but also all the bonds are saturated, so you don't have any dangling bonds for your graphene quantum dots. You can control the position and the periodicity of such arrays, and then you can plug it in simply push this material inside of your heterostructure. So the idea is exactly the same as in the case of light emitting diode. So you have material with a band gap, in this case quantum dots of graphene in the boron nitride matrix, and then you just plug it into your between the two tunneling barriers with two layers of graphene as electrodes, and then you can apply bias and apply gate voltage, and is the tunneling transistor through the states in those quantum dots. And what you get is a typical stability diagram, Coulomb diamonds of electrons tunneling through those quantum dots. So let me now spend a few minutes on the twist control heterostructures, because they're also important for the optical applications as well. So the beauty of the are such that you can control, of course, the sequence of your layers, the number of layers which you put, but also the orientation, the relative orientation between the layers. And this orientation is extremely important. For example, if we're talking about those tunneling devices, if you rotate the two layers of the two graphene electrodes with respect to each other, you rotate them in the real space, but of course they are rotated in the reciprocal space as well. And then rotation in the reciprocal space means that those Dirac cones, they either overlap or they're not overlap. In practice, the devices look very simple, just two layers of graphene aligned under certain angle, separated by, say, boron nitride. But if you align them, the IV characteristics looks very, very unusual. So here we have those peaks in the current. So it means that you apply voltage and you increase voltage, and according to the Ohm's law, current should increase as well. Instead, you increase voltage and the current suddenly starts to go down, and this effect is called the negative differential resistance, and it's usually very thought after for various high frequency electronics applications, because you can generate high frequency with such devices. And it's so here the beauty of this is that it doesn't rely much on the band structure, it relies on the geometrical overlapping of the bands because of the misorientation of the finite twist angle. So generally the the orientation between individual layers is extremely important. Probably the most striking example is the graphite as well itself. So we all know that the most widely spread stacking for graphite is the so-called Bernal stacking, or the ABA stacking. So with the unit cell consisting of two atoms, but in principle you can get also the so-called rhombohedral stacking or the ABC stacking. And in the natural graphite, about say 10 to 20% is actually in the ABC stacking. And all you've done is you shifted this top layer by one unit cell. That's it. But the electronic properties are completely different. So the resistance, there's a band gap in the rhombohedral stacked trilayer, and the Bernal stacked graphene is a semi-metal. So stacking is extremely important, and people realized that quite early on, and probably the most widely studied structure is graphene on boron nitride. The beauty of the situation is that boron nitride is the same graphene, just with carbon atoms being replaced by boron and nitrogen, and the lattice constant of graphene is practically the same as that of boron nitride, just 1.8% difference. If I plot them on such a scale, you won't even notice the difference, even though I included this 1.8% difference in this picture. In fact, I need to exaggerate by 11% for you to see the effect of this lattice mismatch, and the lattice mismatch results in the formation of the Moira structure. The period of this Moira structure is given both by the difference in the lattice constant. If the lattice constant won't be there, the period would be infinite, because we would get perfect matching. But also it depends on the orientation angle. So if you rotate your crystal, even if the lattice constants are exactly the same, you would get certain period of the Moira structure. So for the case of graphene on top of boron nitride, the period of perfectly oriented graphene on boron nitride, because of the 1.8% lattice mismatch, is about 14 nanometers, and that has been observed by STM. Calculations would give you this Moira as well, or you can measure the density of state directly. Basically, what happens, your electrons, when they move in graphene, they now start to see this periodic modulation of the potential. They start to break scatter on this potential, and it results in opening of the energy gap, or it's actually it's a pseudo gap. You get Dirac cones at certain wavelengths, when the wavelengths of electrons match that of the Moira potential. So you get the formation of the so-called secondary Dirac points, and you get this deep in the density of state, which indeed has been measured by many techniques. So what you have is a dip in the density of state. So the density of state for graphene should be linear, should go just linearly up. Instead, you get a dip which corresponds to the small density of state around this secondary Dirac point. And on both sides of this dip, you have this increase those peaks. That's the one-half singularities from the flat bands around those secondary Dirac points. So I won't go much into the details of graphene. I just said that you can get the beautiful Hofstadter butterflies story and the Brown-Zach oscillations, which survive up to room temperature, or boiling, rather than liquid helium temperature. They survive up to liquid water temperature. And these days you can use different techniques how to create those twisted heterostructures. The traditional is of course pick and lift methods, or you can tear and drop method, so which allows you the control of the rotational angle with very high precision. But also in principle you can control this in situ, for example, with a tip of an IFM. So you can push with, so, okay, it's not, you can do it with the tip of a knife, and it's better if you put some soft material on your cantilever, and then you can push against the crystal, and when the contact is established, you can rotate, and you can rotate the two crystals with respect to each other, so the orange and the purple here, or you can actually move them in any direction. So it's actually, and again, it's towards the same question about the how orientation matters. So here it is very, very easy to rotate those crystals if they're not people visiting, the friction is very low. You rotate your cantilever, and the crystal rotates together with you, with the tip. Once you get into the commensurate state, the friction increases dramatically, and then it becomes much harder to rotate. Actually, these days it is possible also to grow such structures by CVD. What people do, they nucleate separately two crystals, one on top of each other. In principle, you can control the growth angle, although it's very difficult. Typically, people simply just grow large quantities of those heterostructures, and then select the angle of interest, and this angle will vary in very large range, and you can see all these Moira patterns in TM in such heterostructures. So of course the most exciting consequence of this is the formation of the flat bands in twisted graphene heterostructures, as has been demonstrated by the MIT group. For today, I'm sure that someone else is going to talk about the twistronics. So I think Paka is going to talk later about twistronics. I'm not going to touch this area today. I just want to say that twistronics works not only for graphene, it also works for other materials as well. And since we're talking about optics today, I thought that I will just show you one example of the twistronics for in case of the semiconductors. So again, it's the collaboration with Professor Shin from UNIST and with Sasha Tartakovsky in Sheffield. And here we studied the heterostructures, very simple, just two layers of molybdenum diselenide and tungsten disulfide, and it became possible because of the CVD growth by Professor Shin, because you basically grow large number of those heterostructures, also of those crystals under different angles, and then you transfer them one on top of each other, and you basically result in randomly oriented heterostructures. But you can always choose a particular angle, and you can notice here that separately molybdenum diselenide emits light, and tungsten disulfide also emits light. But wherever we form the heterostructure, wherever the two crystals overlap, we have the quenching of the luminescence. Again, this is because of the formation of the indirect excitons, which start to emit at different wavelengths. But most interesting here is to follow the behavior of this luminescence as a function of the angle, and you can notice that the position of this indirect exciton peak changes quite dramatically with the changes of the angle, which of course shouldn't be in the linear approximation. So the energy position of the energy minima shouldn't change. But what happens is that this indirect exciton start to hybridize with the exciton in molybdenum, with the direct exciton in the molybdenum diselenide, and this hybridization through the scattering on the Moore potential gives you these changes in the emission. So I think I will stop here just to allow some time for the questions, and thank you so much for your attention. Thank you.
Thank you very much, Professor Novoselov. Well, very exciting results, very exciting talk. So guys, please welcome to start. I'm welcoming you to start the discussion. So there are some questions in the chat right now, so I'll just read them. Tatiana Ivanova is asking, probably regarding the first part. She wonders, so she states that you are using boron nitride monolayer for a tunnel between two graphene layers. If that's correct, then could you please explain what do you do to get a boron nitride monolayer? Mechanical exfoliation on silicon oxide and slow peel off after baking. What sizes of heterostructures you get? Yeah, thank you.
Right. Yeah, that's correct. So that's we mostly use boron nitride, mechanically exfoliated boron nitride. In principle, I mean, it doesn't matter. So, but you really need, especially for the tunneling heterostructures, you need very high quality of boron nitride, especially if you go to a few layers of boron nitride, the tunneling current drops down, and any single impurity start to dominate the tunneling current. But usually you see it, and those tunneling through impurities is can be noticed, and it has quite a characteristic features there. So it is indeed a bit of a tricky to see monolayer boron nitride when you exfoliate it. 19 nanometer silicon oxide helps enormously, but it's still a little bit of a pain. So students usually don't like searching for monolayers. If they have a chance, they just go for bilayers, much easier to find. And then so if you find them, you just pick and lift, and typically you get I would say anything between 10 square microns and maybe 100 square microns tunneling devices. We practically don't work with monolayers, and it's a bit tricky to work with the monolayers tunneling heterostructures because the resistance of graphene is quite sizable, comparable with the resistance of the tunneling junction. So you need specific geometry, otherwise current in the electrodes start to influence the tunneling story. So we confirmed those results simply with tunneling from an IFM tip, flat IFM tip was the goal of the electrodes, and same was done in the group of Philip Kim in Colombia at that time, I think still. It's I mean, monolayers are a bit tricky though possible.
Okay, yeah, thank you very much for such thorough answer. So Muhammad Wahid Ramzan is asking, is it possible by using applied electric field to deform the structure to tune the nonlinear properties of these 2D materials?
Okay, it's some people ask this question experimentally for the non-freehanging, not freestanding. I haven't seen any convincing evidences that you can actually deform it. Of course, once you create those structures, and if you have the more pattern, you get certain corrugation. There have been reports, some indirect reports, that maybe some bending is possible, but I don't think those are convincing. So I would say at this moment of time, I would say the answer is probably not. So the van der Waals is quite strong, even though if you calculate the Coulomb energy is comparable with the gating from the gating is comparable with the van der Waals. So we had such estimations, and Coulomb is comparable with van der Waals. Whether corrugation happens, I don't know. I don't think so.
Yeah, okay, thank you very much. So short question from my side. So in the first part, in the final some slides, you've shown some photodetectors based on monolayers. So I just wonder, in terms of applications, industrial applications, is it kind of scalable to create some large area photodetectors, maybe solar cells and stuff, and how fragile are they? Yeah, thank you.
Right. So I think it is definitely scalable. The problem with those photodetectors is that they're not very high yield, high quantum yield. Actually, it's quite low quantum yield, and the reason is that if they're made from few layers of semiconductor, they only absorb so much fraction of light. So I think it's in the telecommunication, when you can send light not across but along this material, you can solve this problem quite easily, and that's why I think the combination with waveguides, with silicon photonics, is very promising, because you avoid this problem of low absorption. But in terms of scalability, yes, I'm sure it is very scalable, especially for the photodetectors, where you don't care much about direct or indirect band gap, right? So you just few layers would work even better. For the light emission, you need monolayer for the band for the direct band gap. Here you can put a few layers, and it will still work fine. And a few layers of those materials can be grown by anyone these days. So it's quite a simple technique.
Yeah, okay, thank you very much. So with that, I think I would like to thank once again Professor Novoselov. Thanks everybody for a fruitful discussion. And the next talk will be in 20 minutes by Professor Francisco Guinea on twisted layers, narrow bands, and new phases in two-dimensional materials. So with that, I would like to end the first session of the school and thank everyone. And while in such difficult circumstances, we still managed to arrange this to work. So thank you very much, and see you in 20 minutes.
Thank you so much. Thank you.
Thank you very much.
Professor, Professor Guinea, I'm chairman today, and I would like to ask you: do you want a break in your lecture?
Yeah, maybe it's helpful. You're right. Maybe
Okay.
5 minutes, like cost. Yeah.
Okay. Okay. So we're about to start. Dear colleagues, it's my great pleasure to introduce you the next speaker, Professor Francisco Guinea. Francisco Guinea obtained his bachelor degree in physics from the Konstantin University of Madrid and the PhD at the Autonomous University of Madrid. He has been visiting professor at several American universities and has stayed for shorter periods at a number of institutions worldwide. In 2005, he joined India Nanoscience in Madrid, Spain. His research interests include theoretical condensed matter with contribution of many areas, including statistical mechanics and material science. He has published over 400 scientific papers with an IH index of 96 and more than 19 papers with over 100 citations. Has received a number of awards, including the Guinea National Prize for Physics Spain and the gold medal of the Spanish Physical Society. So let me give the floor to Professor Francisco Guinea, giving a lecture on twisted layers, narrow bands, and new phases in two-dimensional materials.
Thank you. Can you hear me? Because I have. There is something weird here. I'm not sure I'm being able to share the screen. I don't know why. Can you hear me?
Yeah, perfect. We hear you well.
Well, let me see what's happening. Can you see my screen?
Yeah, we see, but it's not a full screen.
Yeah, that's what I would do. Sorry, that was the problem. Thanks a lot. Okay, so thanks a lot for the introduction. Let me start. Now you see the screen, I suppose.
Yeah, now it's perfect.
So sorry for the glitch. Let me say I'm very glad to participate in this very interesting meeting run by such a very productive and active institutions. And I will pick up a bit where Kostya left, because I will be speaking mostly about moire materials. And I'm a theorist, so I will put more emphasis on theoretical or basic aspects of what I'm going to talk about. And moreover, part of the topics I'm going to mention, especially twistronics and so on in the second half, they are not terribly developed. So for sure, they will have applications in optics, and they are opening up a lot of very interesting new problems in optics. But the situation is such that I have to start by describing the basic facts and probably leave optics for a future school. Okay, I'm not going to repeat very much stories about graphene, and you all know how versatile carbon is, how often one can find a honeycomb lattice in connection with graphene. Nowadays, the nanotubes are just graphene in a cylindrical shape, or the fullerenes. Same thing is graphene in a spherical shape, and everything started with the famous experiments by Novoselov and Andre Gam in Manchester in 2005. But what I would like as a theorist to say is that graphene is a very simple system, because carbon, to start with, is a very simple element. I mean, it's at the beginning of the periodic table, it had very few electrons. And because of that, the electronic structure of graphene is not complicated at all. Let me say that most of what I am going to tell is associated to one single orbital of carbon, which is this one purple orbital pointing out of the graphene plate, the PZ orbital. These are the graphene bands, and the Fermi energy is right where these two bands, the valence, the top valence and the bottom conduction band touch. This is the Dirac point, and then in addition you have bands at relatively deep low energies, like few EVs below the Fermi level. Those are the sigma bands. They're important indeed because they are responsible for the strength of the sigma bonds, which keep the lattice very, very rigid. But for the point of view of optics, except in the ultraviolet or in the visible, they are not that important. And most of the action for electronic transport and device fabrication and so on is related to the bands derived from the pset orbitals I mentioned to you before. If you look close to this crossing at where the chemical potential is, you see two cones which touch. That's forced by symmetry. This is one of the peculiarities of the band structure of graphene. And then because of that, the density of states vanishes at the Fermi energy, and graphene is neither a metal nor an insulator. It's a semi-metal with no gap, but vanishing density of states at the Fermi level. And then the atoms are, they form these very rigid sigma bands among themselves. So each atom is very rigidly attached to three nearest neighbors. And that takes care of three of the four orbitals in the top shell of the carbon atom, and it leaves a single orbital pointing out of the plane, which is the pset orbital, and this is where this band is placed. And because of that, you have, it's a triangle, the honeycomb lattice is a triangular lattice with two atoms per unit cell. And if you have only one orbital per node, your Hamiltonian is described by a simple 2 by 2 Hamiltonian. Moreover, the pset orbitals are sufficiently localized, so you have only to take into account the likelihood that an electron in one carbon atom hops to the next carbon atom and back. So you have a very simple model you start from, as simple as it can get, or most crystals I can speak of are way more complicated than graphene in this respect. And now you know that this is a symmetry condition, it is forced by symmetry. The dispersion is linear around these points where the bands touch. So you can expand the Hamiltonian in momentum space, and you get something which is linear in the deviation of the momentum from these two inequivalent points in the Planck zone. So you have the so-called Dirac equation, in which has a dispersion which is linear in momentum, unlike what happens in most bands in crystals, where the dispersion near band edges is quadratic. Here we have a linear dispersion, and that changes things in a significant way, as I will show later. And then you can replace, you have this Hamiltonian in momentum space. You can say, well, the wave function may be modulated at the scale of the atoms, but then if we are interested in superpositions of waves which do not differ in momenta very much from these intersections, we can write a wave function as a fluctuating part, fluctuating on the atomic scale, so fluctuating over a couple of angstroms or so, plus the superposition of the corrections due to the fact that we're not strictly at these points, and that will be that can be represented by a smooth function which varies slowly, and then one can replace or back to a description not in momentum space but in real space, and the only thing you have to do is to replace momentum by derivative. So then this is this Dirac equation in momentum space, a 2 by 2 matrix, and you have another 2 by 2 matrix which describes the envelope of the wave functions in real space. And it's a first order, it's made up of two first order differential equations, which are coupled. So in summary, one can describe graphene at three levels. one can look closely to all energies and all electrons using methods which take care of most orbitals, like density functional formalism. And then you have a nice description valid for a wide range of energies, but only for short distances, because you can only deal in such a way with a few atoms. You can go to this effective description in terms of only one orbital per carbon atom, this type binding description. And then you have a description which doesn't take into account the sigma band, so it's not so general. You cannot use this description to study phenomena which take place at 4 eVs, for instance. But still, it's very reasonable for a larger range of energies and distances. And you can simplify even further this tight binding equation and go to a kind of continuum, a KP description of graphene in terms of the Dirac cones, and then you have a differential equation, a very simplistic 2x2 matrix again. And depending on which scale you're interested in, both in energy and in size, you can pick up one description or the other. Now, the advantage of the Dirac equation, which is what I will mostly discuss, also I will mention other approximations as well, is that it's very convenient if you want to treat phenomena which take place at scales beyond 100 nanometers, or between 100 nanometers and 10 microns, for instance. For that, a tight binding description is not feasible, because then you're dealing with patches, with regions where you have maybe 10 or 100,000 atoms. And that means that if you want to study inhomogeneous systems, disordered graphene, so you can add perturbations to graphene, the best choice is to use the Dirac equation. Moreover, the types of perturbations you can include in a 2x2 matrix is kind of limited. You can put a perturbation in the diagonal elements of the matrix, and that is what is called a scalar perturbation. You can put a perturbation which changes sign in the two diagonal elements of the matrix, and that means that is a perturbation which differentiates the two sublattices of the honeycomb lattice, the blue and the red one, as shown here. And then you have perturbations which go into the off-diagonal elements of the matrix, and this is where, in addition of any impurity, any inhomogeneity, the Hamiltonian of the clean system is. And this is something which is just added to the momentum, because this is where the momentum is. So this is a gauge field. It's like a magnetic field, but strains induce perturbations of this type because they also touch or modify the hoppings between nearby atoms. So strains, it's a way of saying that strains produce effects similar to magnetic fields. I will not, it's a very interesting topic on its own, but I will not discuss it any further. So let's look at a simple example. Let's suppose we want to study graphene in a magnetic field. The magnetic field, what it does is to induce a real vector potential. So then one has, instead of the Dirac equation I showed to you before with only the derivative operators, one has this gauge field. It is a particular choice of gauge field which describes a continuum magnetic field in terms of the magnetic length associated to that field. You know, it's like 240 nanometers for 1 Tesla. But then you can notice that the two operators which enter in the off-diagonal are very special, because when you look at the commutator of them, they give you the unity. So they are equivalent to creation operators. In a way, this Hamiltonian is like the square root of the Hamiltonian for a harmonic oscillator in ordinary quantum mechanics. You square it and you get the harmonic oscillator which has term proportional to beta rapid. So then by squaring this Hamiltonian, you can get a very simple description of the energy levels, of the Landau levels of graphene. And this is by no means unimportant, because that was the origin, in a way, of the great interest that graphene arose at the very beginning. Because the confirmation that graphene was very well described by a Dirac equation attracted to graphene research a lot of people from many different communities. That was shown in these two papers, one from Manchester, the other from Columbia, and it was after the isolation of graphene and the characterization of single-layer graphene. This was the beginning of the boom in graphene research in the world. Okay, but that's not the entire story. I have been talking about the graphene monolayer, but then you can put stack layers after layers. That's the way you get graphite, for instance. Graphite just is a repetition of AB stacked by layer graphene. So you repeat this unit cell a number n of times and you get a piece of graphite. You can also put one stack of graphene directly on top of another, and you have what's called AA stack graphene. This is not energetically favorable. These are the two situations. And then you can go and use the Dirac equation you have for each layer, duplicate this equation and add some pieces describing how electrons can move from layer to layer. And the outcome, and then this number is not that small. I mean, it changes the bands, the low energy bands in a significant way, but still you're within the Dirac-like description of graphene. What is interesting is that what you get out of it is band structures which differ a lot from single-layer graphene. In this very simple case, the reality is a bit more complicated. But for the Bernal AB bilayer, the really good one, the stable one, the linear dispersion is changed into a parabolic dispersion. So in two dimensions, that implies that the density of states now is finite. So it's a very weird system because the chemical potential lies between two bands which touch. So it's gapless. But if you look at the density of states, you think you're dealing with an ordinary metal with a single continuous band, because the density of states doesn't change as you sweeping energies from the valence band to the conduction band. In the AA case, things are very simple because you just lift the even combination of the two cones in a single layer graphene is moved up and the odd combination is moved down, and that's what you see in this picture. But what I mean is that the stacking of layers, even in this very simple situation, which is graphene, can change very much at low energies than the electronic structure. And then you have other two-dimensional materials. As Kostya mentioned, you have HBM, which is basically like graphene, except that the atoms you put in the two sublattices of the honeycomb lattice are not equivalent. That is what one of that. So then you can describe hexagonal boron nitride like graphene with one of the perturbations I have already mentioned, this delta, this mass term, which opens a gap, and actually a very significant gap, like 4 or 5 EVs. But to a first approximation is not that different from graphene. If you think of it, boron is on one, if you look at boron and nitrogen in the periodic table, they are right on both sides of carbon. So that's probably why they form the same, boron and nitrogen form the same kind of lattice with similar properties with respect to stiffness and things like that. Also, because boron is different from nitrogen, you no longer have a semi-metal, you have an insulator. And then you have the dichalcogenides, which Kostya also mentioned, which are also semiconducting. Well, there are some dichalcogenides which are metallic and superconducting, but the most famous ones like molybdenum disulfide, they are semiconducting. And let me mention, as I'm a theorist, that two of the most famous theoretical models which were proposed in the last 20 years, let me put it that way, in condensed matter, were defined on the honeycomb lattice. One was the Haldane model, which was the first model with showed topologically protected edge modes without a magnetic field. And the second model is two copies of the Haldane model, basically, which showed that if you add a spin to the Haldane model, you had a more realistic situation, which you could find in real crystals, and which describes what nowadays is called or are called the topological insulators. Okay. As Kostya mentioned, and you can do a lot of things with two-dimensional materials. And the interesting thing is that to make metamaterials, to make other materials which do not exist in nature using the versatility of two-dimensional materials. They are sufficiently rigid, they don't disintegrate when you manipulate them, so you can put them together in different ways. And by now we have superconducting, magnetic, insulating, all kinds of two-dimensional materials which can combine in many ways. I am not going to discuss much the metamaterials you can create by stacking two-dimensional layers in the vertical direction. I'm going to look at what's called moire structures. And this is what I'm going to describe now. But before that, let me mention, Kostya already discussed it, that there was like a phase transition in the research of two-dimensional materials when clean boron nitride layers become available to everyone. That I think, to my knowledge, the first paper which discussed how much the quality of graphene improved when it was encapsulated by boron nitride above and below was in this paper. And you notice two authors which come from the same laboratory in Tsukuba, Japan, who provided the boron nitride for this experiment and for basically all the following experiments. So if you look at the citations, the number of papers and everything of these two authors, probably they have more papers, more production than all the Nobel Prize winners in physics who existed ever. The reason being because the boron nitride they fabricate is available for free, and it's very good. I mean, so all good laboratories like to work with this boron nitride. The condition, if you use that boron nitride, what you have to do is to include the people who made the boron nitride in the paper. Okay, so this is an early case of a superstructure made with a substrate, not with boron nitride, but with metal rubidium in graphene before boron nitride. But as soon as boron nitride arrived, people realized that you have, as Kostya said, two honeycomb lattices, one on top of the other. They didn't match exactly, so you created a superstructure at scales much larger than the lattice spacing of each of the individual lattices. This is what I mean. As you rotate one boron nitride with respect to the other, you see there is a pattern which becomes larger and larger, and it cannot get any larger than this because this is when the two honeycomb lattices are well aligned. It's interesting because this looks like a super lattice. I mean, it looks that there is a pattern which repeats itself. It never happens in reality, to my knowledge. I mean, this particular pattern right on the screen right now is not a repetition of a single simple pattern. Each of these blobs is different from the other because this super lattice is not perfectly commensurate. It looks like that, and we theorists tend to overlook the fact that on a very small detail, this is not a real superlattice. And it seems it doesn't matter because the theory you can fabricate, ignoring this lack of commensuration, fits pretty well the experiments. But let me just warn you that most of the pictures like this you see in papers, in theoretical papers, they're not talking about a commensurate lattice which repeats itself exactly after some length. It's something which looks like that, but it's not it. Okay. So this is the way, the very beginning of the field. Different laboratories realized that this boron nitride allowed for these very nice superlattices, and very quickly many places started to work on superlattices. And one of the reasons is highlighted in these two papers is that you could look at something very elusive people knew it should exist, but nobody found it, the so-called Hofstadter butterfly, which is the electronic spectrum of electrons at very high magnetic fields. You had at very high magnetic fields, you have a self-similar electronic spectrum, which is neither a continuous spectrum nor a fully discrete spectrum. I mean, atoms and molecules, they have discrete energy levels, and metals or insulators, they have continuous bands. And what you have at very high magnetic fields, or rigorously at any magnetic field in a superlattice, is this Hofstadter butterfly, which contains a lot of energy levels, but they are some of them are separated, some of them are not. It's a fractal. It's very interesting, and nobody knew about its properties because there was no way to fabricate these to have sufficiently large magnetic fields, so these spectra could be observable. I mean, if you wanted to obtain this spectra with the honeycomb lattice, you need to put a magnetic flux comparable to 1 per honeycomb unit cell, and that meant a magnetic field in the order of thousands of Teslas, which is, of course, impossible to achieve in a laboratory. But if you look at the numbers for graphene or boron nitride, they are more reasonable because with the mismatch between lattice units, if the two lattices are aligned, you have a Moiré supercell in the order of 120 angstroms with about 5,000 carbon atoms inside. And then the typical bands you get at this scale are like 50 MeV. And in order to have a quantum of flux per Moiré unit cell, you just need a magnetic field of the order of 5 Teslas. So this is a metacrystal where you can come close to realizing the Hofstadter butterfly. The graphene superlattices in general are very interesting because what you're doing, these are some early pieces of work. You fold the Dirac cones and depend on the Moiré mini Brillouin. So here you have the initial Brillouin of graphene, which is large, and then the Moiré unit cell is in real space is much larger than the graphene unit cell, and vice versa. In momentum space, the Brillouin of the Moiré pattern is much smaller than the Brillouin of graphene. So these small red hexagons shown here. And playing with ideas related to Moiré supercells, people realized that you could open gaps in graphene, which is not a trivial issue, and moreover, those gaps could have interesting topological features. And then you can generalize these issues to dichalcogenize, where by making a Moiré with some periodic potential and splitting the bands of the of the dichalcogenide, you could actually fabricate true topological insulators that way by making use of the spin orbit of this system. That was very well described in this paper. The thing is that if you want to study one of these moires, where the moire unit cell is like 100 times larger than the graphene unit cell, you can generalize the Dirac description I have already mentioned here by putting these extra potentials, which describe the moire potential, and you can write them in very easy way because you know from the start that they are periodic functions, but if they change sufficiently slowly, you don't need a lot of Fourier component to describe this potential. So basically, with like 6, so you do something, you do an expansion like shown here. So these expansions with very, very few terms in the series work really well. So you don't have many parameters to describe an arbitrary moire, provided that the size of the moire is sufficiently large. So at the end, you have a Hamiltonian which contains not that many elements. I mean, it's no longer a 2 by 2, it's a combination of 2 by 2 matrices, but with maybe 40 or 60 of such 2 by 2 matrices, which describe different reciprocal lattice vectors, which are coupled together, you're done. You can describe very well arbitrary moires in many systems. I'm talking about graphite. And moreover, by looking at experiments, you can fit this very small set of parameters which describe the moire, and these are fits, and this is what comes out of the calculations. You split the Dirac cones if they are broken. So you have a gap, for instance, where the apex of the Dirac cone was, and then you may have secondary Dirac points, which Kostya also mentioned, or gaps. But this is the general idea of what comes out if you study moire superlattices of graphene on boron nitride in this fashion. And moreover, you can do better because, as I said, once you open gaps, the system becomes insulating or semi-insulating. The gaps are small, but they are not negligible. So you can talk about topological features of the curvature of these bands, and you can have secondary and tertiary Dirac points, as Kostya mentioned. So the world of the moire superlattices, which you could create from graphene on boron nitride, or using, for instance, or combining different dichalcogenides with different lattice constants and so on, which is something also Kostya explained, is very rich, and it allows you to fabricate new materials without the actual need of stacking many layers in the vertical direction. You have supercrystals with a much larger unit cell, and you can engineer a lot of features which were not in the original ingredients of the moire system. Okay. So now I'll go a bit further, then I'll make a stop. Now let's discuss the ultimate or the most recent and most outstanding discovery which has been made in connection with moires in graphene, and that is the superconductivity and many other still not well understood phases in graphene. And it started like 3 years ago with these famous, by now famous papers in Nature. At the same time, a talk was given at the March meeting of the American Physical Society, and these 2 papers were posted in the archives, or everything simultaneously. That really generated a lot of attention because these phase diagrams shown here are very remarkable. People thought that graphene was the opposite of a superconductor, basically because being a semi-metal, it had very low, I mean, even if it had a finite density of states, it was very low. So you needed very strong interactions to have any remarkable effect due to interactions. I mean, in order to have new phases, you need strong interactions and a high density of states, and the second part was lacking in graphene. However, these people argued very convincingly that they were observing insulating phases, which are in red, and also superconducting phases as function of the filling in these samples where one graphene lattice is twisted with respect to another. As I said, everybody was very much interested since the discovery. It was confirmed in other laboratories shortly afterwards. And since then, it has been one of the most active fields, not only in research in two-dimensional material, but I think research in condensed matter physics in general. This is a first summary of the communities which were looking to these problems. And so it was like a year after the experiment. And you see that people with many different backgrounds were very much interested in these systems, people who knew about strongly correlated systems, about topological systems, and you could look at optics, at transport, local pros, and so on. So there was space for many types of research and for many possible backgrounds. And this is what Pablo Jarillo Herrero et al. Achieved at MIT. They rotated one graphene layer with respect to the other. And then you notice you get the same or very similar moire patterns like the ones which you get when you rotate graphene on top of boron nitride. The only difference is that because the lattice constants in graphene and graphene are the same, there is no upper limit to the size of the moire. So you can make them as large as you want, provided that you manage to get the two graphene layers fixed, pinned one with respect to the other, which seems to happen, but I think many other people think as well. It's still a mystery why they don't snap back into place, or maybe they do sometimes and some other times they don't. So let's continue. So this is another picture. Here there are the two layers, and as you change the angle, you see how the pattern grows and grows. So this is, I mean, if I make a larger pattern, it will be difficult to appreciate any detail in the slide. The angle at which the experiments I showed to you before were performed is more like 1.1 degrees, so it's even smaller than this, which means that the unit cell is about 12 or 13 nanometers, and you have like 10,000 atoms inside the moire unit cell. So it's really a large moire unit cell. And, okay, sorry, I forgot to say that. And what you see here, this is the center of the unit cell, or maybe. And you see here regions where the two layers are stacked in the AA fashion, one directly on top of the other. And there are regions where the stacking is AB, and other regions where the stacking is BA. And what I mean by that is that it's different where which one is on top and which one is below. And if you compare these two regions, the situation is interchanged. So that means that you're putting the system definitely has become a lot of quite more complex. The reason being that there are no boundaries between the regions, but you're gluing together regions which at low electronic energies are very much different. because you go smoothly from this situation to this situation. Definitely you can confirm that doing electronic structure calculations. Now I will move into that. I'm going back to theory. And this is what you have out of a simple tight binding calculation, like the ones I mentioned at the beginning, what you put by hand, all your pieces, your carbon orbitals, and then you simply add a coupling between, you put a small angle, here is 1.6 or something like that. This is a truly commensurate situation. Otherwise, you cannot perform tight binding calculations. So you get something which at this scale, which is small because this is electron volt, at this scale is very narrow. And if you amplify, you see a very narrow band whose width is in the order of a few electron volts. Maybe it is time for me to stop here, like Kostya did, for 5 minutes, if it's okay with the chairman.
Yeah, I think it's a good time for a short break, 5 minutes.
So it's okay, because the sound quality I received from you is not that great. So is it okay if we stop for like 5 minutes?
Yeah, yeah.
Okay, great. So I'll be back in 5 minutes. It's fine. I can ready to start anytime.
I think we can start, but we have one question in the chat. How do you control the staking AA or AB between two layers?
Sorry, can you maybe write it in the chat, because I have a very bad sound coming from you.
Okay.
Stop sharing for a moment. If you could put the question in the chat, because for reasons I don't understand, I received you not very well.
Okay, I just type it in the chat. Do you see in Zoom chat?
Oh, that's a good question. I think nobody does control the stacking. That's a good point. Nature chooses for you AB. If you twist one graphene layer with respect to the other, then definitely you have to you force the system to have both types of superpositions. That's a bit shown in this is the unit cell of the moire. It's shown here not very well. I mean, the corners are AA type, and these regions are AB and BA. That is just pure geometry, and there you're forcing the system to take a stacking order which is not favorable energetically, but it does, and it gets stuck there, as I mentioned, for reasons which I think are not yet very well understood. But there are many open questions in this connection. But nature prefers always the AB stacking, and then there are two choices, which Kostya mentioned, rhombohedral graphene or Bernal graphene, which is AB. It looks better, it's better energetically than ABC, but it's another possibility which is found in nature as well. Okay. Okay, sorry. Okay, so let me then continue. If there are more questions, you're welcome to use the chat or whatever. The research in graphene has been often theory-driven, which is interesting for me because I'm a theorist. And this is a particular case. The Pablo Jarillo Herrero's group at MIT was fabricating these twisted samples because he knew the prediction that there were very narrow bands, that if the twist angle was sufficiently small, there were theoretical predictions according to which there were very narrow bands with a high density of states very near the Fermi energy. The model for twisted bilayer graphene was kind of written down very early on in 2007 in this paper by João López dos Santos, Nuno Pérez, and Antonio Castroneto. And then it was studied extensively by Rafi Bistritzer and Alan McDonald in this other paper. And this, at first, nobody worried about very low twist angles because they thought they were not going to be very physical. But these two guys, they did study what happened at very low twist angles, and they realized the existence of these very narrow bands, which separately and simultaneously were being studied using tight binding methods. So two of the methods I mentioned to you before in connection to moires were applied to twisted graphene at small angles before the samples existed. And let me just mention that shortly later we noticed that there was even a situation where these bands were infinitely flat, where the bandwidth was mathematically zero. Okay, and this is a bit what happens in twisted bilayer graphene. These are the two Brillouin zones. The large hexagons are the two Brillouin zones of the two layers, and all the action in graphene is at the corners of the Brillouin zone. So you have 3 equivalent K points and 3 equivalent K prime points for each layer, but the two corners are oriented in different ways depending on where you are. So that's what I'm trying to say. What matters is the K layer of layer 2 and the K layer of layer 1. And they look one with respect to the other like this if you look at this K point, but if you look at this other K point, one is on top of the other, and if you look at this other K point, there's a different relative orientation. And because of that, and then these samples are very, very clean, they're encapsulated with boron nitride and so on. So the tunneling between layers takes place conserving parallel momentum. So then a plane wave which resides in one layer shifts to the second layer and shows up in the second layer as a superposition of 3 different plane waves because of this multiplicity of relative orientation. Then when it is reflected back to the first layer, then it becomes 9 plane waves. So the situation very quickly becomes very complex and there are multiple interference and so on. That wouldn't happen if all the action was at the center of the Brillouin zone. Then the situation would have been much more dull. But because of these multiple scattering processes which happen when you go from layer to layer and back, you have a relatively complicated situation. However, what you can do is you take your Dirac equation once more and you just put by hand a kind of approximation to the tunneling between layers. And what you do, this is the Dirac equation, and what you do for the tunneling is the same story you do for Moirés. In general, you expand in as few reciprocal lattice vectors as possible. And it turns out that you're done with 3 reciprocal lattice vectors. So all the complexity of a twisted bilayer is in this set of 4 first-order differential equations coupled together. So from the mathematical point of view, this doesn't look to be a big deal. The solution of this problem, however, is really cumbersome and complicated. So this is the kind of parameters you put near one of these magic angles. And this is what I was trying to say, that you have a relatively simple Hamiltonian where the energy scales are not small. And at the end, you have this very complicated pattern with very many bands, broken bands, and many of which are very flat. And if you want to solve it mathematically, you put a lot of reciprocal lattice vectors coupled together in the same way you do with Moirés. The only difference is that some lattice vectors are in one layer and some of the wave functions are in one layer, and some of the other wave functions are in the other layer. And at the end, you have to diagonalize like a 400 by 400 Hamiltonian, which is quite remarkable because, as I mentioned before, this model describes well the narrow energy bands of a Moiré system where you have 10,000 atoms in the unit cell. And this is what I'm trying to say. To change the angle, this is the narrow bands. This is how they evolve. They become very, very flat, and then they become wider again. This is what the very interesting feature noticed by Rafi Bistritzer and Alan McDonald in 2011, which motivated Pablo Jarillo Herrero to look for the transport properties of twisted bilayer graphene. So this is again the bandwidth versus angle. And so this is a particular case, the one I showed to you, and this is the kind of charge distribution you have for different states in the narrow band. This is a very special feature of twisted bilayer graphene because, as I will mention later, there are narrow bands in other materials in condensed matter, but typically the charge distribution is the same no matter which point in the brilliance zone you study. And if you go to even a smaller angle, then the number, you have many Dirac points which proliferate and a very complex picture, which becomes even more and more complex the lower the angle. Possible way of studying it is the original way studied by Joao Lopez de Santos et al. You start with your Dirac cones, which are shifted one with respect to the other. You turn on the hopping between layers, you open gaps, and you see that the central region becomes flatter. But that doesn't explain the flat band, because it doesn't explain what happens around here, where the bands remain dispersive. Another way of doing it is to use, to simplify the most you can, this Hamiltonian in terms of many Bloch waves. If you keep only 8 Bloch waves, you already have a description. So you deal with a 16 by 16 Hamiltonian. You already have a good description of the first magic angle, which again is interesting. And what is also interesting is that the bands are very narrow, and it means that they always have Dirac points, but the narrow band means a very low Fermi velocity. And the reason the Fermi velocity is very low is not because the electrons move slowly in each layer. It's because they move basically at the same velocity in each layer, but in opposite directions. The wave functions are a superposition of 2 wave functions moving in opposite directions, and then the Fermi velocity of the quantum object is basically 0, or is actually 0. Where the magic angles come from is still a mystery. Let me just repeat that there is this particular simplification of the model, which is called now the chiral model, where you can prove that the bands are infinite, at the magic angles are infinitely flat. That's interesting because there is another situation where you have flat bands and a lot of interesting electronic features, and that is the Landau level. And in fact, mathematically, the flat bands of twisted bilayer graphene are reminiscent of Landau levels. So there is a connection between Landau levels and twisted bilayer graphene, which was overlooked at the beginning. Let me also mention that if you keep making the angle smaller and smaller, you create giant unit cells. And then there is a lot of relaxation, and you create, I don't have the time to go in details through all this, but you have channels which between regions which are basically A, B, and BA. So what you have is something like that. This is the unit cell at very small angles. The dark triangles are either AB or BA regions, and then there are channels between these AB and BA regions. And then you have like quasi, I cannot turn on the animation. But the thing is that you have, maybe it's here, quasi one-dimensional channels. Let's see. You see now the band moves as function of a bias field. This is applying, and the more marked the channels are, the more one-dimensional the system becomes, which is also remarkable. So this is the region of very small angles, which is also quite interesting, and it started being explored experimentally now. But these angles are less than 0.5 degrees. And now, as I mentioned, you have narrow bands in other materials in nature. There are, for instance, the copper superconductors, they have narrow bands. The heavy fermion materials, by definition, have narrow bands, or the manganite oxides. In most cases, what you have, that's very clear in the heavy fermion materials, you have F orbitals, you have rare earths, which support F orbitals, highly localized orbitals, and the narrow bands are based on these orbitals. And moreover, or in the case of the cuprates, in the bands are from d orbitals of copper, but the atoms, in order to be hybridized between the different orbitals, in order to be hybridized, you have to go through an oxygen atom in between, whose levels are far away, and that decreases very much the Hoping matrix element. And then in addition, as soon as these narrow bands, these bands become narrow, you have to deal with interactions, and then the electrons become even heavier, because then you have magnetic excitations and other types of excitations related to the interactions, and they drag the electrons. So you have electrons strongly dressed by other excitations, and they become even more slow. But that's not what happens in twisted bilayer graphene. The picture of the narrow bands didn't take into account interactions at all, and didn't include any energy parameter, which was really small. Okay, now I will switch to theory a little bit. The way to proceed, according to many theories, the way people have dealt traditionally with strongly correlated systems is by studying the local properties of the bands. Typically, as I said, a narrow band implies local orbitals, and if you study the way electrons sitting on those local orbitals interact with each other, you get some understanding of what's going on. The problem, so for that, there is a well-defined procedure in condensed matter physics. You have to define Vanier function. The problem is that if you try to do it, which was done right away after the experimental discovery, is that the Vanier functions you get are really mysterious. They are not localized. I mean, they are defined in a meta-hexagonal lattice at the scale of the moire, but they have this kind of shape. I mean, each Vanier function has 3 lobes pointing in 3 different directions, and they seem to overlap in the center of the hexagon. So this is a kind of cartoon of the Vanier function. To my knowledge, there were no Vanier functions like that in condensed matter before. Moreover, these Vanier functions are so complicated that they are even questionable as the basis for local description. That's what's called fragile topology or the abstraction. This is an open question, still kind of controversial. The point is that the band is very different depending the narrow band. It's a bit like what you have in a hybridized band. The band changes character. The band of twisted bilayer graphene changes character very much. And then there's no clear way how to describe a wave function which fits well the band everywhere, because in this case it can be either S or P, but you cannot define a wave function which is at the same time S and P. So this is an illustration of some theoretical models which have been used. I mean, what I'm trying to say is that people at the beginning thought the problem was going to be simpler. It isn't, and because of that, many schools, many approaches have arisen. There are still people looking at localized starting models, like the Hubbard model. And then there's the point of view that perhaps totally delocalized bands, like the bands formed by Landau levels in two-dimensional metal in a high magnetic field, is appropriate. And then as you have very narrow bands with very sharp peaks in the density of states, maybe you can deal with Van Hoff singularities. There are many ways, it's like the proverbial elephant described by blind men. There are many ways to describe the electronic properties of twisted bilayer graphene. The whole thing is not yet settled, and that's why there's so many theoretical works appearing in ConMat every week. if what one can do is to classify interactions. And this is the unit cell again, it's in the order of 12, 13 nanometers. The charges you get by applying a gate are not uniform. That doesn't happen in ordinary graphene. When you apply a gate, electrons flow into a graphene layer, and that way you can tune the number of carriers in the graphene layer. But the charge of those carriers is uniformly distributed. In twisted bilayer graphene, that doesn't happen. The charge density of the carriers depends very much on the filling you have. So you create like a superlattice of quantum dots, because at the beginning, most of the charge goes into the corners of the unit cell, and then eventually the charge becomes more homogeneous. And that, if you use that description, then you can define some kind of Coulomb energy of these blocks of charge, and it's significant. It's like 100 MeVs, and as I said, the theoretical bandwidth is 5 MeVs. So interactions are much more strong than the dispersion itself. You can classify the interactions using the fact that the number of atoms in the unit cell is large. And as I mentioned, the leading interactions are the long-range electrostatic interactions. Then you, in addition, have electron-phonon interactions and atomic interactions like the Hubbard interaction, intra-atomic interactions. But in order, for instance, for a Hubbard repulsion to play a role, you need 2 electrons of these narrow bands to sit together in the same atom. So that gives you a factor of 1 over the number of electrons squared. And now in the unit cell, you have a number of electrons, which is n. So at the end, you have an energy scale, which goes like 1 over n, but the Coulomb interaction is inversely proportional to the size of the Moire unit cell, which goes like the square root of n, because n is proportional to the area of the unit cell. And as I mentioned, when you, depending on where you are in, this is one of these narrow bands, depending whether you are at the center of the Brillouin zone, you have a relatively homogeneous charge, but if you are at the corners of the Brillouin zone at the Dirac point, you have charges very much localized at the AA regions, at the corners of the unit cell. This is another way of plotting the unit cell. I'm using an hexagon instead of a rhombus. So as I said, unlike what happens in just a single graphene layer, you apply a gate to twisted layer graphene, you increase the number of carriers, and you create an inhomogeneous distribution of charge. And then that has an effect back into the band dispersion, because you start with this red band, and as you fill it up, and with just a simple Hartree approximation, you change the shape very significantly, the change of the band. The dispersion of the band is very strongly dependent on how many electrons you have in that band. That doesn't happen in other strongly correlated systems in condensed matter physics. If you look at the Hubbard model, the bands are shifted rigidly as function of the number of carriers, and that's the end of it. All the action is happening because of the local interaction within each atomic orbital. And that means, this very simple mean field analysis implies that a new interaction emerges in twisted bilayer graphene, which was called way back electron-assisted hopping. The hoppings which describe the band, because it's a localized band, so in principle you can describe more or less well in terms of hopping. How large they are depend on how many electrons you have in that band. And I appreciate Misha Cardenson for pointing out to me these early references. That was a topic strongly pushed by Jorge Hitch from UC San Diego in connection with superconductivity in recuperates. he claimed that the Hubbard model was not enough to understand superconductivity in the cuprates, and you needed extra interactions, and in particular, he signaled this electron-assisted hopping interaction. We looked at that, and other people have found the same situation, and it makes sense because you have these strange Vanier equations which occupy the same regions of space. So it makes sense that when you change the charge in one Vanier function, the coupling between nearby Vanier functions is also changed. This is a cartoon of what I'm trying to say. You have a hopping, but depending on whether this site is singly or doubly occupied or not occupied at all, the hopping may change. This is an interaction because it requires two electrons. And moreover, you Fourier transform this interaction. It has it's a hopping, it's non-local, so it has a Q dependence. And a Q dependence means that it's an interaction which can change sign, even if you start from purely repulsive interactions. This interaction can be either attractive or repulsive. And you can make simple models based on these strange Vanier functions, and you fit these mean field results quite well. This is an example of how much, with realistic parameters, how much the narrow bands are actually distorted. These are the original bands without interactions calculated by Stritzer and McDonald, and this is where they go when they have field, when you move away from the neutrality point. And even if you have totally flat bands, this mean field analysis will tell you that they become dispersive because if you start increasing the number of electrons in these bands. So twisted bilayer graphene is a system where you can have bands where the dispersion is solely due to interactions. It has nothing to do with the kinetic energy of the electrons. And then there is the exchange term. So far I have discussed what is called electrostatic. They have three terms. The exchange term is also interesting because actually in graphene, it renormalizes the Fermi velocities. The interaction which people knew was important in graphene. I mean, it makes graphene similar to quantum electrodynamics and leads to an experiment-dependent Fermi velocity renormalization and so on. What happens in graphene, these are studies by us, but other people have found the same. You have a lot of broken symmetry phases. You can open gaps at the neutrality point, away from the neutrality point. Basically, you open gaps everywhere. So the initial picture of non-interacting narrow bands breaks down in a big way. Actually, it turns out that simultaneously there were experiments confirming this picture. So you have many possible phases depending on the filling, and then you can have electronic phase separation and whatnot. I mean, it's definitely it's a very rich system to study. These are more theoretical calculations which confirm this picture that the bands are by no means flat as soon as you include interactions. So at the end of the day, the bands which you thought that in the absence of interactions had a width of 5 electron volts or so, they turn out to have 20 or 30 depending on the dielectric function of the environment or the strength of the interactions and so on. But what is more interesting is that this picture has been confirmed by experiments. These are STM experiments, and they all show a density of states which is much wider than a few electron volts. There are narrow bands indeed near the neutrality point, but much wider by almost an order of magnitude than the bands you expect from these non-interacting band structure calculations. These are other STM experiments and other measurements of the direct measurements of the electronic compressibility. And this is our picture, our approximate picture of what's happening. by using a simple mean field Hartree-Fock arguments, which, as I emphasize, is in agreement with many other calculations. So to start with, let me just say that to a first approximation, twisted bilayer graphene can be well described by a well-tested approximation in condensed matter physics, which is the Hartree-Fock approximation. The only thing is that the outcome of the Hartree-Fock approximation is very unexpected. It's not what you get when you do the Hartree-Fock calculation for the bands of a normal metal, where you see that the same metal with slightly different band dispersion and so on. The Hartree-Fock approximation describes a number of very unusual features of twisted bilayer graphene. You don't know to go beyond that. However, you cannot tell. It's clear that there are these strongly correlated phases, which are probably spin or valley polarized, but it doesn't tell you whether these phases are going to be magnetic or valley polarized or what. The interesting thing, I mean, there are other experiments which people have claimed to see superconductivity and strongly correlated systems in other types of graphene stacks, bilayer graphene in a substrate. And we have done calculations about that. Tri-layer graphene also in a substrate, where people claim to have found superconductivity. Again, we have experiments, we have theory. The theory is totally different from the theory I just mentioned. This is more conventional theory, rigid bands and so on. These systems behave more like conventional interacting systems with narrow bands. And the same thing for bilayer graphene. Actually, some of these experiments, the first version of the paper mentioned superconductivity, then the published version doesn't include superconductivity. Again, our calculations suggest that these systems are not as weird that way as twisted bilayer graphene proper. And nowadays, this list of experiments I have mentioned right now are, at least the part associated to superconductivity is kind of questioned by many people, by many experimentalists. But the message here is that twisted bilayer graphene is very special to create situations which look like twisted bilayer graphene, and you lose many of the special features and the superconductivity of twisted bilayer graphene. There is also the question that the dissipation is very unusual, but I'm not going to deal with it. But let me go back to superconductivity. What is special about superconductivity in twisted bilayer graphene is not the high critical temperature, it's 1 Kelvin, 1.5 kelvins, even at most 2. What is special is that in these very complex phase diagrams, the phase which is always there is superconductivity. And sometimes you see superconductivity and nothing else, like in this experiment. So that's very different from what you have in the copper high TC superconductors. There, or in heavy fermions or in the pnictides, the main and the most important phase is magnetic, typically antiferromagnetic, and superconductivity is like a side effect near a magnetic phase. Twisted bilayer graphene is unlike that. It's the common theme of twisted bilayer graphene is superconductivity, it's not magnetism. So it seems likely that the mechanism for the formation of superconductivity is not the same as the one in other strongly correlated materials. So now let me finish by discussing what could be happening. Also, this is very speculative. The main paper about superconductivity, or the seminal paper dealing with superconductivity out of repulsive interaction, was done by Walter Kohn and Joachim Luttinger way back in 1965. And they noticed that because of the sharpness of the Fermi surface, you had Friedel oscillations. Friedel oscillations meant mean a potential which changes sign, so it's sometimes attractive. They calculate high order effective interactions due to screening, which included Friedel oscillation and so on between electrons in a three-dimensional electron gas, and they found superconductivity. However, at very, very low energies and high angular momentum. But definitely that was the first proof that you could get repulsive interactions and nevertheless superconductivity. These are papers which have applied this scheme. I'm going to mention what I will have done, but these are other papers which have applied this scheme to twisted bilayer graphene. Twisted bilayer graphene is very different from the three-dimensional electron gas which Korn and Latinger studied. You have a continuum of electron-hole pairs. You have a plasmon which shoots above the continuum of electron-hole pairs, as discussed in this paper by Cyprian Lewandowski and Leonid Levitov. And then the phonon just overlaps with the peak in the density of electron-hole pairs. If you look at what happens in a 2D electron gas, the plasmon is at much lower energies than the bandwidth, and because of that, you don't have electron-hole pairs which overlap with the plasmon. So your low energy excitations in twisted bilayer graphene is a combination of plasmons, electron-hole pairs, and longitudinal phonons, which are the ones which couple to electrostatically to electron-hole pairs. And that's all. And this is what we found numerically I presented before a cartoon, but these are actual calculations of the continuum of electron-hole pairs, the plasmons. Here the phonons are excluded, and here the phonons. For realistic values of the parameters you plug into your model for twisted bilayer graphene. So as I said, at low energies, these are milli-electron volts, you have this combination of possible low energy excitations. In addition, if you have magnetic phases, you will have magnons and whatnot. But let's for the moment leave out that possibility. Let's just consider which kind of pairing these low energy excitations may induce. Actually, if you look at the screen interaction in real space, you get attraction. And that was already noticed using tight binding calculations in this paper. This is not the attraction discussed by Korn and Latinger, because the Fermi surface of twisted bilayer graphene is very complicated, and these are by no means Friedel oscillations, but definitely the effective interaction between these two electrons in twisted bilayer, if you add to twisted bilayer graphene, includes attractive features, which is suggestive. So what we did, and I apologize for this very formal slide, what we did was to calculate diagrams like the ones calculated by Kohn and Latinger. The only thing is that as the density of states is very high, we didn't stop at a low order. We included the full RPA calculation of the dielectric function of twisted bilayer graphene. And in addition, we will use the very complex wave functions you have in twisted bilayer graphene associated to these multiple scattering events I mentioned already. This is a bit a summary of the input we were using, and this is what came out of the calculations. We got superconductivity, especially when we had the plasmon. The superconductivity, the order of magnitude of the critical temperature, is comparable to what you have in twisted bilayer graphene. I don't think that matters much, because I heard, I think, Alexey Nikitin way back that the serious theories should never put a lot of faith in a calculation of the critical temperature, because after all, the critical temperature is very, very dependent on many parameters. But the trends you have here as function of angle, the critical temperature is highest at the magical angles and so on, is the right one and depends on the doping. If you take away the phonons, you still have superconductivity that is more Kohn-Latinger-like. That was also discussed in this paper, but then you will have critical temperatures in the order of millikelvin. And the critical temperature, of course, depends on the nature of your environment, how well screened the interactions are, and so on. The Fermi surface contains many pockets, and typically the order parameter, what we did basically was to linearize the superconducting order parameter and solve, and it still is numerically a very complex calculation, almost beyond our possibilities. The order parameter basically is limited to the regions near the pockets at the Fermi surface, and what is remarkable is that the order parameter doesn't show sign changes at the Fermi surface, which is unlike what happens in a typical Kohn-Latinger system, where the order parameter, and that's why it has high angular momentum, changes sign. This is what I'm trying to say. This is what we found. If we exclude by hand a lot of processes, you get an order parameter which goes from positive to negative and so on, which means high angular momentum on the Fermi surface, which is more Kohn-Latinger-like. Here, the complexity of the order parameter and the existence of many low energy excitations conspire to give you an attractive interaction at small momentum, which is not what happens in a more simplistic Kohn-Latinger-like system. And then the only thing is that very much like the Hartree-Fock approximation, what we did, it doesn't tell you whether you have a triplet superconductor and a valley singlet or vice versa, because graphene has this extra degree of freedom, which is the valley degree of freedom, because there are always two Dirac cones, no matter how you start from, where you start from. So the details of the superconducting phase you cannot get from this from calculation like this of this type. Here there are more effects. Let me just you can generalize it to broken symmetry phases like the ones which probably exist away from the neutrality point or according to experiments. And then, as I said, we were very much limited by our computing power, so we had to exclude a number of effects, but we don't think those effects will change things qualitative. And at the end of the day, what you have is a new superconducting mechanism, indeed intrinsic to twisted bilayer graphene, and it's shown in this absence of sign changes in the order parameter, which also implies that you don't have that much pair breaking as in other strongly correlated systems. Let me finish by saying that the very latest experiments show superconductivity in tri-layer graphene, where the planes are twisted in a particular way. The top and bottom planes are not twisted, only the central plane is twisted. I could never imagine that that could be done, but it was done at the MIT, again by Pablo Carrillo-Guerrero's group, and at the University of Harvard by Philip Kim's group. And as in the other cases of twisted, as in the case of twisted bilayer, I think they also found a lot of superconductivity. And then one of the reasons is that on symmetry grounds, you can decompose this geometry into a twisted bilayer and a monolayer. And the twisted bilayer inherits all the properties of the twisted bilayer graphene I have described before. We already have done some calculations, and at least they are consistent with experiments in the sense that we find that these trilayers, unlike the other trilayers I mentioned before, are not that different from the trilayers, from the twisted bilayer. I mean, there are many ways you can change the narrow bands. It's not only the interaction. Let me mention that the substrate can change a lot the narrow bands. And these are our calculations and other people's calculations. This is interesting because another thing which can, let's see if I can manipulate this. maybe not. Another thing which can change a lot. Sorry. Now I have lost track of my pointer. Okay. Another thing, I apologize for not being able probably to, or maybe yes. No. Sorry. Another way of changing a lot the narrow bands is by strains. Strains can make them even wider than interactions. I had an animation here, but it seems complicated to show now, so my apologies. So let me just finish by, this is a bit summary of the last part of the talk. First, twisted bilayer graphene at magic angles, they have this, this very special bands due to multiple scattering events, which can be very narrow. These bands are strongly distorted by interactions, by other effects as well. And they, in that respect, they're rather unique. They're not like most interactions in systems with narrow bands where they are not distorted. They may become narrower at most, but they never become wider because of interaction, and they don't change the shape. And finally, the combination of these very special wave functions and the high number of low energy excitations can give you a first explanation of superconductivity in these materials. Thank you very much.
Thank you for brilliant talk. We have a question from Alexey Nikitin. Is it possible to find the magic angle not in the graphene, but
sorry again, I lose the sound. Maybe if...
Okay, I will send you in the Zoom.
If you can put it in.
Yeah, yes or no?
Excellent point. Okay, the materials where this topic has been mostly studied is in twisted dichalcogenides. Twisted dichalcogenides, they already have a gap. So what happens when you twist is that there are narrow bands which drop below the conduction band or above the valence band. But the origin of those bands is simpler. If you have a semiconductor and you create a periodic potential, you will, if the Moiré potential is very perfect and very clean, instead of localized defect levels, you get narrow bands. These bands have not shown yet superconductivity. They have shown interesting features which are compatible with magnetism and so on, but not with superconductivity. But this is a topic also very intensively studied, narrow bands in other twisted two-dimensional materials.
Okay, thank you again. So now we have a break, and the next lecture is Graphene Plasmonics by Professor Alexey Nikitin. So see you in 1 hour. Thank you.
Yeah. Is it in the chat? I don't find the question. As I said, it may be my fault, but I listened to you not too well. Oh, now there's another. I don't see any new message. Sorry. Have you typed the question in the chat? Sorry, but then I can say something more about the structure artificial surfaces. That's another thing people are studying, how to fabricate other Moiré systems with flat bands by manipulating the substrate. So with gates which have some spatial dependence and so on. There are not many results yet, but I imagine that they will come soon. Thank you. It was great to give this talk. Thank you.
Алексей, здравствуйте.
Добрый вечер. Как вы слышите?
Скажите, пожалуйста, вам вот хотел спросить по лекции вопросы, как задавать по ходу или в конце, или как вы можете паузу, может, где-то посередине сделать, и там вот, если накопившиеся есть, я задам где-то.
Можно. У меня будет несколько частей.
Ага.
То есть основных 3 части, можно после каждой части.
Хорошо, давайте так.
Вопросы, а сколько вообще? Я видел, у меня видено 1,5 часа, но мы как-то чуть раньше закончим или не обязательно?
Как вам удобно, то есть сколько нужно времени, столько и берите. Нужно больше, можем чуть больше взять, нужно меньше, если уложимся, тоже без проблем, я думаю.
То есть нет такого формата, что там, скажем, 15 минут на вопрос?
Не, на вопрос сколько-то времени выделяется, да. У нас всего 1,5 часа, ну да, то есть где-то минут 10 хотя бы на вопрос нужно оставить, то есть где-то так сам доклад ориентироваться, да, на час 20.
Окей, потому что завтра ведь будет совершенно другой формат.
Да.
Завтра нужно будет, чтобы люди могли свои экраны шерить и писать.
Да, там что-то, я про это что-то слышал, еще до конца не разбирался.
Ну, в общем, есть возможность такая, чтобы расшаривать экран у участников. Так, то есть у любого участника.
Да, я думаю, что завтра вроде бы будет просто все в Zoom происходить. То есть сейчас они через приложение вас смотрят, а завтра будут все просто в Zoom подключаться, вот как мы сейчас. Так.
Окей, тогда может
быть, у нас еще 10 минут,
расшарить.
тогда вроде бы...
Я могу попробовать расшарить презентацию.
Да, пожалуйста.
Так, видно?
Да.
Нормально видно? Сейчас
да, все отлично видно. Так,
то есть вот у меня будет 3 части. Это как бы введение. Ну, после введения, наверное, нет смысла вопрос. А вот эти 3 части, раз, два, 3, после них можно сделать паузу и люди, посмотрим, будут спрашивать или нет.
Мне кажется, можно вот после второй части, после первой части, то есть введение, первая часть, можем сделать паузу там. Да.
После введения. Ну, после введения, наверное, как раз вопросов не будет, потому что...
Не нужно, да, вот после вот launch and control, мне кажется, вот перед imaging of plasmons можем сделать.
Окей. Сейчас я хотел глянуть, как будет видео.
Да, я за вопросами буду следить, я вам их просто прочитаю тогда, если что.
Хорошо. Так, для видео, наверное, нужно убрать лазер-поинтер и запустить. Нормально видно? Это нормально, что оно так быстро движется, специально ускоренно.
Ага, все видно, да. Все хорошо, да, супер.
Отлично.
Звука нету.
Ну все,
да?
Ага. Звука не должно быть.
Все, хорошо. Все, тогда через 10 минут начнем, я объявлю.
Но мне нужно отрубиться или прекратить расширение?
Не, будьте здесь, все нормально. Можно, наверное, пока звук выключить просто.
Окей. Хорошо, все, я тогда отключаю камеру и микрофон. Спасибо большое.
Yeah, hello everyone. So this is our last talk for today. And it's my great pleasure to introduce you the next speaker, Professor Alexey Nikitin. He received his PhD in theoretical physics in 2006 from Institute for Low Temperature Physics and Institute for Radiophysics and Electronics in Kharkiv, Ukraine. He worked at the University of Zaragoza and the Basque Nanoscience Cooperative Research Center, Nanogon. Now he is the head of the group on two-dimensional nanophotonics at Donostia International Physics Center. His research topics include light-matter interaction with two-dimensional materials and artificial low-dimensional materials. So let me give a floor to Professor Alexey Nikitin for his lecture entitled Graphene Plasmonics. Alexey, please.
Okay, thank you. Thank you, Oleg, for this introduction. I will now share my screen. So I hope this. So this one you've had already two excellent lectures from Professor Konstantin Novoselov and Professor Guinea. I will try to complement a little bit these lectures by showing you some research that we have been doing this year related to light-matter interaction in two-dimensional materials, particularly about plasmon polaritons in graphene, how you can manipulate light with the help of graphene. So I will explain a few topics, not too much, and I will be happy if you could understand at least a third. I will really already happy. So to start with, I would like to show you where we are located. I just will take a laser pointer. Okay. So we are located in the very north of Spain, in the frontier, nearly the frontier with France. This region is called Basque Country. This is a Spanish part of Basque Country, and the city is San Sebastian. It's a very nice city. So our center is located somewhere there. So please come to visit us. We are open to visitors. If centers, several research centers in San Sebastian, let me know. This is our team, which includes a few PG students. Most of them are here in San Sebastian. Arturo has not been able to join this photo. Actually, this photo has been done this weekend. That has been like the first group meeting after the 2 years we have not met. And also these students collaborate with me. They're Olga Matveyeva from Moscow Institute of Physics and Technology. She's sitting in Moscow and we are working remotely. And Kirill Voronin is joining our team this year in San Sebastian. This is the outline of the presentation. As I mentioned, I will not give you too much. So I have picked up a couple of topics which could be of interest for you, and I will try to be as detailed as possible. So we will start with a short introduction into plasmons in graphene, and in general into nano-optics. We will consider the diffraction limit, how to overcome this diffraction limit. We will see what the plasmons are in general, plasmon polaritons, and then we will consider plasmon polaritons in graphene. Then we will see how to excite and manipulate plasmons in graphene with the help of so-called optical antennas made of metal. Then we will see how one can shape the wavefronts, or how one can bend light, for example, refract it with the help of two-dimensional lenses. And then we consider the graphene plasmons closed into the so-called plasmonic cavities, which are actually seen also as antennas made of graphene plasmon antennas. We will see how the resonances in these antennas are built up and how one can image them and see in real space, observe with the help of near-field microscopy. And then in the last part, I will touch a little bit the applied aspects of graphene plasmonics, namely how one can construct graphene sensors or graphene detectors in the terahertz and infrared frequency ranges. So let's start with the introduction, namely with the diffraction limit. Basically, all the nano-optics or manipulation light on the nanoscale deals with the diffraction limit, because the diffraction limit tells us that if a wave propagates in a free space, you cannot compress this wave into a volume which will be smaller than the wavelength of this wave. And this is closely related to this so-called uncertainty principle, which is nothing else but the consequence of the Fourier transform, which basically tells us that you cannot resolve an object which has the size smaller than certain width in momentum space, which is equivalent to half of the wavelength. So because you cannot compress light down to these dimensions, for example, optical fibers where we have signals where we transmit information by internet, so they have a certain minimal diameter, which should be comparable with the wavelength of the light along the fiber. And then, of course, the device transforms this light into other frequencies to get an access to Wi-Fi. But actually now already several big groups are working on the next step, which would be Li-Fi. So it's like Wi-Fi, which is operating at gigahertz frequencies. So Li-Fi is supposed to operate at visible frequencies without any cables and fibers. And of course, for these devices, new devices, it's very important to manipulate light on very small scales if we want to make small optical technologies. But fortunately, the diffraction limit does not apply to the so-called evanescent waves. So the evanescent waves, electromagnetic waves, whose amplitude decays in one of the special directions. And in this case, because of this exponential decay, one can manage to compress light on the scales much smaller than the wavelength. A very simple example of evanescent waves could be seen in an experiment, which is nothing else but total internal reflection. So if you have a laser beam shining a prism, and then you would have at the exit of the prism a refractive beam. But there is a critical angle under which there is no transmitted beam, so there is no refraction, and everything gets reflected. So no light passes through in this half space. But in reality, there are some fields which are exactly evanescent fields, which decay exponentially out from the face of the prism. And these fields could be observed using the near field microscopy, for example. Another good example and very relevant for us is surface waves. The surface waves we could observe daily on the surfaces of water. If you throw a stone into water, you immediately see waves emanating on the surface. But actually, conductors or metals also could support a kind of surface waves, but these are electronic. Well, we can treat electrons in some approximations in metal like gas or even like a liquid. Okay, and then this gas, and then since it oscillates, it creates dipole, and they connect to the electromagnetic field. You create a so-called or hybrid waves, light matter waves, which are called in general such kind of waves are called polaritons. But in case of metals, they're called plasma polaritons because, as I said, you could treat electrons in metal as gas, and charged gas is a plasma. This is why these are plasma. So these are plasma polaritons. Instead of throwing a stone, you could place a small nanoparticle and then shine a light onto it, and this nanoparticle would launch also waves which would emanate from this particle. And well, before I was saying recently, but it has already been nearly 10 years since similar waves were observed in graphene in 1 atom thick, basically conductor, by means of the near field microscopy. And this is what the whole talk would be about this plasmon, these collective oscillations in graphene. But before entering into graphene plasmons, I would like to explain what are in general plasmon polaritons are. So these could be seen as electromagnetic waves whose amplitude decays exponentially in both metal and bound in dielectric, and these waves could travel along the metal surface. This is a dispersion relation of these waves, which is very simple. It contains dielectric permittivities of metal and the bound in dielectric. And very important that if you plot this dispersion relation, you see here frequency as a function of the wave vector, and you see such a curve. But additionally, of light in free space, you would see that the dispersion of plasmon is separated from the light cone. Namely, at a fixed frequency, we see that the momentum of the k vector of our plasmons is larger, which means that the wavelength of these waves are small. So this means that with the help of plasmons, we could compress light into the scale along the wavelength. Okay, but because of the losses, of course, there is also decay along the direction of the propagation. So the wave exponentially decays not only in the transversal direction, but also along its propagation. And now, since this is not just a lecture, so we are supposed to be in a school, so it's not, I thought it could be not a bad idea to give you some home assignments. And actually you could send me during the day, before tomorrow, the ones, of course, who wish. So I suggest you to try to derive by yourselves the dispersion relation of surface plasmons. And for this, you don't need much. You need basically to take the Maxwell equations, take the electric and magnetic field in the form of plane waves, and then just to match the boundary conditions these plane waves. And then you will obtain the dispersion relation, and then I suggest you plug into the dispersion relation the epsilon, which corresponds to Drude model, and then also Drude-Lorentz model. And then you try to find the asymptote of these plasmons, namely how the dispersion behaves when the k vector tends to infinity. And also I suggest that you try to find the propagation length that I mentioned in the previous pages. But tomorrow we will also have some problem solving, and we could consider a little bit this problem and derive, let's say, a leaf, and we will see how it works. So, but I would be happy if you tomorrow could join and try to share your screen drive, and then we will see which problems you have had and which problems you're having, and try to solve these problems. So plasmons have been studied for many years. Well, I should maybe say were studied for many years, because the most studies were in 90s, early 2000s. Particularly many groups, for example, group of Thomas Edison, who, by the way, got the Cayley Prize. So they were designing the so-called Hall arrays and periodic arrays of tiny holes. And these Hall arrays could support, with the help of the Hall arrays, you could excite surface plasmons. And by changing the periods of the array, you could resonantly enhance the transmission at certain wavelengths. And then you could make some color filtering, for example. Also, there was a huge interest in the plasmon waveguiding, so making some wires along which the plasmon could propagate and reflect in order to design some potentially useful optical circuits. That was basically the idea as a challenge. I think, for example, IBM is still working on the creation of optical chips. But in this case, in case of plasmons, the idea was to just to use a standard CMOS technologies to send light along the cables, the contact, metallic contact that connects semiconductor devices, because the plasmons exactly propagate along metallic surfaces or metallic wires. So there was a really intense research in the visible, let's say, optical range. But there are, of course, many other interesting bands in the spectrum of light. For example, there is the so-called mid-infrared fingerprint region, which are mid-infrared frequencies of order of 10 microns with the wavelength. And why it is interesting? Basically because at this frequency range, many molecules, and nearly all the organic molecules, have strong resonances. So they strongly interact with light at this wavelength. Also, as you might know, that the terahertz technology, which corresponds to lower energies, is also important for security and for potentially for some data transmission. But unfortunately, these ranges, with the energies lower than the visible frequencies, you cannot use plasma polaritons in metals for that. Why? Because for low frequencies, metals behave simply as mirrors. So you send the light and all the light is reflected back, because the skin layer is so small that it decays immediately and not capture these oscillations. And this is why people were looking for for alternatives and other materials. But also still they were trying to work with metallic objects. For example, by artificially structuring metallic surfaces, you could effectively reduce the dielectric permittivity of a metal. Actually, the fact that the plasmons are not supported by metallic surfaces could be seen because the electric permittivity is so large. And if you have a look at the dispersion relation, if epsilon of metal tends to infinity, you will see that there is no confinement. The wavelengths become as large as the wavelengths in free space. But by artificially structuring metallic surfaces, you could effectively reduce the electric permittivity, and the dispersion would also separate from the light cone, and then you could get the confinement, and you could manipulate light on at these terahertz and even at low frequencies. But also there are two issues. First, that the wavelength of these oscillations is still very large. So the wavelength is tens of times. And if you need really in your device to make an interferometer or enable a propagation of electromagnetic fields with several wavelengths, of course, your device increases dramatically the size of your device. So in order to reduce it, you have to reduce the wavelength. This is on the one hand. On the other hand, all these plasmons in the metal could be controlled, but they could be controlled by making a different structure. So you just have to change the geometry, have to change the shape of your artificial structures, which is of course not active and not convenient. Well, this is another example. This is how the light could be squeezed into a very small volume when you have two cables, so-called transmission lines, which is used in the television. When you get two cables very close to each other, the waves could be trapped here in between and travel. But still, the wavelength, you see the distance between red and blue oscillations is very large. And this is where Graphene comes. 2010, with the Nobel Prize. There was a huge interest light-metal interaction in graphene. And this is when the interest in graphene plasmons was renewed, because basically people learn to produce graphene in an easy way. And actually, I was going to share with you how with, for example, in Guinea center, how you could exfoliate graphene or other van der Waals materials. So this is quite an old video. This is one of the ex-PhD students. She's now a doctor. So you take Scotch tape and you place your van der Waals material on top. Okay, you place it and then you double the Scotch tape like this. And then this is when you exfoliate a part of materials. So, for example, you use a thickness by factor of 2, and you do it many times. It's not an easy work. It could take really long until you get the needed thickness. You do it many times. And then you have to, of course, characterize, for example, the thickness of graphene or whatever material. You could transfer it onto the substrate like this, and then you go to the optical, basically to the optical microscope. And in the optical microscope, they typically have the scales, the color scales. Each color corresponds to a certain thickness in thin films. And then more or less you already could get which thickness it is. But to know more precisely the thickness, you have to go to the force microscopy. Then you could really get very precise thickness. And then if you're not happy with the thickness, you repeat again until you, for example, get a monolayer. So it is foreseen that graphene could revolutionize the current technologies, or at least complement current semiconductor technologies. To, for example, to make a flexible to devices or devices. But for us, it's very interesting that graphene in the mid-infrared and ultra-high frequency ranges could support graphene plasmons. If we have a look at the conductivity, so it's a complex value, it has both imaginary and real parts. So when the imaginary part of the conductivity is positive, then in this frequency range.
Alexey, sorry, I should interrupt you. We have some noise. Maybe the sound is not perfect, very bad. Maybe you can change the position of microphone or something like this.
Well,
I don't know.
Not change the position, but I can try to. The settings are.
So sometimes
maybe I have to stop sharing, right?
I don't know. Maybe try. So sometimes sound like speeds up, and
okay,
it's difficult to understand. Mm-hmm.
So I'm trying to find the options to change.
Mm-hmm. It seems even now we have such a problem.
Okay. Option to change the device.
Mm-hmm.
Maybe here audio set with sound from my web camera.
It seems it became
Better?
Oh, now it's better. Yeah, now it's better.
So let's try to stay.
Yeah, let's continue. Thank you.
Sorry, I share again. I think which one? This one. Yes. Okay, sorry for this issue. We
in here. So basically, as the energy is smaller than a double Fermi level in graphene, this is where you could have plasmas. But as you see, by changing the Fermi energy, you could change the region where your plasmas exist. And also, by changing the Fermi energy, you could change the properties of graphene plasma. This we could see here, where I show dispersion of graphene plasma. So I said here in my book, basically because I took this from my book, you could have a look maybe to get more information. But of course, I mean, I would need to cite here many scientific groups who contributed to the discovery of graphene plasma. So I'm not doing it here, but I'm doing it in my book. So here you could see the dispersion of graphene plasmons for two different Fermi levels. As I had just said, the dispersion depends upon the Fermi level, and in graphene you could control the doping level, the so-called Fermi level, just by applying external voltage. So by applying the external voltage, you could control the dispersion of plasma polaritonals, and then you control the wavelength, the propagation length, and many other properties. You could see that compared to the light core, which is nearly the vertical line, at a fixed frequency, the momentum of graphene plasma is huge, which means that the wavelength is really short. Here we could see the snapshot of the electric field of a plasma material on a graphene sheet for two different Fermi levels compared to the half of wavelength in free space. So you see how many oscillations feed one half wavelength in free space. So these are really small scale oscillations. And because of being tunable and extremely short wavelengths, they of course are very confined. You see that they decay very quickly, and they are very sensitive to the environment, which we consider in the following. And people just were interested in this because it could lead to important applications like for sensing, for example, or for photo detection. And here I would suggest you try to solve the second task. So this is the second home assignment. I suggest you analyze and you find and analyze the dispersion of graphene plasmons. Then you could, for example, you could write it up, you could scan it and send to me, either to me or to organizers, and then they will form it. I guess you might have some bonuses for that, for these attempts. So you have to do the same that you are supposed to do for the case of plasmons on metal surfaces. You just match the plane wave above and below graphene. You match them by the boundary condition, which is a continuity of the longitudinal electric field, and there is a discontinuity of the longitudinal magnetic field, which is so it has a jump. The magnetic field has a jump, which is given by a surface current, which is proportional to the conductivity of graphene. Then you could find the dispersion relation, substitute there the Lorentz conductivity, and try to demonstrate that the frequency in this case is proportional to the square root of the momentum, which is a very typical scale for two-dimensional materials. Most important, as you see, the frequency is also strongly dependent. The frequency of plasmons, a given character, are strongly dependent upon the Fermi level. And also, I suggest you try to find the propagation length. Well, if you have some problems tomorrow, we try to do it together. By the way, because you see that there is a strong momentum mismatch between light and free space and graphene plasmons, you basically have serious difficulties in coupling to these waves. Of course, for the waves who travel in free space. Because graphene for waves in free space is homogeneous, and the momentum is conserved, and because the momentum is very difficult, because of momentum conservation, you don't have this matching. So to overcome these difficulties, there could be several methods. For example, you could use a prism, ATR, so-called attenuated total reflection geometry. This is a very similar setup that I mentioned in the beginning of my talk. So you have a critical angle upon which you don't have any more propagating waves at the exit phase of the prism, but there is an evanescent field, and if you have an oblique incidence, you could in principle match the momentum inside the prism with the momentum surface plasmas. But for that you would need a prism with very high refractive index. Maybe I mean it has not been shown until now, because these materials simply do not exist. Maybe you could use a metamaterials in the future. But I think it would be useful, at least at a low energy, for low energy waves, to couple them to graphene plasmas. Then there could be a grating coupler, so you could fabricate a grating on a substrate and then place graphene, or you could directly make nanostructure of graphene. And then when a wave is incident on such a grating, it generates an infinite set of field harmonics, and some of these harmonics could match the momentum of the surface plasma. Then you could use simply a point emitter, actually any defect, because any defect breaks the translational symmetry, and then it generates a continuum of momenta. And of course, one of these momenta, which I call delta K, one of these momenta could match the momentum of the graphene plasma, and it will emanate. If you remember, I was showing this example with a nanoparticle which could be illuminated by laser beam, and it launches plasmas. Then you could use metallic antenna. This is what we will consider in the next section. So you could capture light by metallic antenna, and then because of the scattering at the edges, it could also gain the needed momentum, like in case of point scattering, but here you have an edge. And then it could launch graphene plasmas. You could also capture graphene inside of the so-called plasmonic cavities, which are basically not cavities but resonators, because you could lock the oscillations because of reflections back and forth. So this reflection form the so-called Fabric-Mirror modes, and then you could illuminate again this resonator, and because of the scattering at the edge, this wave would be excited. And then there is a very exotic way that we suggested of coupling to graphene plasmas, that you could start with the standard waveguide, and then you could compress, you could say make a tapering, and then by making tapering, you could adiabatically reduce the wavelength until it matches with graphene plasmas. So let's go to the next section, which is launching and control of plasmas with metallic antennas. Later on, after each section, we will make it very small. We'll try to make a small pause to see whether you have posted some questions. You could do it during the talk, and then I will address this question in a few minutes before going to the next session. Okay, so what are in general optical antennas? And actually, we can consider first radio wave antennas, because light is nothing else than electromagnetic oscillation, just of higher energy than radio waves. So the simplest antenna is just a dipole antenna, which could be actually a piece of cable, metallic cable. If this cable, the length of this cable matches the half of the wavelength of light in free space, it could create Fabric-Mirror resonances, because this wave reflects back and forth from the edge of this wire. And then you could convert these electromagnetic waves into electric current. This is what radio wave antennas do. Of course, in case of radio waves, these antennas are huge. These antennas have huge dimensions. So we took this concept and we decided to use much smaller metallic, let's say, wires or resonators, which look like metallic rods, okay, with a few microns of length. Actually, if you take a human hair, you could cover the whole hair with this antenna, because they're really, really small compared to human hair. So what these antennas are doing, actually, they support plasmons, although they are not very confined. So the plasma has the wavelength, roughly the same wavelength as light in free space. And this plasma could be captured here because of reflection back and forth. And it creates the so-called dipole resonance. You see Here you could represent either charge, electric charge, or electric field. You see that at the apexes it has intense spots of opposite polarities. This is an indication of the dipole resonance. So we decided to use this concept to convert electromagnetic waves into graphene plasmons. And then we wanted to image these plasmons with the help of optical microscope, which I will say a few words only because you will have a lecture of Pablo Alonso, and I promise him I will not say a word, but something I need to explain. Okay, so first, before going to experiments, we of course simulated very carefully because we wanted to make sure that we will get a reasonable result. So here I present you the comparison for the excitation of an optical antenna and then optical antenna placed on a graphene sheet. So in case when an optical antenna is without graphene is placed on a substrate, let's say transparent calcium fluoride substrate, but it could be any other dielectric, then you shine light onto it and you create the dipole resonance. If you plot the field enhancement or just the field, you could average the field across the area of the antenna, and then you plot it as a function of the antenna length. So you see that you have a typical resonant shape with a clear maximum, which more or less matches the half of the wavelength of the plasma propagating along this road. And importantly, when you Fourier transform this field, you see, basically because of the edges of this antenna, you see that the Fourier transform extends to really high momentum values. Here the momentum is normalized to the momentum in free space. We could reach really high values. This is why we thought that, of course, you could couple to graphene plasmons. So you eliminate now this antenna placed on top graphene, and if you calculate the electric field, while on the antenna surface it is still very similar, it shows the dipole resonance. Around the antenna, the pattern is completely different. So you see waves emanating from the antenna, which is actually the proof that the antenna could launch plasmons. Then if you calculate the field on top of the antenna as a function of length, well, they're not compared on the same figure, but I can tell you that as the resonance widens, it gets broader because you have a source of losses, because energy is lost by going into surface plasmons. By going into graphene plasmons, and also graphene is also lossy. So there are ohmic losses, and this is why your resonance curve gets wider. And there is also redshift. But most importantly now, if you Fourier transform this field pattern, you still could recognize the Fourier transform of your antenna, but there is a clear circle here. So this circle is nothing else but the isofrequency surface or isofrequency curve of our plasmons. What is the isofrequency curve? It's just our dispersion in general is a surface in four-dimensional space, because you have a frequency or energy and three components of the wave vector. But you could cut this four-dimensional surface, and the cut, for example, the fixed frequency would correspond or would give you the isofrequency surface. And in this case, since we only consider the propagation in one direction, we have a curve which is given by a circle. So once we were sure that in the numerical simulation the concept works, we made the experiments, and then we tried to image it with the S-norm. So the S-norm basically uses a tip, either metallic or dielectric tip. Then this tip is illuminated by a laser beam, and then it could concentrate light below the apex and strongly enhance light-matter interaction. And as well, it could enhance the resolution, because in this case, the resolution is limited by the radius of the curvature of the tip. In this case, we on purpose used the dielectric tip because we wanted, this is actually the experiment performed by Pablo Alonso in Guinea. So we wanted to reduce the scattering, and we wanted to reduce the disturbance that the tip introduces into the system. So we wanted to eliminate the antenna, and then the tip only scatters the created electromagnetic field, but not launches anything by itself. Okay, so we fabricated a set of an array of antennas of different dimensions, more or less of 7 micron length, and then we observe clearly what is expected from the numeric simulation. So you could see the compression for the same wavelengths. There are 2 different wavelengths, and you clearly see how graphene plasmons emanate from the antenna. Also, it's very interesting that this antenna, for example, is longer than this one, and it's nearly in resonance. This is why the fields are very intense. While this antenna launches the plasmons as well, but the efficiency is very small, so that these plasmons could not even be captured by a near-field microscope. So it's important to tune the lens so that you get the resonance in order to efficiently achieve the launching of the plasmons. But then, changing the wavelength, the illuminating wavelength, you could calculate the distance between the fringes of the opposite polarity, for example, between the red and blue fringes, and this would be the wavelength, and the inverse wavelength is a momentum. And then from these images, you could reconstruct the dispersion of graphene plasmons. But we were very curious about the following fact. If you have a look at the wavefront, you see that the first fringe, actually this is even better seen in the experiment, the color of the first fringe matches the color of the antenna area. Okay, so which means nothing else but that the plasmon is lodged with the same phase that the antenna has at the edge. And then we thought, okay, if it has the same phase, now we can shape the antenna and we can, in this way, shape the wavefronts. Then, actually, maybe you have already noticed, we on purpose made the apexes of the antenna of the rod with some curvature, both convex and concave. Here you could see it better. Okay. So, and indeed, in the convex apex, you see that you have divergent wavefronts. But if you make the apex concave, then you see it has an effect like a parabolic antenna. It focuses your plasmon into a spot. So, and for example, if we monitor the intensity along this line, which is nothing else but the line of the same phase for graphene plasmons, you see a substantial increase in the intensity. So by this we demonstrated that you could achieve focusing of graphene plasmon by shaping metallic antennas. But then we also noticed that there was a piece of a second graphene layer close to the antenna. So it's like there was a region of graphene bilayer. Again, graphene bilayer has a different refractive index or different conductivity compared to monolayer. And this different conductivity for plasmon, it is nothing else but the different refractive index. So this bilayer in principle should work as a prism. And indeed, we had a careful look onto the images in the near-field microscope, and we saw that the wavefronts inside and outside of the prism are bended. Actually, if you make a careful measurement of the angle, it more or less matches the Snell's law. So we got some comments from some people that say that this is very easy. I mean, this is a Snell's law. This is so trivial. And I completely agree with this, that this is really trivial optics, basic concept. But we are doing it now. Just think of it. We are doing it in a one monolayer, in a material which is a one monolayer. So we observe the Snell's law on a one atomic thick layer. So if now you have posted some questions, I can try to address. But if not, we just continue. So I don't know. Did we get?
I don't see the question, so I think we should continue.
Okay, let's go. Then I try to leave some time at the end. And
yeah, maybe we'll ask in the end all the questions.
Okay, thank you. So we now will see how one can capture and excite plasmons inside graphene nanoresonators, or you could also call them graphene cavities. So basically, we got this idea because the very first observation of graphene plasmons was done not by means of near-field microscopy, but by means of exactly resonators. So there was a group which fabricated arrays of graphene ribbons of different widths, and these graphene ribbons were gated. So one could apply external voltage and control the Fermi level of the charge carriers in these graphene ribbons. And the observation of the resonant excitation of graphene plasmons was observed. Clearly, the resonance position, you could see changes with the change of the width of the ribbon, but also it changes when you apply voltage. So you move your resonance with the voltage. And actually, this concept was used. I'm advertising the work by Graphene Bajo and Atichu Altuk, a fantastic work, which motivated us actually to make a related research in this direction. So they applied the concept of having plasmons in graphene ribbons already for very practical applications, mainly for sensing of some organic materials. So if you place a polymer on top of or any other organic materials which have a strong resonance, and then by tuning Fermi level, you could match the resonance of graphene plasmons with the resonance of a molecule, and then you could obtain the funnel profile. I will explain you later what it means, the funnel profile. This is very important for the funnel. So you could see that there is a fancy shape of this resonance, but then you could there are methods of disentangling this resonance from the funnel shape. Then you could obtain the so-called molecular fingerprint, which is a spectrum of a molecule. So by graphene ribbon, you could enhance the fingerprint, because if you would try to shine light directly on the molecules, you don't get much, especially if you have a very tiny amount of these molecules. And why this concept works? Well, because graphene plasmons are so confined, the electromagnetic field decays so quickly from the surface, from graphene, that it is very sensitive to even tiny variations of dielectric index. And of course, if you have a resonant excitation of molecules, the refractive index of the molecules is strongly frequency dependent. And this is why you clearly see this fingerprint on top of the graphene resonance. So we wanted, our idea was to make one step forward and to try to even to reduce the sizes of such kind of structures, namely to make nano-resonators, which would be not long, but also very short, like for example circles or small squares. And then our idea was to try to observe the resonances with the help of external optical antenna, which could be, as a proof of principle, an optical microscope. So that was basically the motivation. And we used the optical microscope in the so-called polaritonic echo detection, or it is also called polaritonic interferometry. How it works? So you take your tip, you illuminate it with a laser beam, then you generate here a hot spot with high momenta, and this momenta launch, tip launches the plasmons which emanate as cylindrical waves, like a wave on the surface of water when it's restored. So they emanate from the tip. Then, if there is an edge, of course you could always put the tip close to the edge or close to some depth. Then this wave would reflect back and it will travel to the tip. Okay, and then you have strong interference between the launched plasma and reflected. And then your tip is positioned inside of this strongly interferent field. And then the signal from the tip is scattered back into the detector. This is the same principle as some animals use. For example, bats, they emit sound waves, and this sound wave reflects from an object, and then the bat could recognize the distance, can know the distance to the object very precisely. So now, if we make the same with graphene, for example, we could scan a graphene ribbon. Okay, that it was one of the first experiments and the optical imaging of graphene plasma. You just place the tip on top of graphene and you move it. You move it around, and then you record this called near field image. And you see very bright edges, and then there are stripes, bright stripes, which appear, which are parallel to the edges. But these stripes indicate nothing else but your standing wave, which you capture in your near field microscope. And by measuring the distance between the bright stripes, you could know the wavelength of your plasmas, and you could recalculate the wavelength into the K vector, and you could get the dispersion. So we applied, sorry, this slide is super overloaded, but I will explain you slowly. Okay, because it includes both experiment and theory. We fabricated an array of small disks with diameters ranging from 15 to a half of a micron, and we just imaged these disks by the S1. Okay, as before, as I was showing for the graphene ribbon. And we saw really a set of very puzzling contrast here. So actually we thought, oh my gosh, what the hell is that? Because look here, there are some black disks, then they start to be bright in the center, right? But then again dark. Then you have this dark ring with some dots. So we were really confused about these near field images. But we had to understand them. So to analyze, we just plotted the amplitude of the near field signal as a function of the disk diameter. We took 2 points at the center of the disk and at the very edge. And you see that when you carefully plot the data, you immediately recognize that, okay, there is a resonance. There's a clear resonance in the center of the disk. But now if you do the same on the edge, you also see kind of weird resonance, but this is shifted. Okay, so then we realize, okay, there should be many resonances actually. So these disks should be multi-resonance structure. So there should be many electromagnetic modes which mix, and this image is just the result of the interference between these modes. Then we built up a very simple model. So we just replaced the tip by dipole solvers, and we were taking the near field below the dipole generated by this dipole above the disk. And then we were able to nearly perfectly reproduce the experimental data. And then by plotting the signal as a function of the disk diameter, we see that more or less the resonances match. Okay, here you see more resonances, just because in the microscope it's difficult to capture because the intensity is small. But okay, to go one step further, we also looked at the field snapshots for different disks, and actually also changing the frequency. And here we indeed realized that there are many modes, and actually we could classify these resonant modes into 2 different categories, which are very different. The first one corresponds to the so-called edge modes, and the other category is the breathing modes. So the breathing modes have the electromagnetic field extended along the whole surface of the disk, while the edge modes are localized along the border of the disk. You could draw an analogy between these modes. For example, these could be seen, these edge modes could be seen as a whisper gallery resonances, which are very known. For example, in the St. Paulo's Cathedral, you could hear people staying at the opposite side, okay, because of this interference. And breathing modes are very similar to those which occur in the drum. So then we more or less understood what was going on with this resonator, but still it was very puzzling for us. These dark features, because just think about that, you have strong resonant modes. So what you know that the field is very strong, and you expect that in your microscope you also should have very bright signatures. But we saw dark instead. We saw dark spot. Actually, first we saw that there were some fabrication defects. The graphene here was damaged, or something was going on in some disks. But then we had a look into the previous papers, where the images of nano ribbons were reported, and actually here they already appear to be dark. So we thought, what could it be? Fortunately, my PhD thesis was dedicated to the so-called wood anomalies, and then I remembered, okay, somewhere I saw a very similar thing. And actually, I saw it in one of the oldest Wood's papers. Actually, this is an amazing person, Robert William Wood. I recommend to read the biography of this person. Very extraordinary. He was doing the experiment in the shed, where in the village where he spent his summers. He had a very long spectrometer, which actually he cleaned by pushing a cat inside. Also, I think this guy had as a lab table, he had a pump, okay, with this resin plastic. So that was his experimental tape. Very extraordinary person. And in his paper, he reported, so he was studying, he was interested in diffraction ratings, actually with the application in astronomy. He was doing this metallic diffraction grating, which just transformed the incident beam into many diffraction orders. And then he was presenting, this is just a snapshot of well, from one of his papers, one of the figures. This is a spectra, okay, from the diffraction grating. And in this spectra, you see a really similar pattern feature. It's like a dark reading followed by a bright one. So I thought it should be, although this is a very different structure, the concept should be somewhere there. And by the way, to explain these anomalies, the experiment was done and was reported in 1902. It took tens of years for physicists of that period, okay? Because many people try to address these spectra, including Rayleigh. Lord Rayleigh was trying to explain why would observe this dark and bright feature, but he could not. Okay, he just explained some sharp feature which the spectra had, but not this anomaly. And then it took nearly 30 years for people to understand what was going on, and that was Italian physicist Ugo Fano. We know, you might know Ugo Fano because he's very famous of his work on inelastic scattering of electrons from helium when he reported the asymmetric resonant line shape. But actually, earlier before, he managed to explain wood anomalies. This work was done completely, they're totally independent, but finally, the physics is very similar. And actually, you could find a very good report written by Yuri Kishan and the rest. So you could explain this wood anomaly or any Fano shape as a mixture between a resonant, narrow resonant process and a continuum. If you have an interacting system which has two different spectral behaviors, like a continuum spectrum and sharp resonant feature, if you observe simultaneously these two systems or a mixed system, then you see this asymmetric Fano resonance. So how it works in our case? If we position our microscope tip far away from the graphene disk, then you would observe like a very smooth background signal because you don't have any resonance, it's a normal dielectric, so I have like a nearly constant. Now, if you place your tip on top of your resonator, then you excite one of the nodes, you have resonance field. Then, of course, still you have below, you have the dielectric, and you have that signal, you have to sum up. But if you just sum up these two signals, you would not get an asymmetric shape. Why? Well, because the electromagnetic fields could be described with the help of complex numbers, so they're complex amplitudes. They're described by the complex amplitudes and complex numbers. This is why you have to sum up complex numbers. And if you take the phase of this complex number of the amplitude of your resonant mode, close to the resonance, it changes quite strongly. Okay, the phase changes very quickly. This you could also see by considering just a harmonic oscillator. Just take from the textbook the equation for the harmonic oscillator and plot the amplitude and phase. And this is what you will see. The phase changes quickly. So we have to take into account the phase very carefully, and we have to sum up the complex amplitude. Once you sum up the complex amplitude, so you get it. You see the asymmetric shape. This is the background signal, and you see the dark part, and then followed by the bright signal. You could also see it by vectoral diagrams. For example, in the case when you have a bright maxima, or in general when you have the frequency of the maxima, you have the background field and the resonance. You see the phase is not large, so the phase is very close to, let's say, 0. And this is why this arrow is close to the x-axis, and then these two signals enhance each other, and you have an enhancement. But now, if we move to lower frequencies, so we move here, where the phase is large, your resonant field is rotated strongly, because the phase corresponds to this angle. Okay, in this representation, the phase is given by an angle at which the vector is rotated. So once the vector is rotated, then your total signal decreases, and this is why you see these dark features. When we realized that our observations were nothing else but the Fano profiles in real space. This is a superposition of modes with a background field, which you could explain by Fano interference. And it turns to be that in case of edge modes, the phase is always large, so that you see negative contrast. And then we also made a study of a rectangular resonators. Actually, this is how we started. First, we fabricated. I mean, the story flows better when I talk about the days. But first, we measured these guys, and we were completely confused about everything. So we were complaining to Graphene, saying that the samples are not good, Graphene is not good, because it has dirt at the edges, so the quality is not appropriate for us. But then, once we got the modeling with the dipole, we could reproduce nearly perfectly these features, these dark spots, and then we thought, okay, this is not dirt, this is really optical phenomenon. And now we know that this is the Fano interference. And here we nicely managed to disentangle different modes, so we could know the contribution of each mode to this near-field image. And by the way, here you could see multi-feature. You see a small feature of the edge mode. So this is resonating edge mode with the mode volume being 100 millions of times smaller than the volume of one cube of wavelengths in free space. Let's say than the volume of light in free space. So it's a minute field concentration, and of course, maybe in the future it could be used for coupling with individual molecules or with very tiny amount of molecules, where you could dramatically enhance that net interaction. So let's go to the final part, which would be more applied, but well, also I will explain some interesting physics, but that was more like already applied, more applied concept to build the photodetector. So in collaboration with many scientific groups, including Frank Coppens from England, Werner Hillenbrand, we were studying the encapsulated graphene. So you know that graphene shows much better properties, much better mobility when it is encapsulated in between the two polar layers of van der Waals material boron nitride. So for this reason, we used this encapsulated graphene to get more mobility. And then in ICFO, they fabricated the so-called split gate device. So there is a gate below the graphene, but which is just cut, so that you could apply here and here different voltages. And then you place your tip on top, your microscope tip, which could be an antenna. Actually, the future vision of this, instead of your microscope tip, you place a real antenna there. And this antenna creates, as you remember, at the edges, metallic antenna, for example, creates at the edges intense electromagnetic fields, which are also called hotspot. And this hotspot would increase the temperature, local temperature of graphene. Okay, and when you increase the temperature of graphene, it's like you increase the temperature of air, you have a flow of air. So if you have also apart from having a non-local temperature distribution, you have initial disbalanced distribution between the charges. These two effects multiply together, actually. You see the gradient of the temperature multiplied by the Seebeck coefficient. It could produce electric current. So the charge carriers start flowing, and then you could capture them here by just connecting electrodes into the device. That was the idea, just to try to image this device and to observe the photothermoelectric phenomena here. So if we apply different voltages, we could create the artificial pin junction here to have more holes, and here to have more electrons. And then by generating the temperature profile, by heating it, you see that the maximum, when the tip is positioned just at the center of the pin junction, you have this distribution. This is a derivative which enters this integral. Okay, then you just, and this is a Seebeck coefficient, which is proportional to charge carrier concentration. You just multiply this by this, you integrate, and you get that your device should have the maximum electric current when your tip is positioned exactly above the pin junction. And this is what was observed exactly. So this is the photocurrent map. Each point on this map corresponds to the position of the tip at this point. So we just scanned the tip like this and this and this. And when it was positioned at the center of the pin junction, we saw the maximum signal. Okay, but now if we move close to the edge of the graphene, we could see these oscillations in the photocurrent. So these oscillations are very similar to optical experiments. When we saw this interferometry, you remember this bed emitting a wave, and then this wave reflects back from the fly, and the bed could know the distance. So this is the same, but now we measure the photocurrent instead of electromagnetic field. So in other words, your tip, it hits graphene locally, but it also launches the plasmons as before. Once it launches the plasmons propagate towards the edge, they get reflected back, and of course it creates an interfering field pattern, and this pattern modifies your temperature distribution. And this is what you see. You see the modification of your temperature gradient. But then we thought, okay, we could image this. We could get these maps at different frequencies or different wavelengths of the illuminated laser. This is experiment at terahertz frequency, because there is another paper which was done also for mid-infrared frequency range, very similar observation was done. But then we try to extract the dispersion of plasma polaritrons in this device. Okay, so you just take the profile of the photocurrent. Then here you see oscillations at different frequencies. So for each frequency you would get its own map. Then you take the profile somewhere, and you measure the distance between the maxima, which should roughly correspond to the half of the wavelength of your plasma. And then you could plot the dispersion. So once we plot the dispersion, it was completely linear, and that was very positive, because we knew that actually that is one of your home assignments, to show that the dispersion of plasma should be proportional to the square root. So the frequency is proportional to the square root, but here it was completely linear. So what was going on here? Actually, you see that the confinement could reach, or much higher than the confinement that you could reach with standard, let's say, freestanding graphene or encapsulated graphene at a fixed frequency. Actually, the light cone here is near the y-axis. So you don't see the dispersion of waves in free space because the momentum is negligible. Okay, so but these are let's say conventional plasmons, and these are plasmons in our device, which are much more confined. So the physics is the following. Actually, you could see it here if you in the simulation place a point dipole on top of a graphene, on top of graphene which stays above a gate, above a metallic pad. So you see that the field is very concentrated. It's in micrometers, 30 micrometers, while wavelength of terahertz light is 100 of microns. So here we have 30. The wavelength is of the order of 10 microns. Okay, so you have a good compression. But if you place it on top of a metal, look, you increase the compression by a factor of 10. So it gets compressed 10 times. But why is it happening? Well, because if you place graphene above the metal, you might remember that I mentioned that at low frequencies, metals for light behave as mirrors. So if you place a graphene, you could see it like this. You place graphene above a mirror, but actually if you have a mirror, so you have an image. Okay, so it's like the graphene layer would be also below the mirror. But according to there is actually one of the methods of the solution of electromagnetic problems, which is the imaging methods. The electrostatic is used, for example. So you place a charge. If you have a mirror, you have the opposite charge at the same distance below the mirror, and then you could remove the mirror and you stay with these two charges. The same happens in the case of graphene. You place graphene above the mirror, then you could remove the mirror and say, I have another layer here, which is charged oppositely. Okay, but so it's like a bilayer graphene then. And we know that in bilayer graphene, there are two types of modes, acoustic and optical modes. Why two types? Because initially you have a mode in one sheet of graphene, and now you have another one, which also have one mode. You get them closer, they overlap, like wave functions and quantum mechanics of two particles. Imagine if two particles overlap with the probability functions. Okay, then of course you have a splitting in energy. The degenerated state splits, the degeneration is removed, and you have two new states. The same happens here instead of one plasmonic modes, because of the degeneration. You get two different modes. One is optical plasmon, this is called optical mode, and another one is acoustic. So this one corresponds to the acoustic mode, which means that the field oscillates mainly perpendicularly to the propagation direction. And the field of the acoustic mode is concentrated in between of graphene and metal. You see the intensity is huge. So all the field is squeezed into that nanometric gap. And then the dispersion becomes linear in this case. And by the way, then later on we de-apply this constant that I will mention. So instead of a tip, we fabricated the antenna, which was like a dipolar, classical dipolar antenna, which are two metal rods, and in between of two metal rods you have strong field enhancement. And this strong field enhancement increases the temperature of your of graphene placed above the antenna, and also you could use the same antenna to gate, because you could connect cables here and here, wires to the antenna, and apply different voltages, and then this antenna plays a role of gating device as well. So it heats the graphene because of hotspot, but it also gates. And then by gating it in such a way that you create the pin junction, then you could generate the photocurrent. And this detector, this is the view of this detector. So this is antenna, okay, with the connected wires. This is how you gate it here. And these are contacts to the graphene just to take the photo color. And then we managed to resolve, for example, a beam. And the terrestrial beam by moving antenna in the vicinity of this created beam. And as a future vision, let's say, it would be really interesting to combine now the sensing technology that I mentioned initially that was done for ribbons with these thermoelectric devices. Actually, we tried theoretically to see what is going on when you place your graphene resonators on top of a metal gate. Then, as I explained, instead of normal plasma, you have acoustic plasma. And if you are trying to image, for example, a protein, for example, let's take a protein with this dielectric function. This is the real and imaginary part of the dielectric permittivity as a function of frequency. You see a fingerprint on this protein. Okay, and if you try to image with a microscope, to take the spectrum, the near-field microscope, from this small amount of protein with a, let's say, with a disk of a diameter of, I don't know, 50 nanometers, and with a thickness of a couple of nanometers, you nearly get nothing. You don't see it. But then if you place this protein on top of a graphene disk, you enhance your signal, as was already shown for the graphene ribbons covered with organic materials. But now, if you place your organic materials in the spacer between graphene and the metal part, you dramatically enhance the visibility. So you could recognize the fingerprint of really tiny amount of molecules, which even with normal graphene resonator you cannot do. And actually this concept was later on demonstrated experimentally by two independent groups. There was an array of graphene ribbons above metal parts, or the opposite graphene, array of metallic ribbons below the graphene. Okay, and then these two groups placed some material in between on graphene and metal. In case of IFOS group, that was the boron nitride, and then you could clearly see the signature of phonons in the boron nitride with a thickness of a few nanometers. I think even 1 nanometers or less. But here, the US, the group in the US, by the Simon Och and Tony Ball, they just placed a silk, 0.8 nanometer of silk in between, and clearly could observe the fingerprint in such resonators. And then we also suggested the concept when instead of probing the waves in the resonators, you could actually probe the traveling waves. This is what I mentioned at the beginning of my talk, that maybe in some applications you need that your wave travels several wavelengths. This is where you need a strong confinement. So this is one of the examples. We wanted to capture the signatures of the fingerprints of the molecules just from the experiment where we launched propagating plasma. Okay, and actually this is, we have an experimental paper, but I will show you this theoretical paper. So you launch a plasma from a tip, it propagates to a small piece of small volume of molecules, reflects back, and then you could recognize this, these are CBP molecules. You could in the reflected signal, you could recognize this fingerprint. But if you now place a graphene on top of a metal part, and actually if you even make a tapering, then when this plasma propagates, it starts as a normal plasma, but then when it enters the volume, it becomes compressed because your wavelength gets adiabatically compressed. It's the smallest here. So all the electromagnetic energy enters here, because when graphene is not placed above the metal, you only hit the volume of molecules by some portion of graphene plasma. But here, you completely pass the plasma through this volume and it gets reflected back, and then in the reflected signal, the visibility of the peak is much stronger. So this could, in the future, maybe lead into the optoelectronic devices for sensing, where you could combine all the concepts that I have explained, with the photothermoelectric effect with the high sensitivity of graphene plasmons. So in today's lectures, we have seen graphene as a promising material for surveillance, control of light, of electromagnetic waves, particularly in near-infrared and terahertz frequency ranges. Then I hope I convince you that metallic antennas are very good for launching plasmons, and because they could resonantly enhance electromagnetic fields. They have edges, and because of these edges, they can transfer the necessary momentum to launch the plasmons. Then one also could achieve resonances in small patches of graphene, small circles or small rectangles or squares, and hopefully use them for sensing in the future. And then I demonstrated to you that the graphene could be used for photo detection and for sensing. And if you want to work with us, just contact me. If you want to make a PhD thesis, for example, in San Sebastian, related to light matter interaction in low dimensions, please write me. Also, you could send me the homework assignments if you have time this afternoon, and tomorrow I will be happy to solve some interesting problem for you. Okay, thank you very much for your attention.
Thank you, Alexey, for very exciting and consistent talk. So we have some questions. So the first question is by Deepak Kumar. What is the difference in plasmon excitation process if we design a graphene antenna in one case and a metal antenna on graphene in second case?
Yeah, the main difference is that the graphene is only 1 atom thick, so the volume is negligible compared to a piece of metal. So it's just that you get much stronger field enhancement by the metallic antenna. This is why always the efficiency would be much stronger if you use metallic nanostructures or microstructures to launch the plasma, just the intensity is stronger. But maybe you want to reduce the size of the device, and that then you will, of course, lose the efficiency.
Mm-hmm. Okay, thank you. Another question is by Tatiana Ivanova. Is it possible to create heterostructure with encapsulated TMD, transition metal dichalcogenate, on the top of graphene with antenna and got new hybrid light matter state like exciton plasmon?
Well, I guess, well, I'm not a fabrication person, but seeing how it has progressed recently, I don't see much limitation in putting two different monolith materials together. But of course, I mean, you would need to make sure that your excitons and your plasmons coexist. Let's say they're within the same energy bands. If you want to create a kind of mixed state, I don't know for what you would need it, but I think it is possible, at least theoretically.
Mm-hmm. Thank you. Another question from Ilya Gorbenko. Is there already existing companies that use graphene plasmons?
I would say, well, in ICFA, there is this should be the question addressed to Frank Coppens. I think in ICFA they have the company, but I'm not sure whether they are already working with the detectors in million-infrared and terahertz. I think they are working mainly in the visible, where the plasmons do not exist. I would say at the moment there are no companies exploring, but they might appear in the near future.
Okay, thank you. Hopefully. Again, the question from Ilya: what are the main equations used to describe the mentioned results?
Well, you could just take the Maxwell's equations.
Maxwell. Yeah.
You could actually Google on the internet, but it's better if you try to make by yourself. I mean, you could take my slides. I think I wrote the needed equation there. I will try to send you the presentation so you could see which equations to use.
Okay, we have also the question, Maxim Mazanov, it is quite long, so I will try now to copy it into our Zoom chat. There should be maybe, I will read it now, but also copy to you. So, bearing here in mind the very small wavelengths of plasmons, it is also interesting if any materials exist which host short wavelengths magnetoplasmons, like monolayer sheets of some magnetic materials. If so, do you think it will be possible to excite the short wavelength modes by magnetic dipoles then?
Well, you would actually magnetize graphene itself. I mean, to make it here, you need a couple of Tesla magnets with a couple of Tesla, and you place it on top, and you already have magnetoplasm. Other materials, well, I haven't worked much on that, cannot tell about other materials. And excite, I mean, even to excite magnetoplasms, you could use an electric dipole. You don't necessarily need a magnetic dipole. You could perfectly match with that because this excitation, they have strong electric field as well. So you would excite, for example, standard near field microscope.
And also, as far as I know, so at the interface between metal and the electric, only TM plasmon exists because in optics it's quite difficult to realize media with different permeability, where one is negative. But with graphene, you can do T plasmon very easy due to conductivity, and it would be excited maybe by some magnetic-like dipole.
Yeah, well, this is true on one hand, but on the other hand, these TU plasmons, they are so close to the light cone that the wavelength is nearly the same as in free space.
Okay, maybe it will be more clear after tomorrow practical classes. Okay, another question from Idris Abu Hasbas. Sorry for the maybe spelling. Can SPP exist at the interface separating graphene and Kerr-type medium?
And which type?
Kerr.
I think so. That would be non-linear, right? This is what the question is about. I think people even already consider this theoretically. Well, not only theoretically, there is also a paper, I think, in Nature Nanotechnology, where they showed how one can convert the infrared pulses into terahertz because of the nonlinear processes, nonlinear interaction of graphene plasmons, because of the nonlinear media where the graphene is embedded. You could Google it, telecom and terahertz and graphene, you will find this paper.
Yeah, thank you. I think that's all question to date. So let's thank the speaker again. And now we will have a break. And the poster session will start in about 20 minutes. Yeah, so.
Okay, thank you very much. Hope to see you tomorrow. See you. Bye-bye.
Bye, thank you.
Sorry, I can't hear you. Okay.
Hello, yeah.
Hello.
Can you hear me now?
Yes, I can hear you now, but I feel like we are a little bit late with some of the voices. So
Some delay? Okay.
yeah, I heard my voice like 2 minutes delayed. So.
Oh, really?
But yes. Oh, I think it's okay now. So.
Okay. I tried to switch off my mic and okay. Now it should be better. Now it should be better. Could you confirm, please, that everything is okay? Is my voice?
Yes, it's okay.
Mm-hmm. So, guys, we have to start in 1 minute. Let me briefly remind you that this is poster session arranged in the format of elevator pitch. It means that only 5 minutes for talk and 1 minute for questions. Try to be short asking the questions and try to be short answering these questions. Okay, guys, so it's only one minute. So, and if your talk will be longer, I will have to interrupt you. So I'm very sorry in advance. So try to be in a time schedule. Okay, guys. So let's start. So the first speaker is Evelina Danuta Novak from Poland, from University of Poznan University of Technology, and his talk will be devoted to the influence on doping on the zinc oxide structures. So Evelina, the stage is yours. Could you share your screen, please?
Okay, so thank you very much. I will show my screen. Okay, so I am Evelina, and I will talk about the influence on doping on zinc oxide structures. So I will start with some words about zinc oxide. Zinc oxide is a second 6 group semiconductor, which preferably crystallizes to wurtzite structure. And as this type of material, it exhibits energy band gap that equals 3.4 electron volts in room temperature. And due to this direct band gap, it is considered as one of the wide band gap semiconductors. Although with the special doping, we are able to fine-tune the energy band gap. One of the biggest issue with zinc oxide and also with other wide band gap semiconductor are their native defects that create a special type of conduction. In a case of zinc oxide, we have a lot of oxygen vacancies that creates a lot of excess electrons, and zinc oxide exhibits n-type conduction. So we can try to change the conduction type with also with special doping. And one of the best materials are 1B group elements. But why do we even need to create p-dope zinc oxide? So when we want to use our material as a semiconductor, we want to create some kind of junctions. And to create junctions, we need to have N-type and P-type conduction material. In my case, I've decided to use a very easy way of preparation of my material, which is social method. If you are interested, you can check the links below. Also, I've decided to use copper as a doping because copper exhibits a similar atomic radius to zinc. So, going to my results, after the preparation of material with different concentration of copper, I've decided to check my structure using XRD method and Raman spectroscopy. And I decided to show you Raman spectroscopy because it gave me very prominent peaks correlated with copper oxide, and also I could saw the shifting of zinc oxide most prominent band. So as you may assume, the copper is in our samples. So I thought at the beginning that I should show some trend of changing of optical band gap. Unfortunately, there was no trend, although there was some correlation with this optical band gap with with some different structure that created due to the copper contamination. If you are more interested, you can email me. I will tell you more about it. Also, on a photoluminescence, I saw beside suppression and redshifting of the main peak with increasing contamination of copper, I could saw the changing, the suppression of oxygen interstitial peaks with the increasing concentration of carbon. And also I could saw some very small peaks correlated with copper defects. So as you may see, the influence of copper is noticeable. If you are more interested, you can just email me or don't hesitate to ask more questions. So thank you very much.
Thank you, Evelina. Perfect timing. I don't see any questions in the chat.
Concentration. And also, I saw some very small peaks correlated with... Sorry, I don't know why I hear my voice once again.
I see. Yes, me too. For some reason. I'm very sorry.
If you are more interested, you can just email me or don't hesitate to ask more questions. So thank you very much.
For some reason, I also I tried to fix this.
Concentration. And also, I saw some very small peaks correlated with... Sorry, I don't know why I hear my voice. Okay, it should be better. Sorry.
Yeah, I'm very sorry. Maybe now it's better. There are no questions in the chat, but I have a question from my side. Usually, aluminium is used for doping zinc oxide to have some transparent conductors. And what's the advantage by doping with copper? And the first question. Second question, do you have in mind some maybe possible application of your material? For what purpose would you doing this research?
Okay, so at the beginning, I've decided to, I chose copper mostly because I wanted to achieve P-type conduction, but it was very hard. So I wanted to check if it is possible to reduce amount of free electrons in my material. regarding future usage in junctions. My material is not a typical, will not be used as a transparent electrode, because for a transparent electrode for doping, I should use some different materials such as aluminum that will give me more of free electrons to my material. Although I had, due to the specific of my material, it is a kind of polycrystalline material, I was unable to prepare a very good measurements using Hall method. I've used a Van Pov method to check my conduction type. Unfortunately, in my case, it was very hard.
Answering the questions. Try to be short answering the question.
Oh, sorry.
Okay, try to be short answering the questions, because we have not much time.
Okay, so as I said, I wanted to check if it's possible to create P-type material, and yeah, that's all.
Okay. Thank you very much, Evelina. So,
thank you.
So next talk will be given by Javier Taboada Gutierrez from Spain, University of Oviedo. His talk will be devoted to broad spectral tuning of ultra-loss polariton and van der Waals crystals by interaction. So please, the stage is yours.
Hello, can you hear me?
Yes.
Okay. So hello, thanks, Mr. Chairman, for the introduction. So yes, my name is Javier Taboada Gutierrez. I'm a PhD student at University of Oviedo, and today I'm going to present you my work called Broad Spectral Tuning of Ultra-Low Loss Polaritons in a van der Waals crystal by intercalation. So, as you may know, phonon polaritons are the infrared counterpart of plasmon polaritons, which arise from the collective oscillations of the crystal lattice, and they can be excited in narrow infrared spectral range called Röstralen bands between the TO phonons and the LO phonons, with polariton wavelengths in van der Waals materials much shorter than the incident wavelength with which they are excited. And the main advantage of phonon polaritons over plasmon polaritons is that as they emerge from phonons, they don't suffer from ohmic losses, so their lifetimes are greater, which, for example, is important for biosensing applications. The thing is that we are limited by the Röstralen bands of the materials, as fundamental studies or applications must be done in those frequency ranges. So as the number of van der Waals materials in which we can excite phonon polaritons is still reduced, for example, here I'm showing you the dielectric constant of molybdenum trioxide and hexagonal boron nitride, where you can see that molybdenum trioxide possesses 3 Röstralen bands, one along each crystalline directions, and hexagonal boron nitride 2. You can think that, of course, the main motivation of this work is about how can we manage to tune or to modify the Röstralen bands of the van der Waals materials in order to being able to excite phonon polaritons in the whole infrared regime. So the solution we propose here is to intercalate alkaline and alkaline earth atoms in the material as a tool for tuning the Röstralen band. So here I show you the material we chose to perform the experiment, which is vanadium pentoxide. And in the right part of the figure, you can see how sodium atoms are intercalated into the structure in certain positions between the layers, increasing the distance between the layers. This is modifying the phonon spectra of the material. So as you can see in the upper left graph, the phonon polariton dispersion of sodium vanadium oxide is shifted to lower frequencies, approximately 30 wave numbers with respect to the dispersion of the pristine material. And this is because the permittivity of the material has changed, and in consequence, the Rostalian bands. Here in this graph, you can see the permittivity of both materials. Solid lines is vanadium pentoxide, and the dashed line is vanadium pentoxide doped with sodium. And on the other hand, the low loss nature of the phonon polaritons is preserved after the intercalations, as we were able to measure polariton lifetimes of 6 picoseconds in the pristine material and 4 picoseconds in the intercalated one. So just to finish, I would like to mention that for our study, we chose sodium as the intercalant atom, but we can use other atoms. And in this last panel, I'm showing you the theoretical phonon polariton dispersion of vanadium pentoxide, sodium vanadium pentoxide, and calcium vanadium pentoxide. And in the calcium case, the dispersion is shifted 100 wave numbers with respect to the pristine material. So as we can expand this to the rest of alkaline and alkaline earth atoms, maybe we could eventually be able to excite phonon polaritons in most of the infrared regime. And that's all. Thank you for your attention.
Mm-hmm. Thank you very much. So I don't see any questions in the chat. Let me ask the following question. So I see that there are a lot of co-authors in your talk. And what exactly your contribution? Did you do some experiments, simulations, or intercalation?
Yes. I do all the near field studies, all the studies with the SNOM, with the scattering type scanning near field optical microscope.
Mm-hmm.
I performed some of the simulation, and also I was thinking I mean, how to obtain this sheet. I don't know how to explain myself.
I see. Okay, I see. So, and we see that in your talk, you showed us the theoretical curves, the dispersion curves for polaritons. Do you have similar one but experimental? Did you try to retrieve the dispersion from the experiment?
Yes. In one of the panels, I mean, in this panel, the dispersion is the experimental one I have extracted.
This is experimental dispersion, I see.
Yeah, and these ones are theoretical.
Because it's difficult to compare experiment and theory. So I see.
Yeah,
mm-hmm.
yeah.
Okay, thank you. Thank you very much. So next talk will be given by Dmitry Orehov from Netherlands, from the Lawrence Institute for Theoretical Physics and Leuven University, and his talk will be devoted to plasmon resonances and tachyon ghost modes in highly conducting sheets. The stage is yours, please.
Hey, hello everyone. I'm Dmitry Orehov. So I will tell about this plasmon resonances and tachyon ghost modes in highly conducting sheets. Do you hear me?
Yes.
Okay. So on the left of my slide, you see the simple example of the system. So this is the two-dimensional conducting sheet with conductivity sigma, and electromagnetic field lives in surrounding three-dimensional space around the sheet. And on the right, you see the main motivating paper, which motivated us, me and my collaborator from MIT, Leonid Levitov, to study this. This was the paper called "What if the film of conductivity exceeds the speed of light?" And actually, if you solve the three Maxwell equations, you find surprising solutions, which are tachyons, which means that the speed of such modes is higher than the speed of light. And the question is how one can interpret such plasmonic solutions and how to observe them. Also, additional motivation is the experimental one, that people already reached the high conductivity regime in two-dimensional electron systems. So our main result is summarized by this slide. On the right, you see the plots of spectral function in two different regimes: in conventional regime, where the conductivity is small, and in the unconventional regime, where the conductivity is high. And you see that actually in the measurable spectral function, there is no tachyons, but the plasmon resonances are anomalous. It means that they became very narrow when the damping rate in the system increases. And it increases, becomes larger than the frequency of the plasmon. So these results were published in PhysRevB paper, the link you see on the left. And now I will describe our results more technically. On the left, you see some parts of calculation. So we derived the dynamical compressibility function, which can be measured experimentally, and the poles of this response function describe exactly that tachyon modes. But when you analyze the behavior of imaginary part of this response function, you see the plot which is shown on the right, which shows that the plasmon frequency becomes stick to the light frequency, but the plasmon resonance itself becomes anomalously shaped, and this represents our main conclusions. So firstly, the width of resonance is still small, even at damping rates much higher than plasmon frequency. Also asymmetric non-Lorentzian shapes of these resonances, and they became more narrow with increasing damping rate. So this is the characteristics of this regime where the formal solutions of free equations are tachyons. And finally, I would conclude that such systems were already obtained experimentally, so it's a question of time to check these predictions experimentally. Thank you for your attention.
Thank you very much. The timing is perfect. I don't see any questions in the chat. So, and a couple of questions from my side. And what are the systems where these tachyons can be observed experimentally? What are the materials?
So the material mentioned here on the left in the paper, it was gallium arsenide heterostructures, which very high mobility.
I see. And the second question, could you show this the next slide, please? And one more, please. Next one. Yes, here we see that at low frequencies, the peak is quite symmetric. This looks like Lorentzian, but then it became very asymmetric.
Yes.
Could you comment on it, on this asymmetry? What is the reason of this asymmetry?
So this asymmetry comes from the fact that plasmon resonance is placed near the light cone branch cut. Mathematically, it means that this response function has a branch cut in the complex frequency plane, and as you see on the inset of the figure, the plasmon pole approaches this branch cut, and together they form such resonance, which is non-Lorentzian.
I see. Thank you
and
very much.
Actually, I would say that the tachyons themselves are not observed, so we cannot travel in time, but they produce such anomalous plasmons as we expect.
Mm-hmm. I see. Thank you very much, Mitra. So
thank you.
Let's go to the next speaker. It's Ana Isabel Fernandez Trigueros Mata from Spain, from the University of Aveiro. And her talk will be devoted to the planar refraction and lensing of highly confined polaritons in isotropic media. So, Ana Isabel, the stage is yours.
Okay, can you hear me and can you see my screen?
Yes.
Okay. So, good afternoon. My name is Ana and I am a PhD student in the nano-optics group at the University of Oviedo, led by Pablo Alonso. And I want to briefly show you one of our latest research projects, which explores the phenomenon of refraction at the nanoscale between strongly anisotropic media. So to demonstrate this, we use as an anisotropic media molybdenum trioxide, a van der Waals material that can be exfoliated. And it has 3 different crystalline axes. So it has a strong anisotropy that translates into the optical properties of the crystal, because its optical response is going to be different along the different crystalline axes. So we also are demonstrating this in the nanoscale. So for that, we use phonopolaritons. It was already explained, but they are waves excited on the surface of materials when illuminated with infrared light. And the characteristics of these waves are the combination of the properties of the incident line, the photons, and the material that supports them, the phonons. Therefore, they are hybrid light matter oscillations. And these characteristics also depend on the substrate, and particularly on the wavelength. So we use a near-field microscope scattering SNOM for nanometer resolution visualization of these polaritons. And this technique consists of an AFM tip that is coated with a metallic material acting as a detector. We can scan and get the phase and the optical amplitude over the sample. So refraction in isotropic media is well understood in terms of Snell's law and the refractive index of the material. And when light hits an interface and passes into a medium with a higher refractive index, the ray bends towards the normal. So this law is a direct consequence of the conservation of momentum on the interface. Sorry. Okay. So here I show you the isofrequency curves, which represent the directions along which light can propagate inside the medium. And what happens is that in an isotropic media, the direction of the wave vector is collinear to the flux of energy, to the Poynting vector, which is, as I said, the energy flow. The Poynting vector is always perpendicular to the isofrequency curve. And in an isotropic medium, the isofrequency curve is a circumference, and in a very anisotropic medium, it can be even a hyperbola, where some directions are forbidden. So in this case, K and S are no longer collinear. And in fact, there might be some point of the hyperbola in which they are almost perpendicular, because as I said, the Poynting vector is always normal to the isofrequency curve. And then this anomalous behavior can occur. Remember that, as I said, we need to fulfill the conservation of momenta on the interface. So to demonstrate this experimentally, we built 2 effective hyperbolic media fabricated by electron beam lithography, one of which is a set of triangles on a silicon dioxide substrate. And we etch the layer of silicon dioxide by reactive ion etching with a fluorine plasma, and leaving these triangles on the substrate. Then we put a thin flake of molybdenum trioxide on top that supports the polaritons. We have 2 effective medium, which is molybdenum trioxide air and molybdenum trioxide silicon dioxide. So the polaritons come through here, through the medium of molybdenum trioxide air, and refract at this interface. While in an isotropic medium, they will bend towards the normal. Here they are bent downwards. So it's indeed an anomalous refraction. We see that here it fits very well with the simulations. So all these findings in anomalous refraction can be applied to develop an optical device such as a lens, and then carefully designing this angle here, almost perpendicular to the asymptote, we can focus the refracted polaritons on a point. And the size of this focus, as we see here, is 240 nanometers for an incident wavelength of around 11 microns. And this is well below the diffraction limit. It's incident lambda divided by 50. And this opens the door to make a flat device, because this is in a 2-dimensional medium. It is the first planar polaritonic lens in a hyperbolic medium by refraction. And if we make the same structure in an isotropic medium, like for example, boron nitride, what we have is that the waves diverge. So that's all. If you have any question, you can ask. Thank you for your attention.
Thank you very much for the good timing. So let me have a look at our chat. I don't see any question. So let me ask from my side. Do you see any real practical applications of these lenses? Because this lens is like 2D lens. It's lens for 2D waves, yeah, for surface waves. And what do you think about possible practical applications of these lenses?
So with this lens, we can control the flux of energy at the nanoscale. So as you can see, we are coming from an incident light of 11 microns to a focus of 240 nanometers, lambda divided by 50, and this can have application, like for example, in biosensing, like we can reach the size of molecules and heat management and optical devices controlling light at the nanoscale.
And what are the maximal propagation constant for these surface waves you can reach in your experiments? I mean, in terms of K-node, I mean, wave number of photon in vacuum.
Which number of what? Can you repeat, please?
So, what the maximal wave number for surface waves can you reach in your experiments? I mean,
wave propagation, you mean?
Yeah, wave number. So, because it's K-node, 2 K-node, 3 K-node. I mean, this. How many wave numbers of photon in vacuum? Because it has dispersion, dependence of frequency on in-plane wave number. What the maximal in-plane wave number can you reach in your experiments?
I think I'm not understanding well the question.
So it's surface waves, they have a dispersion. Could you show the previous slide, please, with either frequency contours? So usually we should normalize the wave number to the wave number of photon in vacuum. So, and what the maximal wave number can you reach in hyperbolic regime?
So we can reach the maximum wave number, but we need to have a compromise between the long wave number, which means a smaller focus of our lens, for example, but then the damping is quite high, so we cannot observe. Maybe we cannot have the focus because the propagation, we cannot propagate till the focus. So yeah, we calculate that a boundary of 62 degrees, a wave vector not close to the asymptote, but not just at the asymptote, because then we cannot reach. We cannot have enough propagation. So yeah, we can get large wave vectors, but not the largest one, because otherwise we cannot observe a focus because of the high damping.
Yeah. Okay, thank you very much. So let's go to the next speaker. The next speaker is Gonzalo Alvarez Perez from Spain, from the same university, University of Oviedo. So please, the stage is yours.
Okay, can you hear me now?
Yes.
Okay, so one of the main goals in nanophotonics is to manipulate light at the nanometric scale, and as we already saw in some previous talks, for instance, in the one by Alexey, there is a limit, which is a diffraction limit, that is hindering this control, because we cannot use directly visible light or infrared light to manipulate it at the nanometric scale. So we have to look for a different way, a different mechanism of light and matter to interact, and one of these alternatives is provided by polariton, which are, as Anna said now, hybrid light matter waves which take place at the interface between different materials. So their properties are a combination of the properties of the light and also the properties of the material that supports them. But if we have a look at the dispersion here, which is the relation between the energy or the frequency and the momentum, we can see that the polariton dispersion is towards the right to that of free space light, which means that for a fixed frequency or a fixed energy, the polariton has a larger momentum. It means has a smaller wavelength, so we can use it to confine this light, to squeeze light potentially at the nanoscale. So these polaritongs are particularly relevant in 2D materials because they are really confined in these atomically thin materials. And the thing is that many of these 2D materials are really anisotropic. For instance, molybdenum trioxide is a biaxial material, which means that the optical response is different along the different directions. So if one of these permittivities is positive, as it happens in some frequency range, and another one is negative, what happens is that these polaritongs can only propagate within some sectors which turn to be hyperbolic. And therefore, there are some directions which are forbidden for propagation. And the question I want to address in this poster is if we can enable propagation of these waves along these forbidden directions for a fixed frequency. And the answer is yes, but we have to combine this material with other materials that also support polaritongs. For instance, here we have MO3 on top of silicon dioxide, which is a traditional dielectric substrate. So the propagation features here are more or less the ones of a bare MO3 slab. However, when we put MO3 on top of a polaritonic substrate, such as silicon carbide, which supports isotropic polaritons, the polaritons in MO3, which are hyperbolic, are going to feel these isotropic polaritons and are going to interact with them. And therefore, we will have a resulting polariton of the whole heterostructure, which propagates along the orthogonal direction, along this direction which I was saying that it was forbidden. So to gain some insights into why this rotation is happening, we study the polariton dispersion in a biaxial slab, which is contained in this paper. It's a bit cumbersome derivation, but you can have a look at it if you are interested. And if we take a cut of this polariton dispersion at constant omega, we can calculate the isofrequency curve, which gives us the allowed directions for propagation. So if we take into account the MO3 silicon dioxide system, we see that the isofrequency curve is like this. So polaritons can only propagate along this direction. But if we put it on silicon carbide, we can see that it's along the orthogonal direction. So actually, to verify this experimentally, what we did was to fabricate a gold antenna on top of these two heterostructures. This antenna is resonant with incident light and launches the polaritons in the structure. And we can see that here in MO3 silicon dioxide, the wavefronts are hyperbolas centered along this direction, while in silicon carbide, they are centered along the orthogonal one at the same frequency and the same incident laser frequency. This only happens within the spectral range in which silicon carbide contains polaritons. If we go out of this range, of course, we have a pattern similar to this one. So what we were thinking is that if we go a bit far away from this frequency, what would happen? If we go to 943, which is only like 9 with numbers away, what we see is this pattern by SNAM. And we can see that there are these kind of rays. And if we calculate the analytical isofrequency curve, we have something like this cross. And what happens here is that this is a fundamentally different curve from this one, because here we have a hyperbola, which is a disconnected curve because there are two branches. And here we have a cross, which is a connected curve. So this is a path connected curve. We can go from any point in the curve to any other within the curve, but we cannot go here. So this is a discontinuous deformation. This is not these curves are not topologically equivalent. This is like if we have to cut this cone to get these two different surfaces. So this is the mechanism behind this topological this rotation of the wavefronts in the structures. And yeah, and yes, it's a topological transition. If you have any questions, I'll be happy to answer, and you can also contact me in this email here below.
Mm-hmm.
Thank you.
Thank you very much, Gonzalo. For timing is also perfect. So next, okay, questions. I see the question, but it's related to the previous talk, I think. So, what do you think? Could you control the directivity diagram of your surface waves using different types of antenna? Not like this, like a plasmonic bar, maybe other types of antenna, maybe chiral antennas or something like this, to control the directivity pattern.
Control the directionality, you mean?
Yes.
Well, I think the directionality is more related to the material itself than to the antenna. Of course, if this material is really anisotropic, so if you tilt the antenna, you will probably have different patterns, but the allowed directions and the forbidden directions are more related to the material itself. So you should combine it with probably some other substrate, or maybe twisting some 2 layers of this material, or combine it with another material rather than an antenna, I would say. The antenna will only change the pattern you launch, but not the directionality in the material, I would say.
Thank you very much.
Thank you.
I don't see any other questions. So thank you very much again. Let's go further. So next talk will be given by Justyna Stachera from Poland. It's Poznań University of Technology. Justyna, the stage is yours.
Hello, everyone. I hope that you see and hear me. My name is Justyna, and I am a PhD student at Poznań University of Technology. I would like to present my result about topic self-assembly of selected viscotic liquid crystals forming Langmuir layers at the air-water interface and on solid substrates. And firstly, undoubtedly, the recent years increased in interest in viscotic liquid crystal due to the ability to combine paramagnetic properties with photoconductivity, and I will focus in an paramagnetic core in my materials. And secondly, viscotic liquid crystals are attractive as multifunction materials due to their self-organization. Nowadays, chemistry synthesis materials which concentration solution, so which these materials can aggregation in this solution. So firstly, we have got a paramagnetic core, and the first step we can use a supramolecular structure, and my goal is a focus on use to a paramagnetic core to create and control organization of molecule or molecular in the monolayer, and the next step layer. Thin layers of DLC we can form by various techniques, for example, drop casting, spin coating, and for example, Langmuir blodgett or Langmuir Scheffer. This technique is very comfortable for me because we can control the surface density and number of layers, but it's very important the orientation, this molecule of the subphase. The two of perfect orientation is a flat of homeotropic to the ground plane. Next, in the figure we can show the schematic of Langmuir technique, Langmuir blodgett technique, and Langmuir Scheffer technique. We can, by the Langmuir Scheffer and the Langmuir blodgett technique, we can deposit my monolayer and later layer on salt substrate, depending of methods, so Langmuir blodgett or Langmuir Scheffer, and depending of substrate. For example, if a hydrophobic on hydrophilic quartz of silicon or atomic smooth substrate like mica. And move to my results. If I would like to talk about my results, I will focus by the dependence of surface pressure on a function and the average surface area per single molecule. And this result is the constant temperature is isotherm, and is very important criterion for me because during the record this isotherm, the same time I can observe the organization of molecule during the form my monolayer and later layer. But I would like to repeat, but I focus on very low values of pressure. So please look this figure that my monolayer is very homogeneous, but in the higher value of pressure, we can see different breedness. So we can propose that the density in my monolayer can change. The second criteria of something more about my monolayers is a compressibility modulus, and this gives me information about phase transition and organization in molecule, and it's very, for me, important. The organization of molecule in the low value of pressure is not rigid, and the molecules are not densely patched. So I can control its organization on the subphase. And the third experiment with control and change potential and of function and a per molecule, and we can see that this figure that the first step of my compression molecule is organization. So the potential is different than zero. So my molecule is the first step oriented, and sometimes I can see dislocated, but it's very important because I can deposit this molecule in this phase on the solid substrate. And independent, I would like the quartz on mica or maybe silicon. I can change my monolayer on substrate, but by measure absorbance of by atomic force microscopy, and we can see that I record the absorbance depends of salt substrate. We can change the maximum of
out of time.
Okay, is finally what I'd like to say, that the Scottish crystal of benzoin from stable and compressible Langmuir monolayers. So the last my sentence, I would like to say that molecule with paramagnetic cores can form stable monolayers. We can then deposit on salt substrates. Is very important in different kind of electronic and supraelectronic, and it's all. Thank you for attention.
Okay, thank you very much, Justina. Unfortunately, we're out of time, so we have to skip question, and let's discuss this presentation in the break. Okay, let's go to next talk, please. This I'm sorry for the pronunciation if it wasn't not correct. Juha Duan from Spain, University of Oviedo. So please, the stage is yours.
Okay, thanks, Mr. Chairman, for the introduction. My name is Jiahua Duan, and I'm coming from University of Oviedo. Today, the title of my poster is the Twisted Nano-Optics, in which we can show you how can we manipulate light at the nanoscale with twisted anisotropic van der Waals crystals. So here I can show you, as well known, the twistertronics is a hot topic in physics because of a lot of the nice rich physics inside included, like the flat bands or topological translation and simple conductivity. here in this famous nature, the researcher find that if they twist the bilayer graphene at a critical angle, or they can call it magic angle, we can see the electronic band structure becomes flat, and they have the strongly correlated system, and they also observe the anomalous superconductivity. And now we are thinking what will happen if we bring this concept of twist in optics realm. So in optics, we similarly, we also have the Isar frequency curve in K-space, like the band, electronic band structure. I think you learned a lot from the previous poster already. So here is if the crystal is anisotropic, we will have the open hyperbola as the Isar frequency curve. Here we have the wave vector, and here we have Poynting vector in real space. Correspondingly, we will have this concave wavefront. Now we are thinking what will happen if we put two layers of this anisotropic van der Waals crystal and rotate them with each other, and it's like we put those two open hyperbola together. Then in this slide, I can show you a schematic of our research when we twist these two layers at a critical angle, or we can call it photonic magic angle. The nanolight in these twisted heterostructures will propagate without any diffraction, and we can call it like directional propagation of light, and we observe unique properties like low loss and highly collimation. So in the third slide, I will show you more details about our research. Here I can show you if we increase the twist angle from the 30 degrees to 90 degrees, when the twist angle is 30 degrees in the real space, this top panel is the simulation, and this one is the experimental results. When the twist angle is 30 degrees, we can see the wavefront is still concave and indicating open hyperbola as the Isar frequency curve. But if the twist angle is 90 degrees, we observe this closed wavefront. More interestingly, if we twist these bilayers at a critical angle, like 63 degrees, we observe this highly guided nanolight inside these twisted heterostructures. That means we observe the canalized polaritons along this direction. It is quite promising for applications such as highly guided light or energy at the nanoscale. And also from here to here, we observe the open hyperbola to close the isotopic Isar frequency curve. We observe the optical topological transition. Besides the twisted angle, we also can change the Isar frequency curve with instant wavelengths. We can see here if the twist angle is 90 degrees, we can see if we increase the instant wavelengths from increase the instant wavelengths, the hyperbola is getting closer and closer to each other, and then they start to touching each other. If they are not touching each other, we can observe two open concave shape wavefronts. But here, if they touch each other, we observe this closed wavefront. So that means we also observe the from the transition, optical transition from the open Isar frequency curve to the closed Isar frequency curve. So that's all I want to show you, and any questions would be highly welcomed. Thank you for your attention.
Thank you very much for the interesting talk and for perfect timing. We have 1.5 minutes for questions. So I don't see any questions in chat. So I would like to address exactly to this red rectangle that you highlight here. It's almost like one-dimensional propagation, or very directive one. So it's look like the system changed the dimensionality. So it's like really a 1D system, like a chain or something like this. And we know that if you introduce a disorder affects in different ways for system of different dimensionality. Like for 3D, 2D, and 1D system, disorder affect in different ways. So like we know that in 1D system, for example, disorder can result in a localization. Could we expect something here? So for different orientation angle, could we expect a different effect of disorder? What do you think?
Yeah, actually, that's a quite interesting question. Here we can see it looks like a one-dimensional system because, but it is a two-dimensional system actually, and this propagates only along one direction just because the ether frequency curve is flat band. So all pointing vector only point along one direction, and we contain many wave vectors, but with the same only one same pointing vector, and it is a completely symmetric back and go forward directions. So I can tell you that if you put the disorder here, it is just like the common reflection as normal claritons. Of course, it will. We need to figure it out based on the momentum conservation law, but it's more or less like the same.
Mm-hmm. I see it will be interesting because if you put some obstacle, of course, the scattering result in different wave numbers, but for all wave numbers, the pointing vector again directed to the same direction.
Yes, that's true. If we put an optical here, and because in this system, the pointing vector only can point along this direction or backwards. So yeah. I think it will all of them it will backwards, reflected backward, and then it's like yes, along one direction.
I see. Yeah. Thank you very much for the very interesting talk.
Thanks.
Let's go to the next speaker. It's Ilya Gorbenko from Yofa Institute and at my university. Ilya, please.
Yeah, thank you for the opportunity to talk here. And can you hear me? Can you see my screen?
Yes.
Okay. Yeah. As was said, my name is Ilya Gorbenko. The title of my talk is Current-Driven Optical Response of Plasmonic Crystal from Dissipation to Amplification. My supervisor is Valentin Kocherovsky, and this work was done in collaboration with Center Laboratories, head of which is Wojtek Knapp. Several decades ago was theoretically predicted that field effect transistor is a very promising device to be a TRIGGERS detector or emitter, and appeared that multi-gated structures interact with TRIGGERS radiation much better than single FETs, which means they are more sensitive. So one of these systems, one-dimensional plasmonic crystal, was investigated by Center Laboratories, and was experimentally observed that this one-dimensional plasmonic crystal amplified TRIGGERS radiation with some value of voltage applied. And appeared the question, why does it happen? So we put our theoretical problem like that. We investigate a theoretical model of one-dimensional crystal consists from alternative strips with different plasma wave velocities. Also direct current is applied, and all the system is in a field of TRIGGERS radiation. We used a pretty standard approach here. We discovered hydrodynamic equations and applied Kronig-Penney model. And to linearize Navier-Stokes and continuity equations, we've substituted velocity and concentration as the sum of direct parts and oscillating parts. So, and I want to mention here that was investigated experimental transmission coefficient, and appeared that in this task, reflection coefficient is negligibly small. So to investigate transmission coefficient, we have to calculate dissipation. So we did so. We calculated radiation-induced correction to dissipation. I show you it in a very simple form, but the main physics you can see here. there is two parts. One is positively defined v square, and another one isn't positively defined, because small v and n are oscillating radiation-induced corrections to velocity and concentration. And V0 isn't voltage, but drift velocity of direct current. So we see that second part is DC controlled, and it can be negative. So these parts lead to amplification when dissipation changes sign. I wouldn't show you the main equation. We don't really have time to investigate it properly, but you can see details via this link. There's our published paper. It's in an open access. But I'd rather show you numerical values of this dissipation as a graph. So you can see that when current is 0, we see asymmetric resonance of dissipation, and with increasing of current, which here is evaluated as ratio of direct velocity to plasma wave velocity. So increasing this ratio, we see that at some value, dissipation changes sign, which means amplification, and physically direct current turns its energy to terahertz radiation. So we've accurately calculated this value. It's inverse square of 3. And to conclude, we've investigated one-dimensional plasmonic crystal using Kronig-Penney model and calculated dissipation, radiation-induced dissipation in the channel. It has a sharp asymmetric form, and it changes sign with increasing of current. And this phenomena is in agreement with the experiment that I mentioned. So that's, I think, all what I wanted to tell you, and I'm waiting for your questions.
Thank you very much. So I don't see any question in chat. So here, we see that it's possible to achieve some amplification. Yeah.
Yes.
But what do you think about possible lasing in this case? Because if you have some amplification.
Yeah, you mean if to focus all that radiation into one. Yeah, but you see, to observe, as I know, I don't an expert in lasers, but as I know, to create laser, you need sharper peak of radiation. So at one particular frequency, but here in plasmonics, as I know, resonances are still not as good as in laser technology. So I think this is one of the problems that would appear. Yeah, but I didn't investigate this problem.
Thank you very much, Ilya. So let's go to the next talk. It will be given by Mats Andreas Jorgensen from Denmark, from Technical University of Denmark. So, Mats, please, the stage is yours.
Thank you. Let me, there we go. All right, so I want to talk to you about the rotating wave approximation and the error that one makes when you use it, especially when you do it for strong coupling systems or for collective effects. So we'll be considering a system in which we have some number of atoms or emitters that behave like atoms that interact by the dipole interaction. They're separated by some distance. And we consider that these emitters can interact via the electromagnetic field. And then we try to see how they emit with and without the rotating wave approximation. So if you're not familiar with it, but you've probably stumbled upon it even if you've forgotten since, the rotating wave approximation consists of, pictorially at least, discarding the interaction mechanisms in the Hamiltonian that are typically considered to be energy non-conserving. So we're discarding the mechanisms whereby an atom is relaxed while still absorbing a photon, or where it is excited while emitting a photon. These are typically considered to be non-conserving. And then we utilize a formalism called multiple scattering theory. In this formalism, the propagator pops out of the electromagnetic field, the Green's function. It takes into account all the possible permutations in which the emitters can exchange this energy between them, so that the light, if one of them is excited, can be scattered among all these emitters. And then we can get a total scattering matrix, which provides us with the resonances, which means we get both the decay rates and the emission frequencies of the system. So when we do this, we get, as I said, the Green's function for the system. And this Green's function typically is just, when you take the whole Hamiltonian into account, is just the Green's function of the electromagnetic field as you would normally see it. But when you use the rotating wave approximation, you get some additional terms on top of this previous result. And these terms are purely real, whereas the Green's function itself is generally a complex function. And the real part of the Green's function is what leads to the emission frequency, or to a change in the emission frequency in collective effects, and the imaginary part is what leads to the change in the decay rates. So we would imagine that an error that is purely real would only change the emission frequencies, and probably not very much because these effects are quite small, but that there wouldn't be any change in the emission rate. And if we consider two identical atoms interacting with one another, that's also what we see. So if we plot both the real and the imaginary parts of the interaction term, we can see in solid here that there is a discrepancy in the real part, and in dashed that there is no discrepancy in the imaginary part. So we would expect that if we are only considering or interested in the emission rates, that we would be fine using the rotating wave approximation. It turns out that the discrepancy here between the real parts in the rotating wave approximation and the full formalism actually tends to a factor of 1/2, which we'll see in a bit. But before that, this was for an idealized system where we have two identical atoms. If we deviate from this system, for example, by having detuned atoms that are not emitting at the same frequency, then it turns out that while in the perfectly idealized situation where we have idealized superradiance, there's no difference. And in the completely detuned case where the atoms don't even speak to one another because they are so different, they also behave like normal. There's some region in between where there's a finite amount of detuning for a given distance between them, where there's an error that is actually quite large. And what you see on these two plots here are the decay rates as a function of distance for a fixed detuning, or for a fixed detuning as a function of distance. Similarly, if we consider more than two atoms, 3 for example, then you can also make a configuration that isn't symmetric between all pairs. So if you make a configuration where the interaction between each pair is not identical, then you also end up getting collective emission that deviates up to a very large deviation compared to the exact result where you include all the terms in the Hamiltonian. And the implications of this is of course that anything that wants to model a realistic system is going to fail if you use the rotating wave approximation in the strong coupling regime, which is in light blue here. And for something like faster resonance, which depends on the Green's function, absolute value squared. Yeah. You're well within this regime where you're actually getting all the error of the rotating wave approximation. That's it.
Thank you very much, Mats. So let me have a look at the chat. Just a moment. Do we have any questions in chat? No, it seems not the question. So could you please maybe specify in some general terms the conditions when the green function in terms of in the rotating wave approximation is still applicable?
You're asking when can you safely use the rotating wave approximation?
Yes.
Yes.
The green function which you could derive in the framework of rotating wave approximation.
Yes. Anytime you're outside of the strong coupling or with higher interaction, you're fine. That's what this plot shows here. That outside of this region here, they agree. It's only inside this region, and this is a plot of distance. So strong coupling was, we made a definition of strong coupling similar to how you have in a cavity. So it's when the chance for reabsorption becomes larger than the chance of the atom just escaping. So it's essentially when the interaction strength becomes comparable to the emission rate.
Mm-hmm. I see. We have also one question in chat from the Neil Carnavan. So, is it true that you just include the non-resonant part of the van der Waals interaction into account?
Of the van der Waals interaction? This is just a second quantization of the electromagnetic field, and I'm not familiar enough with van der Waals as a concept to. I don't feel confident answering that. Essentially, you're just including all modes that are possible and in pretty much required by quantum mechanics, but they're usually discarded because these are terms that die out in the far field.
Okay, thank you very much, Matt. So, do we have a next speaker, Luca Sartino, or not? Anastasia, Daria?
Yeah.
Luca, you're here. So, okay. Yeah. So, the next speaker, Luca Sartina from Germany, from Ludwig Maximilian University of Munich. So, Luca, the stage is yours.
All right, thanks for the introduction. I'm here to show you some works with did at the University of Sheffield, where I had my PhD and recently moved to LMU for a postdoc. The main idea of this work is that we couple two-dimensional semiconductors to gallium phosphide dielectric nanoantennas. They work as an analogous of plasmonic nanoantennas, as you might know. So we use them to confine strongly enhanced near fields at the edges and in the gaps of this kind of dimer types of structure. And by using two-dimensional material, we harness the near field to increase the enhanced light matter, to enhance the light matter interaction. We do this by simply placing these 2D materials on top of the antenna. So we just stamp them with a all dry transfer method. And what we end up is that we end up with an extremely close coupling between the excitons in the confined two-dimensional layer and the near field at the edge of the at the surface of these nanoantennas. So we provide some results a couple of years ago regarding the enhanced light matter interaction at room temperature, where we observe very strongly enhanced PL signal from tungsten diselenide in both in the case of monolayers and bilayers, and also signatures of the Purcell effect. But one of the things that is interesting in this system is the fact that we can also harness strain. Since we, as you can see, like we basically stretch the material, we have found out that we can also have the localization in the same points of both tensile strain and enhanced light matter interaction. This was shown in this second work, where we work both like in theoretical simulations and experimental PL, always everything at room temperature. And we actually show that indeed, like we have like the collocation of maximum tensile strain and of near field enhancement. So what is interesting is because in this work, actually, the idea is that we want to harness these two effects to give enhanced brightness to actually the single photon emitters found in tungsten diselenide, which are usually linked to mechanical deformation or strain. The idea behind this is simply that as we strain the material, we also modulate the band structure, creating this lower potential dips, basically, where we can trap single excitons, giving rise to a single photon emission. Here below, you see the emission, indeed, from like this tungsten diselenide placed on dimer gallium phosphide antennas, taken at the temperature of 4 Kelvin. As you see, like the spectra here is definitely different than the one at room temperature, where we can find highly localized narrow line width emitter on top of the antenna, which are indeed proved to be single photon emitters. This paper has been recently on arXiv and soon to be published. And we actually found out indeed that the coupling between near field and this single photon emitter gives rise to a few interesting features. One of them is the fact that we observe like enhanced quantum efficiency of the single photon emission. And we proved this by looking at gallium phosphide antennas and silicon oxide nanopillars, which provides no photonic enhancement, but provide the strain for localizing the single photon emitters. As you see in these graphs on the top, we show the PL intensity normalized over the excitation power, observing like few orders of magnitudes brighter emission from a single photon emitter placed on gallium phosphide. And this can be firstly understood by the fact that we observe like a few order of magnitudes lower saturation powers, excitation saturation powers in case of single photon emitters on gallium phosphide, which leads to the idea that we basically excite more efficiently our single photon emitting state. We then like look also like the correlation between the intensity as counts per pulse, so like how much photons we actually collect from our emitters as a function of the lifetimes. As you can see, we observe like that on silicon oxide, we have very short lifetimes and relatively low intensities, leading to the idea that the lifetime is somehow limited by no radiative decays. In case instead of gallium phosphide, we observe that even for very long lifetimes, up to 200 nanoseconds, we still collect a lot of photons and a signature of indeed like an enhanced quantum efficiency. So we just calibrated our setup and estimated the quantum efficiency of an average of 20% in gallium phosphide, but up to 80% in some of this single photon emitting state. And finally, another interesting features of this system is the fact that we can excite these emitters at extremely low power. And so we look at the photoluminescence dynamics of these single photon emitters and found out that we can observe a clear rise time in their dynamics.
Try to go to conclusion.
Yeah, so we observe like this rise time. So we lay down some model, and we actually could prove that this is probably this is actually the trapping of dark exciton states in this two-level system, giving rise to the single photon. Thanks.
Many thanks for the interesting talk. We have a question in the chat, and could we expect some interesting maybe features in a Purcell effect when if you will compare maybe single pillar or dimer?
Yeah, there should be some interesting effect because as we see, the dimer is actually like the first idea of like a metasurface. So by coupling more dimers or more disk, you can enhance the near field and thus like enhance also like the Purcell effect.
I see. So thank you very much. Dear colleagues, we are a little bit out of time. So, and let me suggest to start, to make a short break and start in 5 minutes at 6:30 Moscow time sharp, just in 5 minutes. Okay, so please make a coffee or tea, what you would like. Sorry? Okay, so let's start in 5 minutes and 6:30 Moscow time.
Ты написал, Денис? НП присутствует.
Нет, ничего. Я просто иду по списку.
Ладно. Все, ты молодец.
Guys, can you hear me now? Next speaker is Alexey Kuznetsov from Itmo University. Alexey, are you ready?
Yes.
So, okay, could you share your screen, please, and start?
Okay, thank you. So, hello everyone, my name is Kuznetsov Alexey, and the title of my work is Investigation of Various Multiple Combination of Silicon Conical Nanoscatterers. Recently, an increasing attention has been paid to the optical properties of sub-wavelength dielectric nanoparticles. Such objects can be used to create different types of applications, for example, nanolaser, different holographic application, meta lenses, and so on. So in this work, we investigated the fabrication-friendly resonator, truncated cones, and achieve a number of important regimes, scattering regimes. A huge step to the development of highly indexed dielectric nanophotonics was made by opening the possibilities to control multiple scattering and, for example, combine different multiples. And for example, it became possible to realize so-called Kerker effect, which can be used in different application. And it becomes necessary to study the possibility of obtaining these type effects in various type of scatterer geometries. In this part, I talk about the possibility to obtain various type of Kerker effect in silicon truncated cones. The direction of forward or backward scattering, linked by unit vector n, and we consider the case of a plane wave illumination with expolarization. Suppose that we need we don't have backscattering, for example, and we're able to express the forward scattering. We can get scattering amplitudes and then get to relation of coefficients for cross-section for different cases. In this work, we showed the conventional generalized Kerker condition for conical nanoparticles. The dependence on the contribution to the scattering cross-section of each amplitude is calculated numerically and analytically, and we compared with analytical model in Mathematica. Thus, various kinds of Kerker effect and necessary far-field scattering cross-section condition are presented for real silicon refractive index. The next step was about transfer Kerker, which was first described in this work. And the main idea of the transfer-Kercher effect is that we create the combination of multiples featuring scattering to the side only with small forward scattering by optical theorem. In these recent papers, transfer-Kercher was obtained and verified experimentally. Okay, suppose that we can get these equations, and we have got a Kercher effect, transfer Kercher for conical nanoparticles. Another possibilities is to realize the so-called hybrid nanopole state in truncated conical scatterers. Surface is based of such meta-atoms driving mainly useful properties such as zero transmission and phase control. Strong near fields are used for nonlinear optics and Raman application, for example, complex and unusual transmission properties, and so on. We got hybrid nanopole state for cylinder nanoparticles, and then decrease top radius of nanocones. And you can see that hybrid nanopole state is exist, for example, for these conical relations, and it means that we can create hybrid nanopole state in conical nanoparticles for more friendly application geometric form. So thus we investigate the fabrication-friendly resonator, truncated cones, and achieve a number of important scattering regimes. So we got Kercher, different kinds of Kercher effects, for example, conventional Kercher, generalized transfer Kercher effects. We got the result for hybrid nanopole state. This is the start of our works, and the next step probably will be about quasi-bound setting continuum or about superscattering regimes and so on. So that's all. Thank you for your attention.
Alexey, thank you very much. Let me have a look at chat. There are no questions in chat. So, and what do you think about to control like a chirality and helicity in scattering process using a similar kind of particles, so without rotational symmetry?
It's open question because I didn't think about it. So we can cancel that symmetry for our particles, and probably we can somehow to do it. I can't answer. I don't know.
Okay, thank you very much, Alexey. So, dear colleagues, let me check the chat again. So, still no questions. Okay, thank you. Let's go to the next speaker. Next speaker is Gleb Fedorovich from ITMO University. Gleb, are you ready?
Yeah, I'm ready. Do you see my screen?
Yes, the stage is yours, please.
Okay. So, hello, my name is Gleb Fedorovich, and today I'd like to present you our recent work on chirality-driven delocalization in disordered quantum arrays coupled via waveguiding mode. So this work is related to the field of waveguide quantum electrodynamics as part of chiral quantum optics, in which people study interaction of atoms or simply two-level systems by photons through a waveguide. These platforms allow to investigate asymmetric interaction of quantum emitters when radiation to the left and to the right side is different. That can be useful in quantum communication systems. At the same time, these systems suffer from various impurities and disorder, which affect its behavior. So in our work, we have tried to take into account both asymmetry and disorder that have not been done before. So let's proceed to the general description of our model. We consider a periodic array of two-level quantum emitters with a single excitation coupled via waveguide. In the case of a finite system, the effective Hamiltonian can be represented as follows, where omega k is transition frequency of k atom, gamma 0 is a radiative emission rate, and GMN are emitter-emitter coupling constants. So we focus on disorder in transition frequencies. So here delta omega k are normally distributed random values with standard deviation equal to delta gamma 0. So simply delta could be named as disorder amplitude. In order to describe the asymmetry of interaction, we introduce parameter psi, which is naturally denoted as the fraction of coupling constants against and along z-axis. So if psi equals 0, the interaction is unidirectional. If psi equals 1, fully symmetric. The special distribution of eigenstates could be described by the participation ratio value, or just PR, that quantifies the effective number of occupied sites by a single excitation. So if only one atom is excited in the chain, PR equals 1, and this state can be named as localized, while for the chain with all excited atoms, PR equals n, and this state is delocalized or extended. So we characterize the spectrum of finite disordered system with a density of states. Here you can see that for psi equals 1, the dose displays a band gap resulting from the avoided crossing of light with the atomic resonance. As expected, the disorder leads to the formation, to the smearing of the bandage and formation the Orbach tails, in which the states are strongly localized, which can be seen from the corresponding figure B. The similar behavior was obtained for psi equals 0.01, so for the symmetric interaction. In order to strengthen this statement, we have plotted the normalized participation ratio depending on the, for eigenstates depending on parameter psi. Moreover, it is reasonable to compare participation ratio with localization length. So here we additionally plotted analytical expression and numerical one obtained from the transfer matrix method. So again, you can see the region of localized states close to the bandage, while the states out of the band gap behave as delocalized due to the relatively large value of participation ratio. At the same time, in the regime of almost unidirectional coupling, when psi close to 0, all the states become localized. So let's try to summarize all the mentioned above. So we observed the competition between disorder and asymmetry, and here you can see the map of normalized participation ratio for eigenstates close to the bandage, depending on two factors, disorder and asymmetry. So for symmetric interaction, when psi equals 1, the disorder leads to the formation of Anderson localized states in which excitation is localized somewhere in the bulk of the array. So with decreasing the symmetry parameter psi, these states starts to delocalize. And finally, when we reach the regime of almost unidirectional coupling, these states again localized. But we decided to name them as chirally delocalized to underline the difference between local Anderson localized states. So the main difference here is that for chirally localized states, the excitation in the chain is shifted to its right edge, and the explanation is quite simple. So if psi close to 0, almost so any area atom in the chain emits only to the right side and almost nothing to the left. So it's the origin of such behavior. So I think that's all I have for today. Thanks a lot for your attention.
Thank you very much, Gleb. Let me check our chat. Yes, the question from Nikita Lepidin. Gleb, did you check that introduction decay in your Hamiltonian and make it non-Hermitian gives the same result as a density matrix formalism?
I think no, we haven't done it through the density matrix formulas.
I see.
Numerically through the exact diagonalization of Hamiltonian.
Okay, and the question from my side, and here you show that you break the reciprocity using the magnetic field, and is it possible to break this reciprocity with maybe without magnetic field somehow? What do you think?
So here I can say that we need a magnetic field just to collect only transitions with circular dipole moment. So for example, you can take just a quantum dot with this feature, or use, as I know, there are some dechalcogenide metals which have circular transitions with circular polarization. So I can say yes. So the magnetic field here does not play a crucial role. So
okay, thank you very much, Gleb. So let's go to the next speaker. It's Pavel Tankayev, also from Edmo University. Pavel, are you ready?
Yeah, can you see my screen?
Yes, the stage is yours, please.
Okay, thank you. So, good afternoon, dear colleagues. My name is Pavel Tankayev, and my today's talk will be devoted to acceleration of radiative recombination in quasi-2D perovskite film on hyperbolic metamaterial. So nowadays, development of effective optoelectronic devices is actual problem. Most of them made on from semiconductors with high refractive index, and however, even if they have a high internal quantum yield, in real device it will be decreased due to some poor outcoupling and photon recycling. There are a few ways to overcome it. First is simple. It's texturing of a surface, and another one it's enhancement of radiative recombination due to Purcell factor. So in this work, we combine quasi-2D perovskite, which has quite high internal quantum yield, and hyperbolic metamaterial, which has a high Purcell factor. Here, main idea is presented here. We deposit perovskite film on the multi-layered hyperbolic metamaterial, and we find out that from a time-resolved photoluminescence management, that for hyperbolic metamaterial with 7 periods, radiative recombination enhanced 3 times. In more detail, firstly, we did some modeling. We estimated wavelength at which we expect a hyperbolic regime. After that, we numerically calculate Purcell factor, and in the experimental part, we did several measurements of time-resolved photoluminescence for 3 different parts, and we saw that for low intensity, then it's only non-radiative decay is dominated. There are no any enhancement, and with increasing of power, when molecular radiative recombination can dominate, we see 3 times enhancement of radiative recombination. So conclusion, here we predict and experimentally shown fold acceleration radiation recombination in quasi-2D perovskite film on hyperbolic material with 7 layers, and this result can create a new platform for efficient optoelectronic devices. So that's all.
Okay, Pavel, thank you for the perfect timing. We have around 2 minutes for questions. Let me check the chat. No questions in chat. Okay, but I have one question. So here you demonstrate this effect using the 7-layer structures. But did you estimate theoretically a saturation of this effect with number of layers of hyperbolic metamaterial?
No, we just.
What do you think if you will use a larger number of layers? Could you expect the strong enhancement or acceleration of radiation or not?
Yeah, actually, there is some work devoted to it, and in this work, it's theoretical work. They claim that there are some critical number of layers. After that, the enhancement, further enhancement is impossible.
Mm-hmm. Thank you very much. So, still no question in chat. Thank you, Pavel. Let's go to the next speaker. Is Anna Popkova from Lomonosov Moscow State University, and he'll talk about the third harmonic generation in hexagonal boron nitride. Anna, please.
Yeah, thank you. 1 second. Yeah. Yeah, did you see my screen? Good afternoon, everyone. Today I would like to present you my work, which is devoted to the observation of third harmonic generation in hexagonal boron nitride flakes. This work is a result of collaboration between the Lomonosov Moscow State University and University of Technology, Sydney. Two-dimensional materials are modern and promising media which is actively development. Nowadays, the many family of two-dimensional materials, such as black phosphor, graphene, transitional metal dichalcogenides, and others are known. The structure of this material lead to unique optical and electronic properties that are uncommon in their bulk counterparts. And these properties make this material extremely attractive for creating different flat photonics and optoelectronic devices. For example, a lot of ideas have been proposed for creating modulators, diodes, frequency converters, and other devices such as 2D material allow one to achieve significant nonlinear transformation at extremely small thicknesses. But not all the properties of the simplest two-dimensional materials have been studied despite a large amount of research in this area. In this work, they studies the flake of hexagonal boron nitride. These materials possess a high optical transparency, large band gap, high chemical and thermal stability, and excellent oxidation resistivity that is interesting for many applications. Due to the crystal structure similar to graphene and the smooth surface, HBN actively used as excellent substrate for electronic devices based on graphene and transitional metal dichalcogenides. There are many works of the study of the optical properties of HBN, but the third harmonic generation have not been observed. The sample in our work is a set of layered HBN flakes prepared on a fused silica substrate by the method of mechanical exfoliation with the subsequent transfer. The crystal structure of the obtained sample is cluster ideal. Here you can see the typical optical image of the flakes obtained by microscope in the reflection scheme. The sample has area of different colors, which is caused by the interference of light in a film of inhomogeneous thickness. For the further experiment, the set of the flakes was chosen, and the precision thickness of the flakes were measured by atomic force microscopy. The center area of the part with homogeneous thickness was used for further measurements. Third harmonic generation in HBN flakes were measured using hand-built multiphoton microscope, and we measured the intensity map of the third harmonic radiation reflecting from the flakes. the third harmonic signal from the flakes region is 3 orders of magnitude higher than the signal from the fused silica substrate. They measured the spectra of nonlinear signal generated from flakes, and the spectrum doesn't contain any features such as luminescence or second harmonics, indicated that only third harmonic generation is measured in the mapping scheme. The spectral measurements for fused silica substrate performed at our setup demonstrate that third harmonic signal with thickness of almost 3 orders of magnitude less than one from the HBN. This indicates that the value of cubic susceptibility of HBN at least an order of magnitude higher than the one of fused silica. The another method to confirm the nature of observed signal is a measurement of its dependence on pump power. Here you can see this graph plotted in the double logarithmic scale. The signal power follows the expected cubic dependence, and in the double logarithmic plot shows a linear slope of 3.01 that confirm the third harmonic nature of the signal. Unlike the second harmonic generation HBN, which can be produced by a single layer due to the inverse symmetry of the volume, third harmonic is generated in the entire volume of the crystal, whose we observed the thickness dependence, and this dependence can be explained by interference of the backward and frontward propagating third harmonic wavelengths generated in the bulk of HBN layer. To correctly determine the third order susceptibility, it's necessary to determine the dependence of the third harmonic intensity on the thickness. And we calculate this dependence by nonlinear transfer matrix method published by Vitune, and this dependence is shown by red line and and demonstrate the good agreement with the experimental result. They found that the signal of third harmonic has non-monotonic behavior, and for thicknesses smaller than 20 nanometers, the dependence on
out of time. Could you go to conclusion, please?
Oh. Yes, of course. The value of third nonlinear optical susceptibility by this method can be estimated as this value. That's all.
Okay, thank you, Anna. So we have maybe time only for a very short question. Let me check the chat. So the question from my side, please. I see that in the experiment, the third harmonic generation is better when in theory in some region where it should be very low. How could you comment on this discrepancy that in experiment is better than the theory? I mean that when the thickness around 75 nanometers around.
Oh, in this region?
Yes, in this region, yeah.
Because in the calculation we use the ideal structure consists of the 3 layers. Yeah, it's air, HBN, and the substrate. But in the experiment, we can it should be some inhomogeneously on the surface or the air, on maybe between the HBN and the substrate, and this inhomogeneous can influence on our result, because all of this is a result of interference. And
I see, yeah. Mm-hmm. Thank you very much for the answer. Okay, thank you, Anna. Let's go to the next speaker. Next speaker, I'm sorry for the maybe possible incorrect pronunciation, and Remigiusz Kasper Trajanovic from France.
Yes.
Second Lepo. So, Remigiusz, so the stage is yours.
Can you see my screen?
Not yet. Yes, I think almost. Yes, we see your screen.
Okay, great. Thank you. Okay, so I will present my poster. The title is very long and complicated, but the study is actually very simple. So if any of you is familiar with the surface functionalization or the biosensing, you probably know that the thiolated compounds are commonly used and are most popular ones for the functionalization of gold surface. But over the years, many teams have noticed that they are actually not that stable when applied to plasmonic sensors. And this is due to the fact that the excitation of the plasmon causes the generation of the hot carriers that can further on reduce this bond and then therefore break it. And over the years, in the 2000s, when people started first trials on the sensing of the DNA material on the plasmonic nanostructures, they have noticed, as you can see in figure 1, that actually adenine, which is one of the 4 nucleobases of our DNA, gives a very strong surface enhanced Raman signal and attaches to the gold very strongly and is very stable. And therefore it attracts a lot of attention in order to use it for the functionalization of the plasmonic structures. So in our study, we're going to compare the spectra of the monolayer of adenine on gold, of the multi-layer of adenine on gold, in order to identify the shifts and the bands. The crucial thing is that we are gonna irradiate our plasmonic substrate with the near-infrared laser, and this is very important due to the fact that it is 3 times lower energy than the first excited state of adenine, and this is crucial due to the fact that if we were to excite the adenine, the complicated photochemistry may perturbate our study. And we are gonna compare those spectra and draw some conclusions. So the experimental part is very simple. We are gonna get the monolayer through the immersion and the multi-layer through the additional evaporation of the droplet onto the immersion, and then we are gonna follow the evolution of the particular modes during the transient irradiation. And the study is done on the 2D photonic crystals, in this case aperiodic photonic crystal, which fulfills the phase matching condition and also gives us a much higher volume sensitivity than normal nanoparticle assays. Okay, and here we have the results. We have a monolayer and the multi-layer signal. And in the monolayer signal, you can see here the close-up on the ring breathing mode of the adenine, and we can see the peak at 733. And in the multi-layer on the right, we can see that during the irradiation, the original peak of 720 splits, or we can see the appearance of the 733, which was previously visible only in the monolayer. And from this, we draw a very simple conclusion that in plasmonic sensing, a surface coverage is a relative term, because during the excitation of the plasmon, we may have a formation of the new binding sites onto our surface, and therefore its saturation, its saturation may be enhanced by excitation of the plasmon. And in case you may think the study, and this study is actually useful practically, because we may try to functionalize our surface during the irradiation also, in order to fully saturate it, and therefore when applied in practice to the sensors, we can prevent a non-specific absorption of the analyte or enhance our sensitivity. And that's it. Thank you.
Dimigish, thank you very much for the interesting talk and for your timing. So there are no questions in chat, but I would like to ask you about possible plasmonic structure. You consider quasi-crystals and plasmonic crystals. Could you compare maybe the efficiency of the structure with efficiency maybe just with the random plasmonic structures, which are also usually used for surface enhanced Raman spectroscopy?
Yeah, so first of all, the biggest difference are the hotspots, which are not present in the EBL. The one that I presented was EBL fabricated. So the resolution of the EBL does not allow us to get the hotspot as in the wet chemistry method. However, we can get some periods, not in our case because it's aperiodic, but because of its aperiodic, it can easier fulfill the phase matching condition because it's not discrete in the K vector space. However, the biggest advantage is the volume sensitivity, which in the periodic structures is much different than in the simple wet chemistry that can outcouple to the far field only through the dipole modes. The periodic structures can outcouple into the far field through different mechanisms.
I see. Thank you very much for the detailed answer. Okay. Thank you, Remigiusz.
Thank you.
Let's go to the next speaker. Next speaker is Ilya Fratkin from Skolkovo Institute of Science and Technology. Ilya, please, the stage is yours.
Well, thank you for an introduction. Good evening. My name is Ilya Fratkin. I'm a PhD student at Skoltech in group led by Professor Nikolai Gibius, and today I'd like to tell you about our recent study on an adaptation of Fourier model method for optical Morel lattices. So today in the morning it was discussed that several years ago there was a breakthrough in the field of twistronics and some bright physical effects were demonstrated experimentally. As a result, it attracted a lot of attention not only to the twistronics itself, but also to the applications of twistronics to some optical structures. And in our group, we decided to explore some basic metasurfaces that are rotated with respect to each other and are stacked one onto another. And in the case when we consider even the most simple structures of one-dimensional photonic crystals rotated with respect to each other, it becomes two-dimensional, and one of the periods of the structure becomes larger and sometimes much larger than the period of original constituents. So how to compute the spectra in fast way? We'll try to answer this question. So if we apply the standard Fourier model method, which allows us to build scattering matrix which connects amplitudes of plane waves corresponding to different diffraction orders, then it might be done for the original sublattices in a relatively fast way, since the number of needed harmonics is rather low and the convergence is fast. However, when we consider the stack of twisted metasurfaces, then the lattice becomes two-dimensional, the number of harmonics increases strongly, and the computational time in these games is determined by the computational time which we need to compute the scattering matrices of the original sublattices, considering them formally as two-dimensional crystals, and time which is needed to calculate the combination of the scattering matrices. And if we want to speed our computations up, then we need to boost both the first stage of the calculations and the second one. So this first stage is rather simple. Indeed, if we note that the original sublattices are one-dimensional, then we don't need to account for the coupling of all the harmonics with all other. We know that they are coupled just within the subsets which form rows or columns, depending on the considered layer, and therefore we can calculate the scattering matrix block by block, which strongly accelerates the calculations. Subsequently, if we consider the stack which has some gap layer, even a very thin layer between the two sublayers, then we can filter out the high Fourier harmonics that decay in this gap layer due to the strongly evanescent behavior of the field. And therefore, the time spent on calculation of the combination of the matrices saturates very fast, and the overall computational time becomes much lower. On a practical example, which considers two crossed plasmonic gratings, we can see that even without filtering out any harmonics, which corresponds to the yellow line, The computational time scales with number of harmonics right in the same way as the original Fourier model method, but approximately 10 times faster, which is a significant result. Moreover, if we filter out some harmonics, which corresponds to the red and blue lines, then asymptotics is faster, and we can benefit 2 or even 3 orders of magnitude depending on the number of harmonics taken into account. This is the final slide. I just wanted to illustrate that our computational approach might be applied for different problems, and we can consider hybridization of surface plasmons in the twisted stacks, or some effects of strong circular dichroism in the electric photonic crystal slabs of more pattern. Thank you. And if you are interested in some details, you can find them in our recent preprint.
Thank you, Ilya. We have time for one question. There are no questions in the chat, but I have one question from my side. So the different layers interact for high order diffraction order via near field, and especially if you consider plasmonic structures, if the structures are placed very close to each other, it means that you need to count many diffraction orders, so many terms. Is it a problem in your case? And the second minor question is about, this, if you consider plasmonic structures, if you use Fourier model method, because for grading the permittivity function in plane is discontinuous, and when you use Fourier model method, usually you can have some problem with the convergence of the Fourier series to the abrupt function, like a Gibbs phenomenon at the edges of your structure.
Of this structure, of this one?
Yes.
Well, so regarding the first question, of course, it will be some kind of problem if the height between the two layers is less, but typically we need much more harmonics to resolve the resonances in one-dimensional crystal, and therefore, if there is at least 5 or 10 nanometers gap layer between these structures, then it is okay. Speaking about the edge effects in plasmonic crystals, sure, it is a problem, and therefore we need some effective method which converges faster than the straightforward approach to resolve these effects. So if we consider the structure as a two-dimensional crystal, it will be almost impossible to resolve them. But considering it as one-dimensional makes it achievable.
Thank you very much for the detailed answer.
Thank you.
Thank you. So let's go to the next speaker. It's Maria Fernanda Ortega from Mexico. Maria, are you here?
Hello, yes, I'm here.
Hello, Maria. The stage is yours. Could you share your screen, please?
Thanks. I know. Do you see my screenshot?
Not yet. Could you try to share your screen again, please?
Yes.
Yes, we see your screen. Please welcome.
Okay. Okay, do you see all the screen?
Yeah, please welcome. You can start.
Okay, thank you. Hello, everyone. My name is Fernanda Ortega. I'm going to present my master research. It's called Plasmonic Color Generation on Random Surface Arrays of Nanoparticles. This is a numerical approach. I'm going to start talking about surface nanostructure in coloring. This color has attracted a great deal of attention by using environmentally friendly recyclable materials and generating stable, no blanching, viewing angle independent colors with subwavelength resolution and almost unlimited lifetime. A very popular example of this type of coloration is present in the Lycurgoscope or in the stained glass windows of the Middle Age, which retain their colors to these days. This color is named a plasmonic color and has a consequence of the resonant coupling of light and free electrons in metal nanostructures, known as surface plasmons. And their tonality is highly dependent on the optical properties of the metal-dielectric interface and the geometry of the nanostructures where they are generated. It was recently been discovered that it is possible to realize plasmonic colors printing using laser processing and on disordered arrays of nanoparticles, which can support plasmonic resonance in and between spanning the visible light spectrum. And well, the random distribution of nanoparticles increase the probability of tuning different plasmonic colors on the same surface by varying interparticles distance with change in the density of nanoparticles or the size. In this way, surface treatment via ultra-short pulse laser irradiation allows modifying and carefully design a nanostructure surface using as main channel the excitation of the surface plasmon polariton. This plasmon is confined to the surface and can be excited by light by scattering the surface rawness. And this phenomenon results in the confinement of the energy in specific regions known as hotspots. And this leads to local heating of the materials, which enables merging and reshaping of nanostructures. On the other hand, the surface color is a consequence of the excitation of localized surface plasmons, which are excited inside the nanoparticles. And the resonance of this plasmon occurs at a specific frequency that depends on the morphology of the nanostructure. This resonance behavior responds to the selective absorption of light inside the materials, which will be seen as the generation of plasmonic colors in bulk. This is the principle, the physics of the plasmonic color. And well, in this work, we demonstrated theoretical approach to the laser printing of plasmonic colors using random arrays of spherical golds nanoparticles placed on thin gold film on whose average density can be modified by laser irradiation. The main idea was to propose an optimal design for their fabrication, where variation of the radius and density of nanoparticles will allow us to tune different plasmonic colors. Now, how we can do it? A numerical analysis was performed using a multiple scattering vectorial model via surface plasmon polariton interactions due to surface nanoparticles to simulate the excitation and scattering effects of surface plasmons. Via surface plasmon polariton interaction due to surface plasmon nanoparticles to simulate a excitation and scattering effects of surface plasmon polariton on the nanostructure surface. And the system response is analyzed with the dyadic ring function, which calculates the propagation of the incident field from a source point to an observation point. And the versatility of the distance between these points is what allows the model to calculate the interaction in both the near field and the far field. And one of the objectives of the investigation was to simulate
You're almost out of time. I'm sorry.
Oh, okay. We simulate images of the first harmonic for obtain the reflection spectra. And this spectra, we use the system of psi-xj color space for obtain the color associated with this surface. Well, this is a resume for my investigation. And this is the result of this research open avenues for a new numerical analysis technique that facilitates the design of nanostructures for printing plasmonic colors by laser irradiation. This is all. Thank you for your attention.
Thank you very much. So there are no questions in chat. So, and the question from my side, and what the maximal, what do you think, what the maximal, like a footprint of the image that you could fabricate with this method? What could you comment on it, please?
Sorry, I don't understand your question.
What's the maximal size of the sample of some picture that you could fabricate using this method? What do you think? It will be 1 millimeter, 1 micron, or maybe 1 centimeter.
Well, the resolution can be sub-wavelength.
Not the resolution, the
nanoparticles.
maximal size of the sample.
The minimum size of sample is 1 micron. For see the color in a microscope, optic microscope. Less of that, we can see the color. So the minimum of the sample is 1 micron.
Okay, thank you. Thank you.
Yes, thank you.
Yeah, let's go to the next speaker. It's Dmitry Chermashontsev. I'm sorry for the maybe possible incorrect pronunciation.
That's okay.
Yeah.
Chermashontsev.
Chermashontsev Dmitry from Skolkovo Institute of Science and Technology and Moscow Institute of Physics and Technology. Dmitry, the stage is yours, please.
Yeah, thank you. Could you see my presentation?
Yes, we see.
Okay, I think we can start. In my talk, I'd like to tell you about diagonal surface waves in the interface that's formed by the materials with negative anisotropy. A few words about diagonal surface waves. That's lossless electromagnetic waves that can propagate along the interface of two dielectric media. And previously was stated that these waves could exist only if at least one of these dielectric media has positive anisotropy. In our work, we, with my colleagues from Skoltech, we try to answer the question about is it possible to obtain such waves in the materials with negative anisotropy? And what is few words about the anisotropy? What is the positive anisotropy and negative anisotropy? The positive anisotropy, as you can see in this figure, just a moment, I'm use a laser. In these figures, the positive anisotropy in axial materials corresponds to the materials with the extraordinary refractive index more than the ordinary one. And the negative material is vice versa. Yeah, diagonal surface waves is a very interesting waves because they lossless. It means that can propagate on the interface without loss and infinite in the infinite distance. And also they are electrically polarized. That's also very interesting because classically we have, for example, for waveguide modes, we have only linear polarization. Yeah. And what we obtain, we find that in presence of special boundary conditions, when we have a perfect electric conductor or metal walls near the special waveguide that you can see here, this waveguide is formed by two anisotropic materials with twisted orientation. We, in our work, we consider the angle of 45 degrees around the z-axis, and the diagonal surface waves in such a structure can propagate in the bisector or formed by these two optical, by the bisector of the angle or formed by these two optical axes of dielectric crystals. Yeah, what we did, we consider that the diagonal surface waves can be considered as a decomposition of the two lowest waveguide modes, and then we use the theory of perturbation for the small anisotropy limit, because classically we have the most materials, for example, in optical range, have a very small anisotropy contrast between extraordinary and ordinary wave. And then we find that by using such approach, we can find the analytical solutions of diagonal surface waves, diagonal surface waveguide mode, because it's not really classical diagonal surface waves, because classical diagonal surface waves exist in the infinite interface, and in this case, we have some type of Diagonal surface waveguide mode. And we find that it is possible to obtain the dispersion equations for such type of surface waves. You can see this equation here. The interesting point that this wave has a cutoff point when it intersects with the dispersion of T, the lowest TE mode of the waveguide. And also we calculate the by our theory, the distribution of field components and obtain a very good agreement with console simulations. Actually, this theory was devoted to the case of perfect electroconductor boundary of the waveguide, but in practice, it is some artificial, and we should use real materials with the skin layers and losses, and we consider such a structure a cupron lithium niobate cupron plane waveguide, and calculate numerically the Diagonal surface waves for such a waveguide, and obtain that the field distribution of this mode is changed, but practically this mode can be observed. And here you can see this, the dispersion curve of our waveguide modes. And here you can see the figure of merit, which show how long this wave can propagate, how much wave length it can propagate before it completely decay. And I think that's all for my today's speech. Thank you for your attention. If you have any questions, I'll be happy to answer them.
Thank you, Dmitry. Let me check the chat. No questions in chat. So, could you show, yes, this slide is some practical implementation. And what is the wavelength here do you consider?
Yeah, here we consider the wavelength of 4 micrometers.
4 micrometers.
Yeah. Oh, 4,000 micrometers. Sorry, 4,000 micrometers.
Oh, so it's okay. I see. And do you have in mind maybe some experiment where you would like to retrieve or extract the dispersion of Diagonal surface waves and some maybe geometry of this experiment?
Yeah, actually, we want to start the experiment with our colleagues from Metmo University, but we plan to do it in metamaterial structure and for much higher wavelength, much longer wavelength. Yeah,
I see.
But we plan to do it.
Okay, thank you.
Thank you.
Let's go to the next speaker. It's Valery Kondratiev from Metmo University.
Good evening, dear colleagues. Do you see my screen?
Yes, we see.
Okay, then I will start. Good evening, dear colleagues. My name is Valery Kondratiev, and my post is dedicated to probing guided monolayer semiconductors polarities below the light line. So, main idea behind our research was to probe polaritons below the light line, as the title said. So, what's polaritons? When there's a transition in material interact with confined optical field in optical microcavities or in optical microcavities, there's 2 hybrid states appear, and they dedicated itself in dispersion as splitting between optical mode and resonance transition, and the splitting is called Rabi splitting. Polaritons in TMD can be achieved due to coupling between external resonance in TMD monolayer and optical cavity. It was realized in different works, and all these works use either or Bragg mirrors, diffract gratings, couplers, decouplers, or plasmon materials, and this is a huge fabrication step in such devices. So in this work, we propose a device without any fabrication, any advanced fabrication. So our sample consists of tungsten discrete layer placed on optical waveguide made from tantalum catechside. So we expect our dispersion to be in a high, in a large K area. So to probe these polaritons, we used solid emission lens technique employed with focal backfocal plane. Sorry. So we tested this technique on silicon waveguide and already successfully published this work. The link you can see on the right side of my page. So what is this solid immersion lens is given to us? It's allows us to probe wave vectors in about 2 and 25 of wave vectors of light. So in vacuum, due to attenuated total eternal reflection phenomena, we numerically calculated dispersion in using a Fourier model method, and in this and in this part you can see the numerical simulation and the corresponds experimental data. So this data corresponds to pure waveguide without any monolayer. So after that, we made a sample with our monolayer on it and perform measurement, and you can see that we shift speaking between optical mode and external resonance in our structure. But the main feature of this setup is that we can tune our losses in optical waveguide to tune the coupling strength and then the rubber splitting of our system. And in this plots, you can see that this distance between our single selenide prism and our tungsten discrete layer, we can tune not only in losses in our waveguide, but we can tune rubber splitting of our system. The peak in the middle figure corresponds to the optical coupling between single selenide prism and our waveguide. And in this case, we can calculate radiative, non-radiative losses of our waveguide. So with this, I want to say that we propose a new technique to probe polaritons in TMD-based structures. Thank you for your attention.
Valery, thank you very much for the interesting talk. There are still no questions in chat, but I have one question. So, yes. About comparison between experimental and theoretical data, we see, for example, at the left panel that the waveguide mode is observed as a dip because it's like a black color, as I expect, yeah. But in the in simulation, but in the experiment, the waveguide mode looks like a bright at the right panel. Yes, for example, so. Yes. Could you comment on it? Why this color?
Yeah, I see a question. So this shape of our waveguide mode is due to that we used in this experiment we used objective which used for near range, and due to this aberration, we see that our mode not in the right shape. So this is like an experimental feature.
Okay. Thank you, Valery. So let's go to the next speaker. Next speaker is Dmitry Tsikhanok from Belarus State University, Institute for Nuclear Problems. Dmitry, are you ready?
Hello. Can you see me? Can you hear me?
Yes, we see you. We hear you well. Could you share your screen, please?
Can you see my screen now?
Yes. Please start.
Okay, great. So, my name is Dmitry Tsyganok, and the topic of our study was the effect of interaction between layers in HBM graphene heterostructures deposing on silicon oxide probing by Raman spectroscopy. Modern devices such as various sensors and modulators are built on the basis of boron nitride and graphene heterostructures. And Raman spectroscopy is a very fast and easy technique to investigate the electrical and structural properties. In this work, we used Raman spectroscopy to demonstrate which mechanisms and effects contribute most to the intensity, frequency, shape, full width that have magnitude of D, G, and to the modes in case of HBN and graphene heterostructure deposited on silicon oxide substrate. Mentioned parameters, as you can see, are mostly determined by the strain effect, the doping effect, the interference effect associated with boron nitride and silicon oxide thicknesses, and the orientation between boron nitride and graphene. During our work, the measured values of the intensity ratio of 2D and G peak, as you can see here, increased this up to 2 times when graphene is covered by the exfoliated boron nitride. I won't stop on the assembly of heterostructure. Main principles, you can find the article behind this QR code. We investigated our heterostructure with atomic force microscopy to determine the thickness of the top boron nitride layer, and the found thickness was about 50 to 55 nanometers. But as you can see at the figure 2B picture here, there was a little gap, the area with the gap between boron nitride and graphene, which can be seen here. At the figure 4, you can see the Raman mapping normalized to G peak intensity spectra of the heterostructure and at 532 and 473 nanometer laser wavelengths. As you can see in the figure 4E, for the 532 nanometer laser, the ratio of intensities of 2D and G peaks, corresponding to 0.3, which can be found over here, and 0.1, are 2 more times bigger for the area that is covered with boron nitride. Full widths that have magnitude of the 2D peak indicated that there is a slight misalignment between HBN and graphene. As the situations are different for 473 laser and 532 laser, we can propose that the intensity ratio is strongly dependent of the laser wavelengths. As you can see at the figure 5D, the presence of the HBN layer on top of the graphene leads to a mechanical strain, but at the same time decreases the doping level. So we eliminated rotation orientation effect. For the interference effect, to model it, we used a multi-reflection model, and the results of this modeling for 2 different wavelengths you can see around here. So for our heterostructure, it belongs to the area right around over here. And as you can see, the impact of interference effect is very minor. But as well, you can produce heterostructures that belongs to these areas in which the impact of interference effect will be much greater. Well, as for doping effect and strain effect, the situation is a bit tricky because there is no yet complete theoretical modeling models. The models suggested here and here contain many empirical constants that can be proposed only for one certain case, and we couldn't really numerically evaluate the impact of doping effect and strain effect at our heterostructure, but as we can see, these two effects didn't give any major impact on the intensity ratios. So we assume that
Dmitry, you're almost out of time.
Close interplay of doping effect and strain effect make major impact on the intensity ratio. So obtained result can be used for monitoring of graphene-based device, as I said at the start of my speak. So that's all for me. Ask any questions.
Thank you, Dmitry. Let me check the chat. It seems that still no questions. So I have a question about the strain effect in maybe in twisted structure. It seems that there was some question about the mismatching between crystal and lattice when you use like heterostructures with van der Waals heterostructures. But what do you think about strain in twisted structures, and could you detect it with Raman spectroscopy, and what we can expect?
Well, if we speak about twisted structures, of course, as you can see over here, strain effect gives main impact on G mode. So in case of twisted structure, I can assume that in case of, like I say, angles that are significantly more than in our case, which they have a very slight misalignment, we can see, I bet, the decrease of the intensity ratio, because G peak will rise a bit.
Thank you very much, Dmitry. So, and the last but not the least speaker for today, it's Vadim Shibashov from ITMO University. Vadim, are you ready?
Yes.
Yes, the stage is yours, please.
So, do you see my screen?
Yes.
First of all, I would like to apologize for the format of my presentation. I didn't notice the template. I'm really sorry about that. So if anyone is interested, I surely can send this presentation via email, for example. And now to the content. I would like to present a project on anomalous exciton Hall effect. I was working on under the supervision of my scientific mentor, Valery Kozin, and in collaboration with two other professors. So I would like to start with the motivation. In 1861, Thomas and Hopfield pointed out that exciton in presence of magnetic field acquires a dipole moment which is perpendicular to both the magnetic field and the direction of propagation. Thus, from a classical point of view, exciton, while scattering on charge impurity, its dipole moment will interact with electric field generated by the charge impurity, and to minimize its potential energy, the scattering will be asymmetrical. And this idea lies in the foundation of our work and serves as a motivation to consider the system. So in our work, we consider the exciton in a quantum well, and the exciton scatters on the charge impurity in presence of magnetic field. And the scattering is asymmetrical, and we wanted to find the strength of the effect. And under the strength, we considered the Hall angle. So we start by introducing the full Hamiltonian. We found the matrix elements of this Hamiltonian, the scattering potential for this Hamiltonian for the two regimes of weak and strong magnetic field. then solving the Lippmann-Schwinger equation numerically, we found T-matrix elements, and using the Boltzmann equation, we found the distribution function. From distribution function, we calculated the Hall angle, which is shown in the second figure, and the results were obtained for the weak magnetic field and strong magnetic field, which is sometimes called magneto-exciton regime. As was mentioned in the motivation to the problem, it based on the interaction between the dipole moment and the electric field. So we calculated the dipole moment, and it turned out that it reaches its maximum value in the non-perturbative regime. Thus, we assume that our effect has the greatest strength in the non-perturbative regime. Then we also introduced the symmetrical quantity. It can be measured, for example, in experiment and compared to the result obtained theoretically. So in conclusion, we examined a new effect, the exciton asymmetrical scattering on the charge impurity in presence of magnetic field. The strength of the effect was about 1% in weak and strong magnetic field, but can be much higher in non-perturbative regime. Thank you for your attention.
Thank you very much, Vadim. Let me have a look chat. I think everybody tired. It's the last speaker for today. There are no questions in chat. So, could you comment on why we need charged impurities? It's my first question. Could you consider maybe other types, maybe not charged impurities? And effect of the mobility of exciton and propagation length that you need to observe this effect in experiment.
So about the first question, the charge impurity was crucial for our problem because we our effect is based on the interaction between the dipole moment and the electric field, and the electric field is generated by the charge impurity. So it was necessary for the material to have charge impurities in it for our effect to happen. And can you please repeat the second question?
So the question about experimental observation of this effect. I see that this is just a theoretical prediction. It's some quantum well. So did you estimate some practical implementation? I mean, some materials and what the quality of exciton do we need, and is it implementable in practice for today or not?
Yeah, we hope that it can be implemented. Unfortunately, we didn't make this experiment in reality. It only theoretical calculation. The parameters were used for the two-dimensional gallium arsenide, and we have, for example, the system can be realized as on the first figure. The excitons are generated by the light. They are moving to the one direction, and there are impurities on its way. The exciton scatters on impurity, and due to the interaction between the dipole moment and the electric field, the exciton scatters mostly in some direction.
I see, because I also see in the panel B, the magnetic field is 18 Tesla. So
yeah,
it looks quite huge. It's 18 Tesla.
We were trying to use the it's for the strong magnetic field regime, and we chose this because I don't know, because it was the strong magnetic field regime, and yeah.
I see. Okay, Vadim, many thanks for the interesting talk. So, dear colleagues, I think the first day of our school is finished. So we are waiting you tomorrow. And let me remind you that tomorrow the day will start from the practical classes, which will be given by Professor Alexey Nikitin. Then Professor Pablo Alonso Gonzalez will give a lecture on hyperbolic nano-optics. And then Pablo, the second lecture of the Pablo will be from the experimental lab. So I highly recommend you to visit it. It should be interesting. And tomorrow Professor Javier Garcia de Abaja will close the second day. So, dear colleagues, so we're waiting you tomorrow. Please welcome. So, for today, our school is closed. Thank you very much for coming.